Good evening everyone. Welcome back. Hi, good evening everyone. We have started the class. Alright. Can you hear me? Quickly write down in the chat box if you can hear me and you can see me clearly. Good evening. Good evening. Everything's clear? Quickly write down in the chat box, dosto, confirm it if you can hear me clearly. Alright. Okay. So, dosto, welcome back. Welcome back to another one-shot lecture for physics. And in today's class, we are going to talk about the first part of class 12th NCERT. Alright, so you can hear me? Very good. Very good. Great. Hi everyone. Hi Sheikh. Hi Nasima. Hi everyone from the Yaqeen English batch. Good evening. A very good evening to you all. And welcome back. So just like we completed the first part of class 11th NCERT last week, right? Today we are going to do the same thing with class 12th. Hi everyone. Hi Vivek. Hi Kirti. Hi everyone. Everybody is ready? So first let me explain that for whom this class is going to be important, who should see this class. So anyone who's preparing for physics, either you are preparing for your board exams, right, or you are preparing for your midterm exams, or you are preparing for NEET, as I believe most of you are preparing for NEET, right, and anyone who's preparing for JEE as well. So today we are going to start with the very basics. We are going to complete each and everything that is given in NCERT, right. The plus point of this class is that I'm going to cover all the derivations that is given in the NCERT. Plus along with derivations, we are going to also do numericals. So this class is going to cover almost everything, right. So we are going to cover theoretical part, derivations, then we are going to talk about numericals, and I have got some special notes for you. So I have broken down the concepts into some small notes. So get ready with a pair of pen and copy, and today we are going to talk about some of these chapters, right, starting from electric charges and fields, then electrostatics, potential and capacitance, right. Clubbing these two, we often call them as electrostatics, right. So basically the whole of the first part, the first book of NCERT, we can call it as electromagnetism. We are just dealing with electromagnetism in the first part, right. Then after electric charges and fields, I'm going to, as I have told you, I'm going to cover all the derivations, Gauss law, and in electrostatics and potential and capacitance, we are going to talk about the derivations of capacitance as well. Then in current electricity, we are going to talk about the derivations of drift velocity and all. Then we are going to talk about magnetism. So here we are going to talk about charge. When charge is when the charge is going to be at rest, then charge is going to move. Then we are going to talk about magnetism, and the last part is going to be electromagnetic induction and AC. So the only thing that you have to do is you have to stick with me till the end of this class, right. Only then you can have the maximum, you can take out the maximum benefit out of this live class, right. How many hours, sir, are you going to take? So just like we did in the last week, we completed the first part and we did not look at the clock. We were just going through each topic one by one, covering theoretical as well as numericals, right. So same thing we are going to do in this class as well. Hi everyone. Hi Pawan. Hi Shri. Hi Navya. Hi Divya. Hi everyone from the yes, I do know that you have got a I do know that you have got a biology class at 5. Do attend your biology class. I will be still here when your biology class will over, right? No, no, you must attend your biology class. Please, please, please. You must attend your biology class. You can then come back. You will find me here only, right? So, I will be here for the longest time. So, do not worry. But yeah, please come back. Somebody has said that you have to sing a song at the end of the class. So, if there is a certain amount of students in the class till the end, then definitely I will do that. Okay, I will do that. Chalo, without wasting any more time, I have already told you for whom this class is going to be for, right? Now let's start the class. Everybody is ready? Quickly tell me in the chat box if everybody is ready or not. So we are starting our class with electric charges and fields, right? That is the very first chapter of your class 12th physics. Well, before starting this chapter, it would be actually great if I'll tell you the whole of the game of class 12th first part of NCERT, right? The first part of NCERT, as I have told you, it basically deals with the concepts of electromagnetism, Now, basically in this branch of physics, we are going to talk about charge, we are going to talk about the electrical phenomena of charge, we are going to talk about the magnetic phenomena of charge, right? So basically we are going to talk about charge and phenomena related with it, right? Hi everyone, hi. Yes, I am going to cover the derivations as well. Right? So in electromagnetism, if we are going to talk about, we can actually break this huge branch, right? I mean, this is a very huge branch of physics. This huge branch into further two branches, and these are, first is electrostatics, and the another one can be called as electrodynamics. Although you might have noticed this thing, that we usually don't use this word a lot, that is electrodynamics, right? Electrostatics is being used quite widely because the first two parts, first two chapters comes under this branch, right? Comes under this thing. And the second chapter's name is actually electrostatics, potential and capacitance, but this term is also this term is totally fine, that is electrodynamics. And now let's start with why we are talking about this, why we are not just starting the chapter, because before starting the chapter, it would be better if you know that what you are going to do for the next few days, or let's say what are going to be the next few chapters that you need to learn, right? So in your head, in your brain, the roadmap must be clear, that first you have to learn electric charges and fields, then you have to learn electrostatics, and then you have to learn current, electricity, then we can talk about magnetism. So the flow should be something like this only, right? We really can't say that, okay, let's start with alternating current. This happens at a few places. You must be knowing this, that what happens, that the two teachers teaches, one of the teachers starts with electrostatics, the another teacher starts with alternating current. So that's not possible. If you are going to really say that we really have to first understand the topic, then we have to cover it. Then the correct way to do is that first let's talk about electrostatics, and I am going to also talk with all of you also, right? Yes, this is going to be quite sufficient, right? Sir, in our school still wave topics remaining chapters. Okay. Yes, we are going to talk about some MCQ questions as well. We are going to do MCQs, right? Next thing is, let's come back over here. So the first part under electromagnetism is electrostatics, and if we are going to actually talk about electrostatics, let's break down this word. This word, that is electro, just the word electro basically means charge. We are talking about charge, or we can actually say is that we are going to talk about when charge is at rest. When charge is at rest, right? So basically In electrostatics, the main concept, the basic concept, the most foundational concept is that the charge is not going to move, right? I know I have repeated myself couple of times, but this is that important. We are going to actually, many times we are going to, when a question is going to come that why this is happening, we are going to say because we are learning electrostatics. According to electrostatics, a charge cannot move, right? According to electrostatics, a charge cannot be under any acceleration, right? So this is very important, that whenever we are going to talk about electrostatics, and in this electrostatics we are going to talk about the first two chapters, the charge will always remain at rest. After this, in electrodynamics, charge can actually move. Charge can move, so charge will be in motion, right? After this, if the charge is still in motion, then again we are going to break down it in couple of topics. Like for example, is when charge is moving with constant velocity or in uniform motion, right? Or it's really not like the uniform motion of kinematics, so it is a little bit trickier than that, but we are just using some terms, from the kinematics, right? Why I am saying that? Because this is all microscopic, right? We really can't, we are going to use some of the kinematics over here as well, but you need to understand it, but this is a superficial level of understanding. If you really want to talk about electrons, if you really want to talk about charges, these you will have to actually study quantum mechanics when we are going to talk about what? When we are going to talk about like quantum mechanics, right? Till then, this is actually all doable, not that bad. So we are going to talk about actually current electricity over here, and with current electricity, we are going to talk about magnetism, and when the current is going to change the direction in a particular circuit, we are going to also talk about the electromagnetic induction and AC. So in a page we have written down each and everything that we are going to do in today's class, right? Nothing's left. I know that we have got like 2 chapters in magnetism. So we have got moving charges and magnetism, and we have got magnetism and matter, right? So here are the 2 chapters. The 3rd chapter is this, 4th and 5th, and then 6th and 7th. What about 6th and 7th? That electric charges and fields and electrostatics, potential and capacitance. Got it? Everything's clear? Done? Will the charge have both electric field and magnetic field? Let's figure it out in this class. After this class, you will get to know that whether the charge has just got electric field or it also has magnetic field. We are going to figure it out. So let's start today's class when we are going to talk about electric charges and fields. Let's start with the first thing. I know it's quite basic, but let's start with it. And that is going to be, what do we really mean by charge? What do we really mean by charge? How do we define charge, right? It's quite a basic question, and whenever somebody asks you, you might say that, oh, charge are of 2 types, positive charge and negative charge, but that's not the correct definition. That's the answer for a question like, how many different types of charges are there? So there are 2 types of charges, positive charges and negative charges. But what do we mean by charge? So charge is basically a basic property of matter, or a basic property related with mass, according to which, or we can say that because of which another charge can experience electrical phenomena or magnetic phenomena, right? So I'm going to write it for you. So a charge is something because of which another charge can experience electrical phenomena, electrical and magnetic phenomena, electrical and magnetic phenomena, right? Now of course charge are of 2 types, positive charges and negative charges. That is quite basic, right? We are not going to talk about protons and electrons. We are going to talk about positive and negative charges. Then we are going to say that out of these positive and negative charges, surely we are going to say that only electron has got mobility. Only electrons have got mobility. That means only the electrons are transferable. So let's suppose that we have got two bodies over here. We have got two bodies over here, and out of these two bodies, this is a positively charged body and this is a negatively charged body. So this means that this body must have transferred its electron to some another body, and this means for this body we can say that this body must have accepted some electrons from some another body. That's the most basic thing, that protons are never transferable, right? As far as we are not talking about nuclear reactions or anything, the number of protons is never going to change. Only the number of electrons can be changed, most basic thing, and that's why we say that only the electrons have got this thing that is called as mobility. What do you mean by mobility? It means that they can be they are the only entities which are transferable from one body to another body. Now charge is a quantity, right? By the way, it is not the fundamental quantity. Charge is not a fundamental quantity, right? The next thing is that if it is a physical quantity, it will be measured in some quantity. It will be measured in under certain units. So it is measured in Coulomb, right? It is measured in Coulomb, denoted by capital C. So this is the SI unit of it, and it is a scalar quantity, right? Have you noticed I said that this is not the fundamental physical quantity. We have got 7 fundamental physical quantity: mass, length, time, and then we have got amount of substance, temperature, light intensity, and what else? Amount of substance, right? Am I missing it any more? So these are the, and current, of course. So these are the 7 fundamental physical quantities. Why we have taken these as fundamental quantity? They have been chosen randomly, right? So charge is not one of them. So the SI unit of charge is Coulomb, and when we are going to talk about the dimensional formula, the dimensional formula of charge will be written using the formula of current, that is current times delta T, right? So this is very important. Quite basic, but still important things over here, right? So these are the, I'm going to speak with you, I'm going to talk with you, I'm going to explain everything, then I'm going to also talk about the notes over here. So electromagnetism is the science of combination of electrical and magnetic phenomena. Electromagnetism can be divided into two things, right? First is electrostatics, where we are going to just talk about the charges which are at rest. Then in under electrodynamics, we are going to just talk about the charges which are in motion, right? And under this, we are going to talk about all of those magnetic phenomena, right? After this, we are going to talk about charge. We have written it as a property acquired or natural. What do you mean by acquired or natural? That means you can actually also give charge to some another body, right? You can also give some charge to another body. So it is a property acquired by an object due to which it produces and experience electrical and magnetic phenomena, right? So it can also produce these phenomena, or it can also experience these phenomena. Like for example, as you always, I mean, you have been talking about this thing that like charges repel each other, unlike charges attract each other. So these are the electrical phenomena that we are talking about. Then types of charges: positive charge and negative charge. Positive charge basically means deficiency of electrons compared to the protons, and negative charge basically means efficiency of excess of electrons as compared to the protons. Are you getting it? Done? Everything's clear till here? Right? So we are starting from quite basics. These are the some of the things that you are talking about that. So SI unit is Coulomb, but we are going to use some more let's say practical units. So practical units are going to be millicoulomb. So whenever the prefix comes, whenever this prefix comes like milli, denoted by small m, just write 10 to the power minus 3 coulomb, right? Whenever the prefix comes micro, just write 10 to the power minus 6 with whatever the suffix is right now, that's minus 6. Then we are going to also talk about the nano. So nano coulomb is 10 to the power minus 9. Mostly we are going to just talk about these ones, right? So it's not like you are going to often see pico or something like that. Most oftenly you are going to just talk about, either you are going to talk about coulombs, right, in and the numbers is going to be written in a standard form, or you are going to talk about some numbers like this. So these are some of the more practical units. After it, what is the CGS unit? That means if you are going to talk about in the centimeter gram seconds system of units, so it is known as electrostatics unit, and that is written as ESU, and this is 1 coulomb is 3 into 10 to the power 9 ESU. So it's quite easy to remember, right? Not at all that difficult. All right. Jishan, I'll provide the notes of this class and the previous class both, right? I'll do that. I know. I still have to do it. I'll do it after this class. All right. Both of the notes will be provided to you by end of this class. Got it? Dimensional formula. Are you comfortable with the dimensional formula of charge? It is m to the power 0, L to the power 0, T to the power 1, I to the power 1. Here I denotes the dimensions of current, right? That's what we have written it. So this is very important, that charge is not a not the fundamental quantity, it is a derived physical quantity. Everything's clear till this point. After this, why we are moving with speed, because these are some of the most basic things, but still we are not leaving it, right? After this, let's study some of the properties of charge. The first property is it is a scalar quantity. What do you mean by it is a scalar quantity? That means, let's suppose if in a question someone says that we have got a body whose initial charge is actually equals to 2 coulomb, and we have transferred a charge of minus 10 coulomb to it. So now the net charge will be written as the sum of these two charges, that is plus 2 and minus 10, that is now the total charge becomes minus 8 coulomb. That's it, right? So this is the thing that we are going to talk about, that scalar additions are very much possible over here, right? After it is conserved. What do you mean by it is conserved? When we are going to talk about that the charges are conserved, then we are going to say that, let's suppose that we have got again two bodies over here, and then these two bodies are going to be considered as our isolated system, right? Are you comfortable with the concept of isolated system? It means that we are not going to consider anything out of these two bodies, right? So this is our isolated system. Now if someone says that we have transferred some amount of charge from this body to this body, so now please understand, because again we are going to use these things in capacitance as well, right? Let's suppose that the initial charge of this body was Q1 and for this it was Q2, and finally the charges are Q1 dash and Q2 dash, right? So we are going to say that Q1 plus Q2 will be actually equals to Q1 dash plus Q2 dash, right? This is what we mean by that the charge is always conserved, right? So if a certain body is accepting some charge, there must be another body who is actually giving that charge off. Is that correct? Got it? Anyone takes notes? So you are basically trying to say that do you want to take notes from the screen? Is that what you want? I'll try to go a little slow, right? But for all of the students who are in the Yakin batch, you will get the notes, and for everyone else, I have asked the authority to actually upload these notes in the description box, right? So we'll get that done. Although these things are quite basic, that's why we are moving fast. Whenever some derivations are going to come, I'm going to obviously slow down. So you don't have to worry about, right? You don't have to worry about it. After this thing, that's what we have written. In an isolated system, total charge remains constant. The next property is quantization. What do you mean by quantization? It basically means that we were talking about these transfer of charges, right? So this transfer of charge will only be possible when, let's suppose, a q amount of charge is getting transferred. So it is only possible if the charge is in the terms of plus minus Ne. Now what does it mean? It means that if we are talking about the transfer of charge, something like this is not possible. Like for example as 5/4 electron, this is actually not possible, alright. Either 1 electron can get transferred, 2 electron can get transferred, 3 electron can get transferred, nothing such that 0.5 or 0.35, although now this is something which is not in your course, so you don't have to worry about, right, but still I'll explain it. There are some quarks, right, protons and neutrons, and these particles are also made up of quarks. Quarks have charge as plus 2 by 3 electron and minus 1 by 3 electron, right. So we call them as up quark and down quark. So you don't have to worry about it, right. These are some of the quarks. You must actually just have an idea, okay, this is something where we are not going to apply the quantization of charge, but right now we are not going inside the electron. We are talking about if an electron is getting transferred, then it will be something like if only one electron can get transferred, or 2 or 3, not 2 by 3 electron. Are you getting it? What's the difference, right? So now after this is actually very important, because whenever you are going to talk about charge, you are going to use this formula. You can use this formula, that is Ne, where E is the charge of, where E is the elementary charge, that is 1.6, I am just writing its magnitude, 1.6 into 10 to the power minus 19 coulombs, right. And if you are going to talk about electron, we are going to write it with a negative sign. That's it, right. Are you getting it? Everything's clear? Can we move on? The last property is charge is always associated with mass, right. So if a body has got some charge, definitely it will have some mass, right. It is always associated with mass. So there is nothing much to the last point. Got it? Got it? Got it? Got it? Everything's clear? Done? After this, now let's start our business. Let's come to business. Let's talk some serious topics. The first serious topic is Coulomb's law, right. And now this particular topic, when we are going to actually talk about Coulomb's law, this is very, very important. Again, because lots of numericals are going to come from this particular chapter. So now let's start this thing. You know that when we are basically talking about Coulomb's law, what does Coulomb's law says, right? Coulomb's law basically says that if we have got two charges and they are of magnitude q1 and q2, and they are at a distance of r, they are being kept at a distance of r away from it, and they are in a certain medium, right. So medium is also important. What is medium? Medium is basically, let's suppose that right now we are talking about air, or when I say air, I can also write it as vacuum, right. So air or vacuum is the medium, right. Now according to Coulomb's law said that of course they are going to actually either attract or repel, right. Let's suppose that they are actually repelling each other. They have the same charges, so they are repelling each other. So I am going to draw the forces something like this, right, and we are going to write it like this is the force on 1 due to 2, and this is the force on 2 due to 1, right. So the first thing that Coulomb said was that of course these forces, like any other forces in nature, these electrostatic force also exists in pairs, right. Are you all following it, what I am trying to say, right. So now I am going to say that according to Newton's third law, I am going to say F12 will be actually equals to negative times of F21. After this, let's say that their magnitude is F, right. Their magnitude is F. I am going to write it over here. F12 magnitude equals to F21, and let's say the magnitude is F for both of them. Direction is opposite, magnitude are same. Then Coulomb said that this force is directly proportional to the product of these two charges, that is Q1 and Q2, and divided by the square of distance between them. So this is what Coulomb said, right. And after this, what you can actually do is you can use a constant over here. That constant is 1 upon 4 pi epsilon naught and q1 q2 upon r square. This is what the magnitude is, where this value of this constant is actually for air, it is often denoted as k, and this will be 4 pi epsilon naught. This will be 9 into 10 to the power 9 Newton meter square per Coulomb square, right? This is for air. All right, everything's clear? Now see, this is not important for your board exams or for your school, right? Or even for us, because if we are talking about forces, which is a vector quantity, let me just let you all see what's written in the board. If you are going to talk about forces, force is a vector quantity, right? So let's always draw the vector diagrams. Got it? Always draw vector diagrams for things like this. So let's move to the vector diagram of this. The what we can say, Coulomb's law in vector form, because that's what is important. So for that we are going to use, as you know, we are going to use Cartesian plane, right? And I am going to say that, let's suppose now I have got two charges and one charge is kept over here, that is Q1, another charge is kept over here, that is Q2. So this is Q1, this is Q2, and the distance between them is D. Now the thing that we are going to use is, can you guess what we are going to use? We are going to say that, let's first define the position vector of these charges. So the position vector of these charges is R1. If let's suppose that you don't know what position vector is, I'll suggest that watch my videos of this basic mathematics I have done just now, right, few months ago. Then I have got you for the first part of class 11th. We have done that as well. So we have completed position vector in that also, right? So R1 is the position vector for Q1. Similarly, R2 is the position vector for Q2. R2 is the position vector for Q2, right? And if I am saying that these two charges are like charges, they both have got same polarity, then would it be fine that if I will draw the repulsive forces something like this? Just tell me in the chat box quickly if this is all good. If this is all good, is that correct, right? Is that correct? Can I draw it like this? So for this vector I am going to write something like, I am going to write that this is the force acting on particle 2 and it is being applied by 1. So this is actually F21. And similarly for this one I am going to write, this is force acting on particle 1 due to 2. Right? Now to write all of this in vector form, see what I will do. Let's first write this vector quantity. Now you tell me in the chat box, if I want to write a vector quantity, what I have to do? I have to write the magnitude of it and I have to write the direction for that vector quantity. Is that correct? We already know what magnitude of this force is going to be. You are going to say, sir, now we are comfortable with the magnitude. The magnitude is going to be, we are going to call this constant as K. It's going to be K Q1 Q2 upon whatever that distance is, square of that, right? So we are comfortable with the magnitude. How to write the direction in vector form? So please see over here. Let me write the vector, let me draw a vector something like this. Now please tell me in the chat box, the vector that I have drawn with the pink color, that pink arrow, is it along the same direction as the force F21? Is that correct? Right? Absolutely. So now I am just going to use the triangle law and I am going to write triangle law for all of you so that you can have an idea. Triangle law says, if I have got a vector like this, vector A, and this is the head of vector A and then this is vector B. So I have joined the tail of vector B with the head of vector A. Is that correct? So if I am going to draw this third side of the triangle something like this, so this will be called as the vector sum of these two vectors. That means C will be written as vector A plus vector B. Is that correct? Absolutely, right? Everybody is good with this thing. I am going to remove it because we are not going to, this is of no use for us right now, right? So now let's just use this thing over here. So I am going to say that according to this I am going to write, let's say that this is vector R. I am going to write vector R1. Just see, vector r1, and then with the head of this one I have joined this vector, and this is vector r, equals to the sum, that is vector r2. So that means vector r will be written as r2 minus r1. Is that correct? Please tell me in the chat box. Is that correct? Absolutely clear? Now, just to show that this is, just to name this thing, I am going to name this vector as r21, and the direction of this r21 vector is going to be in this one, in this direction. So this is going to be r21 vector, right? So over here as well I am going to name it. So this is going to be r21. This is the only thing that you need to remember. After this, again we are going to just write down whatever we have studied in Coulomb's law. So I am going to write for F21, I am going to write K Q1 Q2 divided by, now you are going to say, sir, what is the magnitude? So I am going to just say why we have to worry about magnitude. Just write R21 and square of it, and then write R21 and cap over it, just to show that we have actually written a vector quantity. Everybody is good with this thing, right? Now there are many other variations for this, right? Like for example, as I can write R21 cap as R21 vector divided by mod of R21. Just like you can do it for any vector quantity, dosto. Is that correct? Quickly write down in the chat box. Will the diagram come? Absolutely. Now you tell me if in your board exams they tell you that define or state Coulomb's law, so and it is of, let's say it is of 2 or 3 marks. So are they just going to expect you to just write this much? No, right? So this is how you are going to do it, the vector form. Got it, right? So this is applicable for any sorts of vector quantity. A vector quantity has its magnitude and its direction. So the direction can be, the unit vector can be written as the vector quantity divided by its magnitude. Is that correct? I will provide the notes, don't worry. Please don't get worried about this thing. Is that correct? So let's just substitute it over here. So I am going to write that F21 is equals to K Q1 Q2 upon R21 and square of this is the magnitude, times, instead of R21 cap I am going to write R21 vector divided by the mod of R21 again, right? So this will actually now become K Q1 Q2 divided by R21 and cube of it, right? Don't worry, I mean, even if I am writing a vector under over here, I have got modulus out of it. It means that we are talking about magnitude, right? Okay, it's looking like I am seeing a sunrise, lots of yellow over here. Okay, chalo. So after this, I am going to also write that is R21 vector. Everybody is comfortable with this thing, right? And after this, let me just write, I'll also use yellow. Let me just write that if you want to find out what R12 is, so R12 vector is actually something like this. R12 vector is something like this, just opposite of this one. This is what R12 vector is. Is that correct? So if you want to write F12, so you can now just please rewrite everything using R12. So this is nothing but this is negative times of R21. So we have completed the vector form of Coulomb's law. By the way, now I am expecting you to write F12, right? You do it by yourself. Got it? Everything's clear? Quickly write down in the chat box if everything's clear till here. Quick. Can we move ahead? All right, all right. Now after this, what type of questions are going to come from these? By the way, also remember that this epsilon naught is known as permittivity of free space. So if we are going to talk about any other medium, let's suppose we are not talking about air or vacuum, we are talking about any other medium, right? So they might give you another value for this. They might give you a value as they might just write it as epsilon. So if you are seeing something like this, this will be known as absolute permittivity of that medium, of a medium. I am writing it right now, it as of a medium. Are you getting it? It is known as absolute permittivity, right? So it means that the force acting between two charges depends on, of course, the magnitude of the charges. It also depends on the distance between them, and it also depends on the medium. So if you are going to change the medium, you are going to actually change the force as well. Now somebody has written that, can you define E naught, right? Because I know that at many places we don't define what epsilon naught basically means. This is just a property of a medium, which basically tells us that I mean, by what factor does it is actually decreasing the electric field. Like for example, is if permittivity is increasing, the force is actually decreasing, right? So it basically tells you that. So it is a property of a medium. It tells you that if epsilon is going to increase, the force between them is going to decrease, right? Keeping everything else as constant. Yes, its value is 8.854. This is for epsilon naught. Its value is 8.854 times 10 to the power minus 12. And what about its unit, dosto? So its unit is going to be Coulomb square per Newton per meter square. Is that correct? Got it? But for a particular medium, if you are going to talk about that, we have fixed a medium, then its value is going to be constant, right? Moving on to some new topics, and this is actually very important as far as numericals are concerned. I am going to write it for you also. So this is important for numericals, right? Now what does principle of superposition says? Principle of superposition basically says that if we have got n charges over here, let's suppose I've got a charge q kept at this point. Let's say the magnitude of this charge is capital Q, right? Magnitude of this charge is capital Q, and I've got n charges kept over here. I've got Q1 over here, I've got Q2, Q3, and similar to this I've got like n number of charges. So let me just write it as Qn, right? Now see here, this is now very, very important, right? In NEET also there are some questions which are pretty easy, but you get confused because you're getting confused with the basic definitions. Now what the basic definition says, let's see. Let's find there are two things. Let's find the force acting on this charge Q. So you are going to say, sir, the force acting on this charge Q, let's suppose that we don't have Q2, Q3, Q4 right now and Q1, we just have got Q1. So the force acting on charge Q is going to be something like this, and just so that the diagram looks a little good, I am assuming that all of these charges are of same polarity, like charges, right? So the Q1 is going to repel it over here. So the force will be something like this. So this will be force applied by Q1 charge. So I am just writing as 1, right? Now my question is, quickly answer it, right? My question is, now if I have another charge q2 over here, so will F1 will change or not? Or if it will change, whether it will increase or decrease? You got my question? Quickly write down the answer in the chat box. If, see, till now I didn't, I mean I just had got q1. Now I have got q2 as well. Now I have got q2 as well. And still just q2, no q3, no q4, nothing. What I am trying to say is that, tell me what will happen with this F1. Will it increase or will it decrease? Or will it remain same? Quickly. Quick. Will it increase? Will it decrease? Or what will happen? First, we only had Q1, then Q2 came in. What will happen with F1? What will happen with F1? So, I mean, till now I've got like 10 answers and all of you are saying decrease. So actually you proved me correct that I just said that you are going to get confused with some of the most basic things, and you are getting confused. See, yes, very good, Shai, very good. At least one answer is correct. I am not talking about the net force on Q. I have just said after Q2 comes into the picture, what happens with F1? Now, the first thing that you will have to say is that what is F1? F1 is the force between capital Q and small q1. So, on what factors F1 depends? So, F1 depends on capital Q magnitude, small q1 magnitude, the distance between them, and the medium in which they have been kept. So, now you tell me, have we changed anything out of these which I have just said? Have we changed anything? No, right? We haven't changed the magnitude of this charge or this charge, the distance between them, or the medium in which they have been kept, right? We have not changed it. So, F1 will not change. The most basic point is the force between two charges is an affair of those two charges. It's a business of those two charges. When a third charge is going to come, don't apply common sense over here that, oh, third charge has come, something must get changed, right? Got it? Are you getting it? It will not happen like that. Okay, the second charge has come, so now we are going to say, all right, so what's going to change? I will tell you, the net force on the capital Q charge will change. The net charge on capital Q charge will definitely change. I have said that now F2 is also acting. The net force will change, but F1 will not change. Now Q3 has come. So will it change F2 or F1? No. So what it will do? It will just apply another force. Q3 will just apply another force. By the way, capital Q is also applying the forces on these charges. The same, with the same magnitude, capital Q is also applying the forces, but we are not concerned with that right now. Why? Because right now what we want to find it out is, what is the net force acting on this charge, right? Got it? Done? So, let's say, and by the way, dosto, that this is, let's suppose that this is actually R1, this is actually R1, this is R2, this is R3, and for the last one, we can have like n number of charges like this. So, this is actually Rn, right? So, let me draw for the nth. So, this one was for the third particle, and for the nth one I have got something like this. So, this is force applied by the nth particle, this is force applied by the third particle, right? So, the net force acting on the charged particle is going to be the vector sum of all such particles. Now please understand I am talking about the vector sum. Everything's good? Right? Now let's solve some numericals on this, right? Let's solve some numericals on this, and if I am not wrong, we are going to also talk about some equilibrium of charged particles for this, and if we are going to find the equilibrium of the charged particle system using this concept only, right? So let's suppose we are talking about some structures like this. Let's start with the very basic. Let's say we have got an equilateral triangle. That means all of the sides are of same length, and the charges right now, let me just write it as Q, right? I just want to let you know that how to do problems like this. And let's say this charge is also Q, or this charge is capital Q. It can be anything, right? It can be anything. Got it? Got it? Got it? Done? See, obviously I have assumed these to be like charges, so this is going to repel this one over here, this charge is going to repel this charge in something like this, right? Let's say this is A point, this is B, this is C, so this is force applied by charge which is kept at B, this is force applied by charge which is kept at A. So the net force acting on the on charge capital Q is going to be just the vector sum of these two. And what is this angle? This angle is 60 degree, right? Now it depends on you whether you want to draw the component over here, or you want to draw you want to use the resultant formula, right? I would suggest that if you have got a problem like this, quickly use the resultant formula, because that's I mean quite fast, right? So we are going to say that R will be written as the square root of A square, that I am just talking about the vectors, by the way. So or what I will use is I will just use F1 square plus F2 square plus 2 F1 F2 cos theta and root of it, right? So just use it over here as well. So now please remember these things. Don't solve these things for the first time in your board exam or in your NEET exams, right? Are you getting it? I can take negative and positive also. There is nothing to worry about. If you are going to if you are saying it like that, then let's take for any example. It is dependent on any example. Let's suppose that this is positive. Let's suppose that this is negative, and let's suppose that this is also positive. Happy? Right? So it's nothing. So if it is negative, the force will be drawn something like this. If it is positive, the force will be drawn something like this, right? And by the way, these vectors needs to be drawn of equal length, at least by me, right? So now the angle between these two is going to be 120. So nothing really changes, right? And whenever we have got something like this, if we have got like equal forces, it will be along the angle bisector. So if you are going to talk about the net force over here, the net force over here will be, see, I'll just do it like this, F square plus F square. Now what is F over here? So F is going to be K Q into Q divided by A square. So this is what F is. So first write down what F is, right? Now net force is going to be F square plus 2 F into F, again F square, times cos 60. Is that correct? Is that correct? So we are going to write it like F square plus F square plus 2 F square into cos 60, that is 1 by 2, right? So this is going to be just, this will be 3 F square, so this will be F root 2, F root 3, and we have found out what F is. So finally write the answer something like this. And if you want to find out for this one, cos 120 is minus 1 by 2. Cos 120 is minus 1 by 2. Please remember all of these things. So for this one, what will happen? F square minus 2 F square into 1 by 2. So it will be what? It will be F square plus F square minus F square, right? So finally the answer will come as F only. Is that correct? Everything's fine till here? Quickly write down in the chat box if everything's good. Moving on. Now using this principle of superposition, you can also find out something that is called as equilibrium point or neutral point, right? Something that is called as equilibrium point. So this is important for board as well as for competitive exams. So for board, I am going to explain the entire method, and for competitive exam, I am going to give you a little trick, a shortcut formula, a shortcut method, right? Let's quickly do it. So the main concept about this is, let's suppose that we have got two charges kept over here, and now again I am going to use all the cases, positive, negative, like, unlike, both the cases. Let's suppose I have got Q1 over here and I have got minus Q2 over here, right? Quickly let me explain it to you. Done? Done. So after this, I am going to say, let's suppose, first of all, what do you mean by equilibrium point? So equilibrium point basically means a point where net force will be 0, This is something that is called as equilibrium point. Now what do you mean by net force equals to 0? What we mean to say is that, let's suppose I am putting a charge over here. Let's say I am putting a charge Q0 over here, and I am saying, is it possible that on this charge Q0 the net force can become 0? So you are going to say, sir, yes, it is possible if the vector sum is 0. Vector sum of two forces, right now we have got like these two charges, and the vector sum of these two forces, the forces applied by Q1 and minus Q2, if they are 0, then it will be, then the net force on this charge will be 0. Is that correct? So let's find it out. For this, first let's say that this is a positive charge, right? So if this is a positive charge, then we are going to say that this charge will actually attract it, something like this, and this will actually repel it, something like this. So now you can see it that if we have got a charge in between of these two, then these two forces are getting added up. So this is F1 and this is, let's say this is F2. These are getting added up. So they can never cancel out each other, right? They can never cancel out each other, and for this reason we are going to say, when we have got like unlike charges, the equilibrium point will never be at the middle of these two charges. Are you getting it, what I am trying to say, right? So we cannot find the equilibrium point at the middle. So what we are going to do now? Now we are going to say, let's suppose that the magnitude of Q2 is less than the magnitude of Q1. This is the another important point. We are saying, let's say. So if magnitude of Q2 is less than magnitude of Q1, then already this charge is actually lesser in magnitude. Think about it like this. This charge is lesser in magnitude, right? And if you will actually keep the neutral point close to it, then actually that particular point can be in equilibrium. Does it make sense? So now I am going to say that, let's suppose the equilibrium point is somewhere over here. Now think it like this. This is Q0. This is Q1. So Q1 will actually repel Q0, something like this. So this is the force applied by, Q1, and Q2 is, because it is negative and this is actually positive, it will actually attract this thing. So the force applied by Q2 will be something like this, right? And now there is a possibility that they can cancel out each other, right? So now what I am going to say is, let's suppose the distance between these two charges was x. The distance between these two charges was, let's say it is r, and the distance between these two charges is x. So I am going to say now, for them to be at equilibrium, that is net force is equals to 0, it means that F1 is equals to negative times of F2. This is what we mean. And after this, I am going to write for F1, I am going to write K Q1 times Q0 divided by distance, that is R plus X, and square of this equals to, now I am just talking about magnitude, right? I am not going to use directions and all. I am not going to use negative sign over here. Are you comfortable with this? Why I have written negative? It means that these two forces must be equal in magnitude and they must act in opposite direction. Got it? So after this, I am going to write the force, that is F2. So I am going to write K Q2, just writing the magnitude, times Q0 divided by X square. So this is the relation, and after this you can find out what the value of X is going to be. Quickly write down in the chat box if this makes sense. Quick. And if they are, I mean right now I have talked about this one, this case was part of unlike charges. Unlike charges, right? Got it. And if you are going to talk about like charges, then for like charges it will be at the somewhere in the between of those two charges, right? Also please remember that neutral point or the equilibrium point is always close to the charge with smaller magnitude. All right. So for like charges, hopefully I think you can do for the like charges, right? Moving on, the trick that I wanted all of you to know is something like this. This is the trick. The trick is, let's suppose that we were talking about unlike charges. We have already dealt with unlike charges. So for unlike charges, this is x1, right? So if you want to find out x1, this is actually q1. So this is actually the smaller charge. This one is actually the smaller charge. All right, and for this one again, this one is going to be the smaller charge because the neutral point is in between of that, and the shortcut formula is going to be this. That is the total distance between them, the separation between them, under root q2 by q1, where q2 is the magnitude of the bigger charge, divided by q1 plus 1. This is for like charges. Please understand, when we are talking about two like charges, q1 and q2, and if you are going to talk about unlike charges, then you are going to use this as the formula. All right, quick. Now let me explain another example for this, and those two examples can be something like this. That let's suppose if we want to find out the equilibrium of the symmetric geometrical point charge system, which are something like this, right? We have got like small q charges over here and we have got a capital Q charge over here, and what we want to know is we want to find out the magnitude of capital Q so that this system is in equilibrium. Take a minute, just think about this thing. We are talking about equilibrium of the whole charged system. Now before moving on, let me first explain what do we mean by this. If we are really saying that the system is in equilibrium, whatever thing is in the equilibrium, it means that the net force acting on that particle or the system is going to be 0. This is what do we mean by equilibrium. Also we are going to talk about torque as well, but right now we don't have to talk about torque, right? So if a system is in equilibrium, let me break it down for you. If a system is in equilibrium, everything is in that system, every charge particle in that system will have no net force. Net force will be 0 on those, on everything that is inside that system. It means that if this is the system, quick, let's say if this is the system, and I think we had got Q over here, we have got Q over here, and we have got Q over here, and at the center we have got capital Q, right? And by the way, this is again an equilateral triangle, and they are saying that this system is in equilibrium. It means that net force on this is 0, net force on this is 0, net force on this charge is 0, net force on this charge is 0. If they would have said, Q is in equilibrium, then we will say that only the net force acting on capital Q will be 0. We can't assume for everyone. If they will say for system, we are going to say that the net force on each and everything that is inside the system is going to be 0. Got it? Now my question is, or what we were actually trying to find, that let's find the value of this capital Q. Let's find the value of this capital Q. What should be the value of capital Q in terms of small q, so that this system is in equilibrium? Alright, let's quickly do it, then we will move on. Now to solve this problem, the first thing that you can actually do is, you will say that, okay sir, fine, the force by this Q will be something like this. Okay, just a second. The force applied by this charge will be something like this. Force applied by this charge will be something like this, and force applied by this charge will be something like this, right? And they are going to cancel out each other. These forces are going to cancel out each other, but how you are going to find out the value of capital Q from this? You can't get the value of capital Q. So what I'll suggest you to do it, let's do the same thing for this charge. I've got a charge Q over here as well. This charge will actually repel it something like this along the line. This charge will actually repel it something like this along the line. And again this charge will repel it something like this along the line, right? Sorry, it will not repel, because for repelling it then the net force will not be 0. So this is actually force. I will also name them. So this is, let's say this is A, this is B, and this is C. Please understand. And I have got a Q charge over here as well. So this is force F B, this is force F A, and this angle is also 60 degree, and you know what the resultant of these two forces are going to be. You can now quickly tell me this, sir. Now it's very easy. Let's suppose that this is F, so this is also going to be F. So that means the resultant force is going to be something like this, the resultant of these two, and the resultant is just going to be F root 3. We have just calculated it. So that's how you increase your speed. If you have already done all of these things in the practice, then you know that, okay, this is how it's going to be done. It means that if the system needs to be in equilibrium, if the system has to be in equilibrium, the net force on this charge should be 0. And till now, the net force on this charge is F root 3, and I have got this Q. It means that now I am going to say something like that the force due to this charge Q will be also F root 3 in the opposite direction, so that it can cancel out this one, right? That's how you are going to do it. So let's just find it out. So force applied by Q on C, on charge particle kept at C, right? So that should be actually Q divided by, dosto, what is this distance? Can anyone tell me what this distance is going to be? This distance, right? This is perpendicular. So I'll just find it over here. And again you just need to find it once. In exam you'll just write it as it is. This distance is a by 2. This distance is a by 2. This is 30 degree, right? So this is your hypotenuse that we are talking about, right? So let's say this distance is x. So this distance is also going to be x. So cos 30 will be actually equals to base times hypotenuse. So x will be actually equals to a by 2 times root 3 by 2. So this is nothing but this is a by root 3. So I am going to write a by root 3 square of that. So this will become a square, and that's root 3 will go up. Okay, I am not talking about this distance or this distance, I am talking about this distance, right, equals to, now this should be actually equals to f root 3. Can you tell me what f is? So f is actually going to be equals to k q square divided by a square and root 3. Now let's cancel out everything that we know we can cancel. These things will be cancelled, and as far as capital Q is concerned, it will be q root 3 divided by 3. That means it is q by root 3, but this is not the correct answer. Why? Because if this force, this charge applies a force something like this, and this is a positive charge that we are assuming, that means this needs to be a negative charge. So after writing the answer, we are going to write the negative sign. Till now we were only concerned with the magnitude. Now I think we can move on. We have pretty much talked about all of these things, that what are principle of superposition, we have talked about Coulomb's law. Quickly tell me in the chat box if everything's clear, then we'll move on. Quick. And by the way, the next thing is about a square, which is your homework. Now some are asking why a negative sign. You tell me. We have assumed that, and see, this is not about negative or positive sign. When we have this something like this, they in the question they have not told us that what is the charge of small q, right? Let's assume that it is positive charge. Let's assume it. Then I'll assume the another case as well. Let's assume that this is a positive charge, right? So if these are positive, obviously they are going to repel each other. The resultant is going to be something like this. And now if you are going to say that I also want to have the same charge of this q, then this will also apply the same type of repulsive force. So how will the net force on this charge will come out to be 0? It will not be possible, right? That's why whatever the polarity of this q is, capital Q should be opposite of that. That's what I'm saying. I'm not saying it should be positive or negative. That's all what I'm saying, right? Got it? Everything's clear. After this is your homework. Do this one in homework, right? So this is also quite easy. Again, let's just consider one of the particle over here. Don't draw the Coulomb's forces on this charge. You need to find out this magnitude, the magnitude of this charge. Got it? Everything's clear? All right, let's move on to the next topic. Now we are going to talk about electric field. If we are talking about electrostatics force, if we are talking about Coulomb's force, and obviously it is a non-contact force, so it means that there must be some sort of field that would exist around a charge, right? A region. The simplest definition is a region around a charge about which another charges can experience electrostatics force, right? So electric field is the space surrounding an electric charge in which another charge experiences an electrostatics force of attraction or repulsion. Is that clear, dosto? So when we are going to talk about actually electric field, again we are going to discuss two things. We are going to talk about basically one is electric field, and the another thing related with it is that electric field intensity. Electric field intensity. So electric field is just like it's like an area. It's like a space around a charged particle, right? Now how much that force of attraction is going to be, that we actually want to find out the intensity of that force. So we are going to use electric field intensity, and inside this again we are going to talk about the direction of electric field, so very important, and we are going to talk about the magnitude of electric field. Alright, everything's clear, right? So we are going to talk about these two things. Well, first let's start with the electric field intensity. Electric field intensity is nothing but it is the amount of force experienced by a unit positive charge at a particular point, right? I'll explain it. What do we mean by this? Let's suppose that we want to find out the electric field. We want to find out the electric field of this charge at a certain point, somewhere over here, right? At this point P. So now what I'll tell you is, let's suppose that we have got a unit positive charge that we also called as test charge. So this is a unit positive charge plus 1 coulomb. Why it is called as test charge? Because the only purpose for this charge is to find out the electric field intensity of this charge. We have got to do nothing with this test charge, right? So and let's say that the distance between these two charges is r. So the force acting at this point is going to be something like this. Okay, just a second. All right, just a second. Let me get someone. So you have, I think you have got a 2 minutes of break. So you can, by that time you can actually talk with me. I'll just fix it. All right, so how many of you are still here? Quick, quick, quick. Hmm. Friends, just give us 2 more minutes. Yeah. I'll be back. Thank you. Just take 5 minutes of break. I'll be back, right? I'll just take 5 more minutes to fix this up. Then we'll start electric fields, right? Yes. Thank you, Rihanna. Thank you. All right. Just 5 minutes. 5 minutes break. Hi everyone, hi. Sorry for the delay because a slight tech issue. Alright, now I am back. Let's start where we were. We were talking about electric field intensity, right? Let's start. We are talking about electric field intensity, and when we are saying that we have to find the intensity of electric field of, let's say, a charge capital Q, which is at a point P at a distance of r, right? Got it? Now what we are going to do is we are going to assume that we have got a test charge kept over here, a unit positive charge. I have already told you why we have taken it as a unit positive charge, right? And the force experienced by this is, let's say, it is F. So the electric field intensity will be written as, it is the force experienced by a unit positive charge or force per unit charge. That's how we are going to define electric field intensity. So force is a vector quantity, so electric field intensity is going to be a vector quantity, and the direction of electric field will be in the direction of force, right, along the direction of force. So at this particular point the electric field will be in this direction. Electric field will be in this direction. Got it? Everything's clear till here, right? Quickly tell me in the chat box, right? Other than this, what are going to be the important points regarding this? The electric field intensity at a point is the force experienced by a unit positive charge placed at that point. It is a vector quantity, and like we have said, it is actually force experienced by a unit positive charge. It means that its unit is going to be Newton per Coulomb. So SI unit is going to be Newton per Coulomb, and dimensional formula is going to be m1 L1 T to the power minus 3 I to the power minus 1. Alright, got it? Everything's clear? Done? Now, like we have talked about the equilibrium point for a force, there will be an equilibrium point for electric field as well. Got it? We are going to talk about that. We can talk about the same thing as well, and the concepts are pretty much same. So I am not going to repeat it again. Other than that, we have got something that is called as electric dipole, and we have got some very important derivations regarding electric dipole. So now this part is very important for your boards. When we are talking about electric dipole, first of all, let's understand what do we really mean by it. An electric dipole is actually a system of two charges. Let's suppose I have got a charge over here, it is written as plus Q, and I have got another charge at a small distance. So the first thing is that this distance is actually small. Let's say it is kept at a distance of d, right? There is just medium in between of those. So we have got two charges equal in magnitude, opposite in polarity, kept apart by a small distance. So they are kept apart by a very small distance. This system is actually known as electric dipole, right? So there is no formula of electric dipole. There is a formula for electric dipole moment, right? What is electric dipole moment? So we have come up with a formula which was not really which was not something that was derived from any other thing. We have just said that electric dipole moment, which will be denoted by vector P, will be written as the product of the magnitude of any charge. So magnitude is same, so let's write it as Q times D, that is the distance between these two, and times basically the unit vector. So this is the dipole moment. Now what about the unit vector? What is this P cap? So P cap is basically the direction of dipole moment, and it is actually it is from negative to positive, something like this. So this is P cap. Alright, this is P cap. Everything's clear till here? After this, we are going to actually, and also I have got notes for you, a system of two equal and opposite charges separated by a small distance is called electric dipole. Dipole moment, it is defined as the product of magnitude of either charge and the separation between the charges. Dipole moment is a vector quantity, and conventionally, what do you mean by conventionally? Conventionally basically means that we have not really, there is not very some logic behind why the direction is taken from negative to positive only. It has been taken conventionally. Direction is given from negative pole to positive pole, or from negative charge to positive charge. Everything's clear till here? Now we are going to actually talk about electric field due to electric dipole, and the first case over here is that is at a point on the axis of the dipole. Right. So now this is the derivation that I was talking about. So for us, derivation is important. For anyone who's preparing for a competitive exam, for them this derivation is not that important. The final result is very important, right? So again, let's start with the same thing. Let's say that we have got two charges over here, and those two charges are something like this. Let's say I've got plus q over here, or minus q over here, and plus q over here, right? And if they are talking about at an axis, what do we mean by that? That let's suppose at certain distance, or at this point, we want to find out the net electric field at this particular point. That's what they are talking about. Got it? And we know that they have been kept at a small distance, right? Well, according to the diagram, it doesn't look like this. I'll change this diagram up by a bit. And I also tell you why I am doing that. The reason is that this is the distance between those two charges must be actually, we must also explain that they are very small, right? So here we have got, let's say we have got minus q, and at this particular point, let's say we have got plus q, and at a certain point somewhere over here, we have got our charge. We have got a point at which we want to find out the net electric field, right? Let's suppose, after this, now this is very important, let's suppose the total distance between these two charges is 2a. Why we are taking it as 2a? Let's understand this thing. We are assuming it as 2a because we are going to say that from the midpoint of these two charges, let's say the distance of this point is x. The distance of this point is x, right? If we are going to say something like this, we know that the distance over here is a, the distance over here is a. So the distance from this minus q to that point will be x plus a, and the distance between this plus q and this point is going to be x minus a. This is the reason that we have taken it as 2a and not d, right? Everything's clear till here? After this, at this particular point, if you want to find out the direction and magnitude of electric field, just assume a point charge over there. So let's just assume we have got a point charge, it is a positive charge. So electric field due to this charge is going to be in this direction, right? Electric field due to a positive charge is outwards, so it will be in this direction. So I am going to write it something like this. So this is electric field due to plus q, right? And this is the negative charge. So if we are going to assume that here we have got a unit positive charge, so this negative charge will attract that unit positive charge. So electric field because of this minus q will be something like this. This is electric field due to minus q charge. Is that all right? And before going forward, let me also explain that if we have already talked about that electric field formula was E equals to force divided by q naught, and force is actually K, I am just talking about the magnitude, K q naught divided by r square times q naught. So q naught can be cancelled out and the formula comes out to be kq by r square, and let's also write the direction over here as E cap. Is that basically what I am trying to say is the formula of electric field due to a point charge is kq by square of distance. Is that correct? Okay, so let's apply this formula over here. So the net electric field at that point will be, according to vector rule, will be the vector sum of electric field due to plus charge plus electric field due to minus charge. Now this is the point where most of students who are learning it for the first time, they get confused. Right now I have written the vector sum. Why? Because electric field is a vector quantity. I really can't just add them like 2 plus 3. I can't write 2 plus 3 equals to 5 because electric field is a vector quantity. So what I'll have to do is I'll have to actually add them vectorally. Now understand one thing. If I'll write the individual electric fields over here, I'll write it something like this. Electric field due to plus q charge is going to be k q upon square of distance. Now, so what is the distance between plus q and this particular point? It is x minus a. So I'll write x minus a and square of that. And if I'll write electric field due to minus q, so I'm going to write k q. I'm just writing magnitude, so I don't have to write minus q, right? I'll write k q divided by square of distance. What is the distance from minus q? It is x plus a. So I'll write x plus a ka square. Is that all good? Is that all good? Now tell me what is the direction between these two vector quantities. The direction between these two vector quantities is 180 degree, right? So even if I'll apply that under root formula, the resultant, the net magnitude, I can write it something like this. See, now this is the difference. Now I'll write the net electric field will be out of these two, which is actually greater in magnitude. Just think about it. Out of these two, which is greater in magnitude, obviously electric field due to plus q. Why? Because plus q is closer to this point, minus q is farther away, right? So electric field due to plus q will be greater in magnitude. So I'm going to write that magnitude of electric field due to plus q minus electric field due to minus q. Can you really differentiate between these two steps? Are you really comfortable? Right? When I was writing something like this, I was really focusing on the vector sum. When I am writing something like this, I am just talking about the vector, I am just talking about the magnitude. Now quickly let me find it out. So this is going to be k q divided by x minus a whole square minus k q upon x plus a whole square. Solving this one out, I'll take it out kq common, and I'll write x square plus a square plus 2ax. What I'm trying to do, I have taken out kq common, then I have 1 upon x minus a whole square, 1 upon x plus a whole square. I'm just expanding it, right? Minus, I'm just afraid, let me just write it this thing over here. Yeah. After this, we'll write everything with a minus sign. If you are not comfortable with this step, I would suggest that please do it by yourself. You will get it. It's quite easy, right? And for the denominator, I'll just use the property of a square minus b square. So x square can be cancelled out, a square can be cancelled out, and finally we'll be left with kq 4ax divided by x square minus a square and square of that, right? Got it? Please see the formula. If we have got everything over here done, right? Hopefully everything's clear. After this, we have got our formula as E equals to the net the net electric field at that particular point, we have got something like this. We have KQ times 4A, KQ times 4AX divided by x square minus a square and square of that. But this is just the magnitude. Hopefully you are all with me on this. This is just the magnitude. Alright, let's write the vector form of it. Also we know one more thing, that dipole moment can be written as charge times distance. So right now the magnitude is q, but the distance is actually 2a, is it? Isn't it? Right? So let me just apply it over here as well. So I'll write the electric field in vector form as E net equals to, I'll just break this 4 into 2 into 2, right? So I'll write something as 2k x, and for this 2a and q, I'll just write it as p. Hopefully you are getting it. For 2a and q, 2a and q I have just written as p, and I've got x, I've got just 1, 2, and I've got k, right? Divided by x square minus a square and square of this. Now please understand, this is a vector formula, this is a vector quantity, so I'll write a vector sign over here. But you will say, sir, how to write vector, how to write direction for it? Can you please tell me the net electric field direction in this diagram? The direction of net electric field will be in this direction. This is going to be the direction in which the net electric field is acting. The net electric field. I'll again explain it. Why? Because electric field due to plus q is greater in magnitude, that's why, right? Alright, one more time. What is the direction of dipole moment? So you are going to say, sir, direction of dipole moment, which was assumed conventionally, was from negative charge to positive charge. This was the direction of dipole moment, is it? Right? So it means that direction of net electric field is along the direction of dipole moment. That's it. We'll just write one more thing over here. So this was the magnitude of electric field, and if I have written a vector quantity over here, I'll just write it as p cap. See, I have done nothing wrong, right? And it makes complete sense that now what we have done is that net electric field was acting in this direction, dipole moment was acting in this direction, so I can use the dipole moment's direction, right? I mean, this is just a unit vector. I have not changed anything in this one. After this, there is just one more thing, then we'll quickly move on. We are going to talk about a short dipole. So this is the case. We are going to talk about a short dipole, and this is the special case, right? Which is actually which is used more frequently. So short dipole basically means that we are talking about something like if x is far more greater than a. That's why I actually changed the diagram from the initial case. Do you remember I shortened the dipole by a margin, right? So what does short dipole basically mean? Short dipole basically means that x is very large. This x is very large than a. So in that case, if x is far more greater than a, it means that x square will be even greater than a square, such that I can actually, this will imply that I can just assume that a square is 0 in front of x square, right? Or what I want to say is, I can say that from this I'll imply that x square minus a square can be written as just x square. Would that be correct? Right? It's not a wrong assumption. So after this I am going to say that, okay, so that means net electric field for a short dipole, and that too net electric field, net axial electric field for a short dipole will be 2kxp times p cap. I'll remove these things from here, divided by x raised to the power 4. So this is x cube. So finally the answer will come out to be E net in vector form will be 2kp divided by x cube dot p cap. This is the formula that we wanted to derive, and this is the part of your school syllabus and considered as important for your for the part of derivations, right? Is that all good? Can we move on without wasting any more time? Yes, there is one more thing, that electric field actually depends on the cube of the distance, but we have not changed any unit. For over here we have got one dipole moment, so still the unit for electric field is going to remain the same, obviously, right? Moving on, after this we have got something like at a point on the equatorial line. Is that correct? Let's do the derivation for this as well. So for an equatorial line, we are going to again say, let's suppose that I have got the dipole something like this. Again, this is a short dipole, but now just to make the diagram a more clear diagram, I'm exaggerating the distances, right? So again, this is, let's say this is minus q, this is plus q, right? This is plus q, and equatorial line basically means a perpendicular bisector something like this. So if I want to find out the distance, if I want to find out the electric field at this point, what I would want to know is the distance between these 2 points and the distance between these 2 points, which I can easily find it out, right? Why? Because I know that, okay, this distance is actually a, this distance is a, and they are saying that we have to find out the electric field at a distance of x on an equatorial line, right? Is that correct? All right, everything's fine. What's the another step, sir? So the another step would be that this is going to be, obviously this is going to be x square plus a square and root of that. Similarly, this thing is going to be also same. Next step is going to be, assume that we have got a test charge at that particular point. We have got a test charge at that particular point, right? So if I've got a test charge, I'm going to say, let me just make some horizontal and vertical axis so that I can correctly draw it. If I have got a test charge, then because of this, the electric field will be something like this along the line. So this is electric field. This is electric field due to plus q charge, right? This is electric field due to plus q charge. Moving on, electric field due to minus q charge will be something like this. This will be electric field due to minus q charge. And because we don't know what these angles are, so let's just assume them to be theta, but the thing is that if this is theta, then this is also going to be theta. So in that case, this is also going to be theta, and this angle is also going to be theta. After this, let's move a little fast because it's all now simple things. If this is E minus Q, then we have got a vertical component of this over here, and I'll write it as something like E minus Q sine theta. Similarly, I'll write another component of this along this axis, right? And that will be E minus Q cos theta. Again, for this one, there will be one component over here and the another component will be over here. So this is going to be electric field due to plus Q charge into sine theta. And then again we have got plus electric field due to plus Q charge into cos theta. Please quickly write down in the chat box if everything's clear till here, right? Now one more thing, what is electric field due to plus Q charge? So electric field due to plus Q charge, I'm just talking about the magnitude. It is K Q divided by the square of distance, that is x square plus a square. That's it. And the magnitude will be equals to the electric field due to minus Q charge as well, isn't it? Because there is no difference. Well, I have got same charges, the point is at the same distance. So the magnitude of electric field will remain same, right? It means that I can pretty much cancel out these two electric fields, these two vector quantities. Quickly write down in the chat box if everything's clear till here. Why we are able to cancel out? What's the reason? This is the reason. Now the net electric field's magnitude, I'm going to write it something like this. The net electric field will be again, I'm just writing the magnitude, we'll figure out how to write direction later. It will be 2E cos theta. Why 2E cos theta? Again, this was E plus Q, E minus Q. Their both magnitudes are same. So let's just add them, right? Let's just add them. So it will be 2E cos theta. So I'll write 2 instead of E, I'll write K Q divided by square of the distance. So x square plus a square times cos theta. Dosto, cos theta is base A upon hypotenuse, that is x square plus a square and root of that. So that means the net electric field magnitude will be 2K QA, and I'll again over here I'll use something where I'll club this 2, I'll club this Q, I'll club this A, and I'll write them as P. So Kp divided by x square plus a square whole raised to the power 3 by 2. So this is the net electric field's magnitude. Now let's talk about its direction as well. So when you are going to talk about the direction, tell me what's the direction. Direction of, again we'll use dipole moment. Direction of dipole moment is in this direction. This is the direction of dipole moment. This is P cap, and direction of net electric field is in this direction. This is the direction of net electric field. So let's write the direction. So last step is going to be E net. E net equals to, in vector form, it will be minus, first I'll write the magnitude, it will be K P upon x square plus a square whole raised to the power 3 by 2 times P cap, and to show that it is in the opposite direction we'll write with a negative sign. Now tell me in the chat box if everything's clear. Quick. Clear till here? After this, again the special case, that is for short dipole. For a short dipole, we are going to say that again x will be far more greater than a. So we can write electric field, the net electric field, as in the vector form. This will be only, a square can be neglected, this will be x cube. So it will be Kp by x cube and negative sign over here and P cap. Something like this. Quick. So we have completed the two derivations. Let's move from here. Quick. Alright, everything's clear? After this, we are going to talk about torque on a dipole in a uniform electric field, right? But before that, please understand that these things are going to again, repeat when we are going to talk about magnetism. These are quite similar. So it's better that we actually at some angle, somebody has asked that at some angle also let's do it. I'll do at some angle, but we'll do it for potential, because usually for electric field either it is something like on axial point or an equatorial point. For potential, generally they ask for a general point. So we are going to do that, don't worry. But hear me out carefully. The reason that we are properly learning each and everything in electric charges and fields is that everything will be repeated in magnetism. So in magnetism we'll actually move quite fast, right? Sir, can we clear GW? Absolutely, you can do it. Absolutely, no doubt about it. Alright, let's move ahead now. If you have any doubt, please, you can ask your doubt in the chat box. How many of you are still here? Quickly write down in the chat box if everything's clear. Quick. Then we'll start with torque acting on a dipole in uniform electric field. All right, Kirti, all right. So everything's clear till here, right? Fantastic, great. So now we are going to say that we have got uniform electric field. What do you mean by uniform electric field? Electric field has got two things. When I say electric field, I mean electric field intensity. All right, Rehana, all right, Dhairya, Mishti, good. All right. Little boy, I don't know what your name is. Write down your name. All right, Smruti, great. Guys, you can ask your doubts, right? If you have any doubt, you can ask it on the chat box. When we say that uniform electric field, it means that the direction at every point must be same, as well as magnitude should also be same, right? So we must draw the electric field lines something like this. So electric field lines must be drawn somewhat like this. That means even if I was unable to draw it, what I meant is that the separation between these lines must be same, and they must be parallel. So parallel equidistant electric field lines represents uniform electric field, right? All right. So if we have got some lines which are not equidistant but parallel, still they are not going to be considered as uniform. We have got some lines which are not parallel, we are going to say that is a non-uniform electric field lines, right? So for uniform electric field lines, the distance between those lines must be equidistant and they must be parallel, right? And then after it, they are saying that we have got a dipole kept on this electric field lines, something like this. And let's say this is plus Q and this is minus Q. So if this is electric field lines, on plus Q charge, electric field will apply force, and the force will be in this direction. Hopefully you can understand it. The force will be along this direction. Tell me if you have any doubt. And if you want to find out what would be the direction of that, what would be the magnitude of that force, so that force will be QE. Why is that? Because electric field is written as force per unit charge. So force can be written as charge times electric field. And why only in this direction? So I will give you a little trick to remember it. Whenever you see a electric field something like this, always remember that from a positive charge electric field lines originate, and on a negative charge they terminate. Although we have not talked about it, we are going to refer to some electric field lines property soon, but you can just assume it that here are certain positive charges, here are certain negative charges. This is just an assumption, right? After this, so that means that on this particular charge force will be applied in this direction, on this particular charge force will be applied in this direction, and again the magnitude will be same, the magnitude will be QE. So now I can write from all of these things, I can write the net force on the dipole. The net force on the dipole is 0. Is that correct? Because here Q is acting in this direction, Q is acting in this direction. So the net force is 0. If net force is 0, then we can say that there will be no translational motion, or there will be no change in translational motion. That would be more suitable. The next thing is, these forces are not acting in one line. They are not collinear forces, right? So they are going to create a moment, right? They are going to create a torque. They will try to rotate it, and let's suppose this angle is theta and this distance is actually d. So I am going to say that if this distance is d, then this distance is going to be d sine theta, right? So the torque, the net torque will be, which is written as r cross f or rf sine theta. So it will be written as QE times d sine theta. By the way, Q times d is nothing but dipole moment. So it will be PE, I am writing Q and D, right? PE sine theta. So if you want to write down the vector form of this torque, we can write torque can be written as P cross E. It means that the electric field is trying to rotate the dipole along the direction of itself. That's what the electric field is trying to do, right? Everything's clear with this one. Torque acting on a dipole in a uniform electric field, we'll see some of the questions regarding this, right? After this, we have got something like continuous charge distribution, but it's not that important. We'll talk about it when we'll reach Gauss law. As of now, let's quickly go through the properties of electric field lines, because this is actually important. What do you mean by an electric field line? It is an imaginary line drawn in such a way that its direction at any point is the same as the direction of the field at that point. Now what do we mean by this? Let's understand. Let's suppose we have got a charge over here, and this is a positive charge. This charge, or I'll draw it somewhere over here, this charge is known as an isolated positive charge. Why? Because it is actually, it is not with some another charge, it is not in some system or anything like that. It is an alone charge, right? So I am going to say that it is an isolated charge. Now the direction of electric field due to a positive charge is something like this. Right? Everything's clear? Why is that? How we'll know that? Just put a unit positive charge at any point, and you will see that at that particular point the force is acting in this direction, right? That's how. And similarly for a negative isolated charge, so that means for a positive charge the direction of electric field is outwards to the charge in all directions, right? For a negative charge the direction of electric field is inward. You can now understand it. So if I have got a negative charge over here, the direction of electric field would be something like this. And so on. Right? And if I have got a dipole, so these were two isolated charges, right? These were isolated charges. If I have got a dipole, and dipole is kept something like this, so I have got a positive charge over here plus q, and I have got a negative charge over here, that is minus q, right? So the electric field due to this will be drawn something like this. Let's suppose that I have got a unit positive charge over here. So electric field due to positive charge is something like this, and electric field due to a negative charge is also towards the negative charge, so it will be drawn something like this. Other than the midpoint, the direction of electric field lines will be drawn somewhat like this. Right? And this will be along this direction and so on. Hopefully now you can understand it. Right, for over here as well, and from positive charge to negative charge always. Why it is curved? Because of the resultant electric field. That means if you want to find out the electric field at any point, what you will do is, at any point the electric field due to positive charge will be always outwards. So outwards basically means something like this, right? And due to a negative charge the direction would be something like this, and the net electric field will be the vector sum of these two, which is going to be the tangent at this point. So that's what the point was saying, right? That if you want to find out the direction, at any point, you just draw a tangent at that field line. So you will get to know what electric field, in what direction the electric field is acting at that particular point. So this this first line says the same thing. A field line, first of all, a field line is an imaginary line drawn in such a way that its direction at any point, that is the direction of its tangent, is the same as the direction of the field at that point. Everything's clear till here, right? Got it? Field lines can also be used for comparing the magnitude of the electric field intensity. How's that? If you have got crowded electric field lines at a particular point. For example, let's suppose I am saying that I have got 2 points. I have got one point over here. This is point A, and I have got another point over here. This is point B. We can see that at point A, the electric field lines are crowded. The electric field lines density is more. At a given area, more number of electric field lines are passing through. At the same area, I mean, if I'll just take a area something like this, and I'll draw the same area over here. So more electric field lines are passing from area A than B. So electric field is more dense over here. So electric field intensity will also be more over there. So that's what the next point is saying, right? Field lines can be used for comparing the magnitude of electric field intensity. The intensity of field is proportional to the number of fields crossing unit area at right angles, right? Unit area at right angles, electric lines of force have the following properties. What are the following properties? They are imaginary, smooth curves, can never cross each other. So quite basic things, you might have read all of these things already, but still, let's suppose, I mean, saying that we don't believe in the second point, let's say that we are writing something like this. Let's cut 2 electric field lines, something like this. Alright, now what will happen? At this particular point, now 2 tangents are possible. So one tangent will be drawn something like this, and the another tangent will be drawn something like this, which is not possible. At a particular point, there can't be 2 directions of electric field. Now don't say that, okay sir, just do the vector sum of these 2 electric field lines and make a resultant. That's not how vector sum and things go, right? Just think about it, find the answer by yourself only. Now the thing is that they can't cross each other, they can't cross each other, they are smooth curves, they can never form closed loops, right? So this is actually important. So it means that they always form open loops. They always form open loops. The number of lines originating from or terminating on a charge is proportional to the magnitude of the charge. So if a charge, if the magnitude of the charge is more, the more number of electric field lines are going to emerge out of it or terminate on it, depending on the charge. If it is a positive charge, more number of electric field lines are going to originate. Got it? The number of lines originating or terminating, I have already explained this thing. Electric field lines end or start normally at the surface of a conductor. What do you mean by this? We mean to say that if you have got a conductor something like this, right? And you are saying that we are having an electric field something like this. So at the surface, the electric field line will be always normal. How to know that it is normal? Just draw a tangent at this particular point. So it must make a 90 degree at this point. It can go curve anywhere, but at the surface it must be perpendicular. What's the reason for that? I think we are going to figure out the reason for this particular point in electrostatics, potential and capacitance as well, but I can give you the reason here as well. The reason is that let's suppose the electric field is not perpendicular to the surface. Let's suppose you are again considering that, let's break this law and let's say that electric field is not perpendicular but it is at a certain angle, something like this. Now what will happen? This electric field will have 2 components, and those 2 components are going to be, one is going to be normal to the surface. This is going to be normal to the surface, and one component is going to be parallel to the surface. So we don't have any problem with this thing because that's how the electric field should be. But we have got a problem with this electric field, and the problem that we have got with that parallel electric field is that if you have a component of electric field along the surface of the conductor, then the charges which are kept on the surface will be under some force. The electric field will apply some force on it, right? So if they will apply some force on those charges, the charges will start to move, and that's basically against the basic concepts of electrostatics. Do you remember I told you this, that we are going to use these simple things again and again. So this is the place why we are going to say that electric fields are always normal to the surface of any conductor. Everything's clear? Can we quickly move on? Quick, tell me. Tangent to any field at any point in an electric field gives the direction of electric field. So we have already covered that, right? Now let's talk about electric flux. Next topic is electric flux. Electric flux can be defined as electric lines of force passing through a given surface. And how to actually derive the formula for this? Let's suppose we have got an area. We have got an area something like this, and at a certain angle, and this is the horizontal line, and the electric fields lines are passing like this, right? Electric field lines are passing like this. Got it? Got it? Got it? Got it? Then we are going to do two things. This is electric field lines E. Let's suppose that initially I would like to actually explain this to you. Let's suppose this is my hand is actually the area, and these are the electric field lines, right? If my hand was something like this, right? If my hand was something like this and electric field lines were passing something like this, then I would have said the maximum number of electric field lines are passing from my hand. So the flux was maximum. Now I am saying that I have tilted my hand something like this. Now what is happening? The electric field lines which was earlier passing, which were earlier crossing my hands, are now not able to cross it, right? So now what I am going to tell you for this general case is, let's use the concept of area vector. You must be knowing that area is a vector quantity, and it is always drawn perpendicular to the surface. So if, let's suppose if this is my hand and electric field lines were passing something like this, the area vector will be perpendicular something like this. Is that correct? Right? So electric field lines are passing something like this, area vector is also in this direction. I am saying that right now they both are at 0 degree, they are parallel, right? Is everything's okay? At this particular point, let's say the area vector is perpendicular to the surface and somewhat like this. So this is the area vector, and this is the electric field, and the angle between these two is theta. So the formula for electric flux that is written by phi will be E dot A or EA cos theta. EA cos theta. Is that correct? Got it? Is that correct? EA cos theta. Now, because we are talking about dot product, that means it is a scalar quantity. So flux is a scalar quantity, electric field and area both are vector quantity, but flux is a scalar quantity. Flux is positive if electric field lines are leaving the surface. So this is something that we must understand. Let's suppose that we have got a cube something like this. And electric field lines are, hopefully you can understand that from what phase I am talking about. Electric field lines are passing something like this. So the area of this phase times the intensity. So let's say area is A, electric field is E. So the flux that is incoming will be written with a negative sign, and it will be E times A. That's what we are trying to say with the negative flux. Are you getting it? Right? And it makes complete sense. If I am going to talk about the area vector of this side, the area vector will be drawn something like this. This will be the area vector. And the electric field is in this direction. So we are talking about cos 180 degree. Right? Got it? Got it? Got it? Everything's clear? Right? And these electric field lines are all also going to pass through this phase, Now we are going to say that this is outgoing flux, right? So that's what we had written, that if flux is positive if electric field lines are leaving the surface, flux is negative if electric field lines are entering the surface. Got it? Everything's clear? Done? Moving on to something which is of our use of right now, and that is Gauss law, right? Let me explain what Gauss law is. Gauss law's statement is the total flux emerging out from a closed surface is equal to the product of sum of enclosed charge by the surface and the constant 1 upon epsilon naught. So this is the statement of Gauss law. Quite easy to understand, but let me explain it using an example. And the example is something like this. What does Gauss law says? Gauss law says, let's suppose we have got a closed surface. So this is a closed surface. Right? And we have got, let's suppose we have got some charges over here. We have got Q1, Q2, Q3, Q4, and by the way this one is positive, this one is positive, this one is negative, this one is negative, and we have got some charges like Q5 and Q6. Alright, this is the thing. We have got a closed surface, we have got some charges which some of which are inside it, some of which are outside. Sir, when theta is maximum, dear, when theta is maximum, it means that whether you are talking about from 0 to 90, so theta will be maximum, then there will be no flux, Kirti, right? When theta will be maximum, it would be something like this. This is my hand, this was the theta, this was the area vector, right? Right now the area vector was 180 degree. Now let's suppose theta is maximum, that is now the theta is 90 degree. What do you mean by theta? Theta is the angle between electric field and the area vector. So if theta is maximum, that is 90 degree, it means that now the flux will be 0. There will be no more electric field lines passing through it. Is that good? Clear? Your doubt is getting clear? Done? Quickly tell me, can we move ahead with this one? Now what does Gauss law says? Gauss law says that the net flux is actually equals to the enclosed charge divided by epsilon naught. This is what the statement of Gauss law is. Now the next point is, what do you mean by enclosed charge? What do you mean by enclosed charge? So enclosed charge basically means whatever charge is inside this surface, right? Whatever charge is inside that surface, write them with their sign. You don't have to worry about the signs of that charges. Is that correct? Right? So it means that enclosed charge would be Q1 plus Q1 minus Q2 plus Q3 and minus Q4. That's what we mean. Is that correct? After this, we are going to say that, okay, so this means that the net for this electric field, I'll use this symbol is used for surface integral. This symbol is used for surface integral. I'm going to write E dot ds. E dot ds is actually, this is nothing but this is net flux. This is actually equals to the enclosed charge, which was this Q1 minus Q2. I'll just write it as Q enclosed for now, because I have told you what enclosed charge means. So Q enclosed divided by epsilon naught, right? This is something which is important for your board plus for all of your competitive exams. Got it? Next thing is, this is actually quite important, that in this formula, please note that you have got two things. You have got electric field written over here, and by the way, this is also a vector quantity ds. You have got electric field written over here. This electric field is it is due to all the charges. It is due to all the charges. I am explaining it to you. First of all, where are we finding the electric field? We are trying to find the electric field, let's say at this particular point. At let's say this particular point. So let's say we draw a small area at this point, dosto. Right? Let's draw a small area at this point. Let's say it is ds. Hopefully you are able to get it. This is, let's say this is ds vector. Right? And it will be something like this. I don't know in which direction the electric field is, because I don't know in which either it is net positive or it is net negative. Now hear me out. When I am trying to find the electric field at this particular point, I am saying the net electric field will be due to all the charges, not only the charges which are inside of it, but also with Q5 and Q minus Q6. It will be due to all the charges. But why are we just writing the enclosed charge as Q1 minus Q2 plus Q3 plus Q4? So this Q enclosed is only those charges, which are inside of surface. So what's the logic behind it? And why are we doing it? The logic is that if you are talking about Q5 and minus Q6, just think about it like this. Q5 is positive, so the electric field coming out of Q5 is going to be like outwards, it is a positive charge. So let's say this is one of the electric field lines, right? It enters the surface. You are going to say, sir, see, flux is getting linked. That's how the terminology we use. Flux is getting linked. I say, okay, so this is the incoming flux. One electric field line entered it and one electric field line get out of it, right? So what is the net flux? 0. So it will happen with all the field lines. So what is the net flux due to Q5? That is 0. That's why we are not writing it in the enclosed charge. But electric field will be because of that as well. But you don't have to worry about, so sir, how we are going to get it. You just have to apply the Gauss law. But for your concept, please remember that's how this thing works, right? Are you getting it? Done? Everything's fine, right? Clearing this thing. Now let's move to some applications. I'll explain one or two applications over here. Before that, let's see some. So Q enclosed is the algebraic sum of the enclosed positive and negative charges. Electric field due to charge outside the Gaussian surface contributes 0 net flux through the surface. This is very, very, very important, right? Is that correct? Good. After it, electric field due to a charge out. Okay, so we have done that. Moving on, let's talk about, when we are going to talk about the, just a second. Okay. Now, when we are going to talk about the applications of Gauss law, then we are going to say that how to choose those Gaussian surface. What do you mean by that? Let's take an example. In applications of Gauss law, the first one is electric field due to a long charged wire. So that means we have got something like a long charged wire, something like this. And when they are saying that we have got an infinite long charged wire, it means that it is actually the electric field is moving towards infinity. The line is moving towards infinity, right? Something like this, right? And for simplicity, let's just say that it is a positive charge. Now we are going to assume a closed surface around it, and that closed surface, it's going to be called as a Gaussian surface. Now there are certain rules to actually take those Gaussian surfaces. And what are those rules? The first rule is that the Gaussian surface must cover this entire whatever the wire or whatever the conductor that we are taking, whatever the element that we are taking, the Gaussian surface must cover it, right? So let's take the Gaussian surface something like this. So in this case, we are taking it as a cylinder. Now you will have to actually remember all of these things. I mean, what I am trying to say is that you cannot really wish to take any other Gaussian surface for this case. If you will do it, you will actually there will be some errors and you will not be able to find the correct answer, right? So the first principle was, the first rule was to take a Gaussian surface such that it covers the entire wire or whatever the shape that you are talking about, whatever the conductor that we are talking about, right? The second rule is that if you are going to talk about this entire Gaussian surface, we have got three surfaces over here. We have got one curved surface, and we have got two circular surface. We have got a circular surface over here as well. Is that correct? Right? So the net flux is going to be, and let me just name them. So this is, let's say this is surface 1, this is surface 2, and this is surface 3. So the net flux is going to be written as flux linked with the surface 1 plus flux linked with the surface 2 plus flux linked with the surface 3, right? Also, flux is nothing but E dot A electric field dot area vector. That's what the electric flux is. So let's draw electric field and area vector. So for the first surface, the electric field will be drawn something like this. Electric field will be drawn something like this. And you can also draw the electric field over here. That's how we are drawing the electric field, right? What about the area vector, friends? The area vector will be drawn something like this. This is what the area vector is. And what is the angle between these two things? The angle is actually 0 degree. Is that correct? Let's do the same thing with the curved surface as well. So the area vector over here is actually something like this. This is the area vector. And electric field is still in this direction only. Over here there is also positive charge, right? So the area electric field is in this direction. So here the angle between these two is actually 90 degree. It means that when we are going to talk about the dot vector over here, over the second surface or for the third surface, it will be 0. And the net flux will be only with the first surface. So that means E times area, and for area I will write it as E times ds, integral of ds, because E is uniform, equals to enclosed charge. Now for this, please understand, we have to write here as enclosed charge divided by epsilon naught. Is that correct? Right? Quick. Students, please write down in the chat box if everything's clear till here. If the diagram is all good till this point, write down in the chat box. It is Q enclosed divided by epsilon naught, right? Instead of Q enclosed, let me say that we are considering this much amount of length is actually L. And now we are going to actually coin a term that we are going to say that let's talk about linear charge density. Linear charge density. Let's say the linear charge density is lambda. That means for a unit length, we are going to start questions after this. Don't worry. We are going to start questions after Gauss law. We are going to have some multiple choice questions, poll questions, everything we are going to cover it. Let's say linear charge density is lambda. That means in a unit length, lambda amount of charge is present. So for Q enclosed, I am going to write this amount of length is lambda, this amount of length is L. So that amount of charge will be lambda times L divided by epsilon naught. And what is the curved surface area of this cylinder? So that is curved surface area of this cylinder is 2 pi. This distance is, let's say, r. This distance is, let's say, r. So this is going to be 2 pi R into L equals to lambda times L divided by epsilon naught. So, L can be cancelled out and you have got your formula of electric field as E equals to lambda upon 2 pi epsilon naught into R. So, this is something that we are going to say that if you want to find out the electric field due to an infinite line charge at a point at a distance of r from it, then this is the formula that you are going to use. Now, the first rule of the taking the Gaussian surface was that the Gaussian surface must be contained inside it. What is the second rule of Gaussian surface? The second rule is you take the Gaussian surface such that either the electric field is parallel to the area vector. So, this is the first thing, either the electric field is parallel to the area vector or electric field is perpendicular to the area vector. So that we really do not have to worry about the different angles, right. We do not have to worry about whether it is 45 degree at certain point, or just take the Gaussian surface as, I mean, after taking the Gaussian surface electric field and area vector, the angle must be either 0 or 90 degree, that is it. Alright, is it all good till here? Quickly write down in the chat box. Can we move on to the next derivation? The next derivation is due to a charged infinite plane sheet, right? Due to a charged infinite plane sheet. For this one, let's just consider that we have got a charged infinite plane sheet, something like this. I will draw it for you. So, we have got a infinite sheet over here, and by the way, this is actually non-conducting, right? Yeah. Something like this, right? So, we've got an infinite sheet over here. Got it, got it, got it. All right, welcome back to all of you who have come back from the zoology class. Good, good, good. Welcome back. Now, for this one, let's consider because it is an infinite sheet. What do you mean by infinite sheet? That if you want to find out the electric field at this particular point, let's say at a distance over here, at a distance of x, then this x is actually very small. This x is actually very small in front of this entire sheet. So, what we are going to do is we are going to assume that we have got a cylindrical surface over here. And this is the cross section at which it is actually getting entered. So, I will draw it something like this. So, this is the case. Now, the thing is that if we want to find out what amount of flux is getting linked over here. Now, again we are going to do the same thing. So, electric field is getting out of it like this. This is the direction in which the electric field is, and from this surface the electric field is getting something like this, right. So, again we are going to write that we know that the net flux is actually equals to the enclosed charge divided by epsilon naught. Is that correct? The enclosed charge divided by the epsilon naught, right. Now, for this one we have got like two surfaces. Let us suppose the area of this surface is actually A. So, area of this surface is also going to be A, right. So, flux is getting linked with this surface and flux is getting linked with this surface. there is no linkage of flux over here because area vector is at 90 degree with the electric field. Is that correct? Right. So same thing we have done over here as well. So now for the net flux I am going to write, because I have got two surfaces over here, I am going to write 2 times of EA equals to, now initially, hi, welcome back everybody. Initially the charge was formed along a line. Do you remember from the center of mass class? The charge was distributed along one dimension only, along a line. So we said that let's talk about linear charge density. Now the charge is along a area. It is distributed along an area, right? So we are going to now talk about surface charge density, that is denoted by sigma. So instead of Q enclosed, I am going to write surface charge density, that is the amount of charge in unit area times the area. So area is A divided by epsilon naught. So area can get cancelled out and electric field comes out to be sigma upon 2 epsilon naught. Is that correct? Clear, clear, clear. Moving on. Can we move on to the next topic? Quickly tell me in the chat box. Can we move on to the next topic, or shall we start solving some questions? If you are going to talk about conducting sphere, this is actually quite easy. If it is a conducting sphere, I'm going a little fast because this is a partial homework for you. You think about it. If you want to cover a sphere, so we have got a sphere, and by the way it is a conducting sphere. So what do you mean by a conducting sphere? It means that even if you are going to throw some charge inside the sphere, it is conducting, and because of that conduction the charge is going to come towards the surface. So the surface will always lie on this thing. Well, the solid, even if you have got like a, see, I'll break it down for you. I'll break it down, then we are starting questions. So don't worry. This is the last topic. After this we are starting questions. I'll break it down for you. How many types of spheres are there? So when we are going to talk about spheres or shells, either you can have conducting spheres or shells, or you can have non-conducting. Non-conducting is not in course. By the way, it is quite easy. You will have to use a little bit of your again volume charge density. Other than that, nothing's really difficult. Then in conducting also, we are going to talk about like solid, and we are going to talk about shells. So even if it is a solid or if it is a shell, there is no difference. Why? Because even, so what do you mean by solid? That there is matter inside the shell. There is matter inside the shell, right? So even if we are talking about a solid shell, still the charge is on the surface. And if you are talking about a shell, well, you only have surface to hold the charge. You have got inner and outer surface, right? If you have got a non-conducting solid sphere, then the thing is something like this will happen, that you have got charge all over the place. Are you getting it what I am trying to say, right? Everything's clear? Done? So if you are talking about a conducting sphere, there is nothing to worry about. If let's suppose that, say that, okay, find out the electric field at a point which is actually less than the radius. That means an inside point. So draw a Gaussian surface inside O on this. So this is a Gaussian surface. Let's say this is a Gaussian surface. So now you tell me what is the enclosed charge over here. The enclosed charge is 0, so there is no electric field. Enclosed charge is 0, so there is no electric field, right? Done? Got it? I don't have to explain each thing over here. I don't have to explain what's on the surface. Well, on the surface the electric field will be, shall I do it on the surface, R equals to R. So for this the electric field is 0 obviously, because there is no enclosed charge. For r equals to r, I am going to write E times area. Are you following me? E times area. So 4 pi r square equals to, this is the surface area of a sphere, equals to enclosed charge. Let's say the enclosed charge is, total charge is q, divided by epsilon naught. So the electric field at surface will be actually 1 upon 4 pi epsilon naught q by r square, right? For if they are going to ask you for outside point, instead of capital R, just put x. Done? Everything's clear? Quick. Let's start some numericals. Quickly. Quick. Now let me know if you have followed it or not through your numericals. Through numericals, let's find it out whether you are following everything or not. Three charges plus q, capital Q and small q are placed in a straight line of length L at points distance 0, L by 2 and L respectively from one end of line. What should be the value of capital Q in order to make the net force on small q to be 0? Alright, hear it carefully. I am starting the timer, it's for you, right? I think 60 seconds would be sufficient. Quickly solve it, don't waste your time. Let's start. For these polls, just write your answers in the YouTube chat box, right? Just write A, B, C or D, whatever your answer is, just write that. That's going to be, the poll will get that, right? That's how you're going to do it. Poll is over. Let's start solving it. So see what the question is. We have got 3 charges plus 4q. We have got 3 charges and let's be quick. Plus 4q we have got over here at 0, then at L by 2, that means at the midpoint we have got capital Q, and at the last we have got q. That means this distance is L by 2, this distance is L by 2, right? Then this is also q, right? Then they are saying that find the value of capital Q in order to make the net force on q to be 0. Now please hear me out. This is plus 4q and they have not really talked about the charge of the polarity of q. Let's consider it to be positive, right? Let's consider it to be positive. So if it is positive, this force, this charge will actually repel this one. So this is force applied by 4q. Is that correct? Now to make the net force on this charge 0, q must actually attract it. So all I want to actually say is that the sign of this capital Q must be opposite of this Q. That's what I want to say, right? So this is force by capital Q, right? So now let's just equate them. So force due to 4Q is going to be, I am just writing it something like this. The magnitude of force applied by Q will be applied by capital Q. So this is going to be K 4Q times Q divided by the distance, that is L, equals to, this is actually K capital Q small q divided by distance is L by 2 and square of that. So again it will be 4 over here. So I can cancel out K, I can cancel out one of the Q, I can cancel out L square. So capital Q, and I can also cancel out this one. So capital Q is coming out to be Q, but I am going to write it with a negative sign because it is attracting it, right? So it's going to be minus Q, that is option A. Have you got it? Have we got it? Why it would be C? Quickly. Quick. Okay, I'll give you a 30 minutes, 30 seconds more in the next poll. It would be 90 seconds poll. But let's find it out. It's A. Nobody was able to do it. Nobody was able to do it. Was pole not working? Pole was not working. Okay, I'll give you a little more time in the next one. Let's do it. Let's do this one. Alright, let's do this one. A simple pendulum of time period t has a metal bob which is negatively charged. If it is allowed to oscillate above a positively charged metal plate, its period will. So this something like this is happening. We have got a simple pendulum, and it is oscillating above a, and by the way, this is a negatively charged simple pendulum, right? And it is oscillating about a positively charged metal plate. So I have drawn the diagram also for you, and then I am going to give you a time. So let's take 90 seconds. Now do it quickly. You must know a little bit of something about simple pendulum for solving this one. You must know that for simple pendulum the time period is actually 2 pi under root L by G effective, right? Now along with G right now over here, okay, good dosto, along with G, if there was only G, the time period was T, right? Along with G, there is also an electrostatics force acting over here, an acceleration because of that. Acceleration because of electrostatics force. Is that correct? So basically this G effective is more than G. This G effective is more than G. So the denominator is increasing. So the time period will be less, right? So it will be less than T. So it is B. Got it? Easy questions. 44.44% I have got this one correct. Very good, Himanshi. Very good exploration, and there good. Is it all good? Can we move to the next one? Let's move. These are some of the questions which are for your schools as well as for competitive exams, both, right? So I've actually come up with some questions which will be beneficial for all types of students. Let's see this question, and let's be fast, right? In figure 2 positive charges Q2 and Q3 are fixed. So Q2 and Q3 are fixed along the y axis. Exert a net electric force in the positive x direction on charge Q1 fixed. So we have got charge Q1 over here. If a positive charge capital Q is added at x equals to 0, so somewhere over here, right? Then the force on Q1 will. That's what the question is. Then the force on Q1 will. What will happen to that? That's what the question is. Can I start the poll now? Can I start the poll? Got it? 90 seconds. Let's start. Quick. See how simple it is. Can we start? Is the poll time over? It's about to get over. Can we start? what they are trying to say, that we have got two charges Q2 and Q3, we don't know anything, we don't know about the sign of these two, right? No, sorry, we do. These are two positive charges. So we have got two positive charges over here. So I have got Q2 is positive and Q3 is positive. All right, fine, done. Because of these two charges, the net force acting on Q1 is along the positive x-axis. Fine. So let's draw it. So on Q1, the net force is along this axis. That's what they are saying. This is along this axis. What does it means? Just think about it. When will this happen? This will happen when we have got this charge will actually attract this charge along this direction. This charge will attract this charge in this direction, and they will have now two components, something like this. They will have two components. One will be along over here, one will be along this side. For this one as well, one will be along this side and the another will be along, another will be actually along this side, right? And now they will cancel out each other, and so this will be the direction of the resultant force. Everything's clear, everything's fine. This is the net force direction. And when will this happen? This will happen when this is a negatively charged body, because they have already told us that these two are positively charged bodies. Got it? After that, you have also added one more positive charge. So now what will happen? There will be one more force acting on this in this direction because of that positive charge. So it means that that force on Q1, the force on Q1 shall increase along the positive x-axis. So it would be A. It would be A, not B or not D. Why it would decrease? Why it would decrease? This one is negative, this is for sure. And now we are starting, we have actually put another positive charge over here. So it will also attract it. Polls are on YT chat. You just answer your questions on YT chat, your answer will be taken, right? Got it? So the correct answer is going to be option A. Whoa, almost all of you have opted for D, but the correct answer is A. But I can explain it again. If you have any doubt, I can explain it again. I will not move to the next one if you have any doubts. Quickly, but quickly tell me. Quick. If you have any doubt, let me know, else let's move on. Fine? Can we move ahead? Alright, let's move. Let's talk about the next question. Simran, please ask your doubt, dear. Okay, I'll come back to the next one. I'll explain it again, but hear me out carefully. They were saying that these two are positive charges, and because of these two positive charges, there is a net force on Q1 which is along x-axis. How is it possible? This is only possible when these are going to attract the Q1 along these red lines, and the resultant of these two red lines is only going to be along the x-axis. That is the only possibility, right? Now this means that if these are positive and the forces are along these things, that means this is a negative charge. And if this is a negative charge, and in the second part of the question they are saying to you that we have got another positive charge Q over here. So that means now this is also positive, this is, we have found out that this is negative, so this positive charge will also attract it along the positive x-axis. So that means it shall increase along the positive x-axis, the net force on it, right? That's what the thing is. Got it? Moving on to the next one, quickly do it. The electric flux through the surface. This is the question, easy question, giving you time. I think it would be more than sufficient. Quickly do it. Now I want to see some good percentage on the correct one. Quick. Is it good? Is it good? You know the answers. You know it, dosto. Don't get confused about the net flux. Net flux formula is enclosed charge upon epsilon naught. That's it, right? So it's enclosed charge. So enclosed charge is same in everything, in every object, plus q plus q plus q plus q, so it would be same for all. Is that correct? So D is the correct answer. Quickly tell me if this is all good. Very good, great, 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 great. Let's move ahead. Let's move to some new questions. Let's do this one. Have we solved it? Have we solved it? Now we can quickly do it. If you have got three charges placed at the corner of an equilateral triangle, that means the net force, I am not giving this for the poles, right, because we have already done it. The net force on any charge will be actually root 3 times of F, and root 3 time of F is actually K Q square by A square, right. So root 3 K Q square by A square, so D. Now you can just remember these things. Is that correct? Not giving this for poles because this one is quite easy. What about this one? The figure here shows electric field lines, and you just have to find out, by the way dosto, this is P1, this is P2 if you can't see, and here they are at certain distance. They are saying that then which of the following statement is true? They are talking about where the electric field will be more. Easy, not giving for poles, don't want to waste the time, this is quite easy. The electric field will be stronger at that region where the electric field lines are more crowded. So at point 1 it is more crowded, so E1 is greater than E2. Is that correct? Quickly tell me. Let me give you one or two more questions, then we'll move to the next chapter. Last question for this class, for this particular chapter, then we are moving to the next chapter, right? A hollow cylinder has charge Q Coulomb within it. If phi is the flux in unit of voltmeter associated with the curved surface B, then the flux linked with the plane surface A in unit of voltmeter will be. Alright, so this is the question. 90 seconds is the time. Let's start solving it. So for this one, we know that the enclosed charge is Q naught. Enclosed charge is Q, right? That's what we know. The enclosed charge is Q. Alright. So it must be somewhere over here. Then if we are going to talk about the net flux, we know that the net flux will be written as the flux linked with surface A plus flux linked with surface B plus flux linked with surface C, and this will be equals to the enclosed charge divided by epsilon naught. Now out of these two, A and C are exactly same, so the flux are also going to be same, right? So let's just write them as 2 times of phi A plus phi B is nothing but phi, that's what they have given as curved surface, Q by epsilon naught. So that means phi A will be actually equals to Q by epsilon naught minus phi divided by 2. So that means 1 by 2 Q by epsilon naught minus phi is the correct answer. Is that correct? So A is correct, not B or not D. A is correct. 42.86. But now tell me if everything's clear till here. So now we can start our next chapter, that is electrostatics, potential and capacitance. We are not going to indulge in, we are not going to give same time for every chapter, because I have told you electrostatics is similar to magnetism. So whatever we have done till here, in magnetism it will all get repeated. So in magnetism we'll swiftly move. We'll talk about Biot-Savart's law, we'll talk about Ampere's law, but things are quite similar. Are you getting it? Right? Here we have got electric field lines, there we have got magnetic field lines, here we have got electric dipole, there we have got magnetic dipole. Here we talked about electric dipole in uniform magnetic field, there we are going to talk about magnetic dipole in uniform magnetic field, right? We are going to talk about torque there as well. So similar kind of things. Again and again I am saying, dosto, for polls you just have to write down your answer in the chat box, just like A, B, C or D, that's it, right? Now let's start with the electrostatics, potential and capacitance chapter. And when we are going to start it, the first thing that will come over here is electrostatics potential energy, right? Electrostatics potential energy. Now the last time you studied potential energy might be was in circular, in simple harmonic motion, right? Do you remember it in grade 11th? And do you remember that always the potential energy is actually associated with a conservative force. So a conservative force is required, is actually required so that we can actually talk about potential energy, right? This is actually very, very important. What do I mean by that? If an external force does some work against a conservative force, then only there is a concept of potential energy. We talked about in the last week's marathon class also, isn't it? Right? Here also this electrostatics force is actually a conservative force. Let me explain it. So let's suppose that we have got a charge Q over here, that is a capital Q charge, which is actually, let's assume that it is fixed at this particular point. Going through the basics, so please hear me out carefully. We have got a capital Q charge over here which is fixed at this point, and at certain distance, let's say at a certain distance of r, we want to place a charge, another charge Q naught from infinity, right? From infinity. So if this charge needs to be at this particular point, for that what needs to happen? Let's suppose that in this journey the charge is somewhere over here, over here as Q naught. This is also positive, and I'm just assuming that this is also positive. So after this, we know that this charge is going to repel this Q naught in this direction with an electrostatics force, and that is Fe. With an electrostatics force, you all will agree with me, is that correct? Fe, and this Fe is nothing but Q naught by whatever that distance is. This means that the external force must act in this direction. This is the direction in which the external force must act, and the body is also getting displaced. It means that the external force is doing some work. This work will be stored in the form of electric potential energy or electrostatics potential energy in this system, not just in a particle or in one of the particle, in the system, right? So the work done against electrostatics force will be stored in the system in the form of electrostatics potential energy. That's what the thing is. Are you getting it? Everything's clear with the conservative force and with why we are talking about all of these things. So the first thing is to understand that electrostatics force is a conservative force. Now if you want to find out the work done by the external force, so work done by the external force will be actually, now we'll have to use a little bit of integration over here, obviously. Why we need to use integration? This is the second point, that you usually are facing trouble in physics because sometimes there is differentiation, sometimes there is integration, sometimes you don't use it. And why is that? In MGH we were not using integration. Why we were not using integration, right? The reason is The reason is that right now please see that this force, that is this external force at this particular point, let us say at this particular point the distance is actually x. This distance is actually x. Please understand. Now with change in this distance, force is going to change. Are you following what I am trying to say? When you are going to change the distance, force is going to change, and when force is going to change, you just can't put one value, can you, right? So we are going to write something like this is going to be the integration of external force dot dx, and because right now the dx is now this is actually something really important, this is the dx, right, and this dx is actually decreasing, so I am going to write a negative sign in front of it. This is something really important, right? After this, just integrate it, and after integrating it, we'll get, what I'll do is I'll just solve it over here only, right? So this will actually negative times of integration of k, force was dosto k q q naught divided by x square times dx, and from infinity to r. Please tell me if you have any doubt till here. After this, if you will integrate it, can everyone easily understand that after integrating it, the work done will come out to be, I have got a negative sign, k q q naught will come out, and I have to just integrate 1 upon x square with respect to x, and the limits are from infinity to r, and the integration is actually nothing but negative times of k q q naught, and this is going to be actually minus 1 by x, and the limits are again from infinity to r. We have got 1 minus over here, 1 minus over here, so the work done doing all of these things is k q q naught by r. That's it, dosto. Now please hear me out again. Hear me out again quickly. Quick. This was the system. I mean, you wanted to bring, I mean, when I say you, an external agent wanted to bring a charge q naught from infinity to this point, right? So finally the system looks something like this. Finally the system looks something like this, that you have got a charge q over here, you have got a charge q naught over here, the distance between them is r. Now if somebody asks you that what is the potential energy of this system, so this is the answer. This is the potential energy of the system. Are you getting it what I am trying to say? So this is the potential energy of system. Please write down in the chat box if this is all good, right? And after this, everything is very easy. The work done per unit charge is actually nothing but is actually potential due to a point charge, that is k q by r, right? That's what you have learned. Electric potential, and the definition that you have been learning from grade 10th. That's what you learned it. The amount of work done to bring a unit positive charge from infinity to a known point. Now you have got it. So it's really nothing like electric potential is not a very big thing. First understand electric potential energy. What is that? Electric potential energy is the potential energy of the system. Now you are going to ask it where the system has got this energy. The system has got this energy from the external work done, from the external force. The external force has done some work. That work is getting stored in the form of electrostatics potential energy. Is that correct? Quickly write down in the chat box. Does it make sense? You guys have been learning about potential energy, conservative forces, all sorts of things in work per energy. Does it make sense? Quickly. That's why I said to all of the Yakin English students that please attend these classes, so that, I mean, now you can actually relate, you can actually connect all of the things that you have studied in work per energy to a grade 12th topic, right? Alright, good. Got it? Now again, electric potential is a scalar quantity as potential energy is a scalar quantity. Only difference is the SI unit of this electric potential is volt. It is volt, right? When we are going to talk about the electric potential difference, we mean to say it is the work done in bringing a unit positive charge from one point to another point. That's it. So I am actually killing all the topics at once, right? So we have talked about electric potential, we have talked about electric potential difference, right? Electric potential due to a point charge. What would be the electric potential due to a point charge at a point? It would be just K Q by R. That's what it is. Is that correct? And we have got to know how we have got this formula, right? Is it all good? So understand it from electrostatics potential energy, then it will be all good. After this, the same thing we are going to do it for potential energy of system of charged particles, right? Potential energy of system of charged particles. Before reading all of these things, let me give you an example, right? After getting to know it, the reading is actually quite easier. The answer is that let's suppose we have got a system like this, and somebody is asking you that what is the potential energy of this system. I have got Q1 over here, I have got Q2 over here, I have got Q3 over here, and by the way these distances are something like, let me take it as A for simplicity, or I can just take any other things also, right? So let me just take it as A, right? And now they are asking that what is the potential energy of this system. What they mean to say is that what is the electrostatics potential energy of this system. That's what they want us to know. So what would be the electrostatics potential energy? The answer is, first of all, remove all of these charges and let's say all the charges are at infinity. Q1, Q2 and Q3, all the charges are at infinity. Got it? Everything's clear? Done. So first let's bring Q1 charge from infinity to this system, right? So let's bring Q1 charge to this point. Now tell me what is the amount of work done, to bring Q1 charge from infinity to this point. You are going to say, sir, there was no work done. Why? Because, well, basically, I mean, there was no charge to repel this Q1. So we don't have to do any work. We can just bring this charge without doing any work, without applying any force. Is that correct, right? Don't really think like, okay, sir, if we are moving it, how come we are not able to apply any force, right? Please understand, when we were talking about the initial concept also, we were saying that the force is exactly equals to what? Exactly equals to the conservative force. We don't want it to accelerate. Is that correct? Are you getting it? So there was no work done in bringing this Q1 charge to this point. But after Q1, let's suppose I want to now bring Q2 charge at this point. Now in bringing Q2 charge at this point, there will be work done, and we are going to write it as work done in bringing Q2 charge is going to be potential due to Q1 multiplied by Q2 charge. This should make sense to you. Why? Because potential was amount of work done to bring a unit positive charge. Let's suppose to bring a 1 coulomb of charge, the amount of work done is 100 joules at this point. So if I want to bring a unit positive charge from infinity to this point, I will have to do 100 joules of work. External force will have to do 100 joules of work. So if you want to bring Q2 amount of charge, so just multiply 100 with Q2. That's what we are trying to do. Are you getting it? So what is V1? V1 is nothing but K Q1 by A times Q2. Similarly, when you are going to now bring the third charge particle, now you will have to do work because of Q1 also and because of Q2 also. So the work done in bringing Q3 is going to be V1 into Q3. By the way, this is V1 at this point plus V2 into Q3. So this is going to be K Q1 Q3 by A, and that's why I actually to remove the confusion, I should actually say this is actually 1 2, this is actually 1 3, and this is actually 2 3. So this is going to be A 1 3, this is actually A 1 2 plus K Q2 by A23 into Q3, and finally the total potential energy of this entire system is going to be the electrostatics potential energy of this entire system is going to be let's just add them, K Q1 Q2 by A12 plus K Q1 Q3 by A13 plus K Q2 Q3 by A23. So this is the final answer of the entire system. Now if you have got a numerical for this, you don't have to think all of this, you just make the pairs, that's it. Got it? You just have to make the pairs, that's it, that will solve your problem. So if you have got a rectangle, if you have got a square, I'll just explain it, but first of all tell me if you have got any doubt till here, then I'll move on. If you have any doubt. So let's suppose you have got a square and the charges are Q1, Q2, Q3, Q4, and the distances are A and A, right? So again the potential energy of this system is actually equals to, and when I say potential energy, of course electrostatics potential energy is equals to the amount of work done to assemble all of these charges. And if somebody says what is the amount of work done to disassemble, to actually to take all of these charges again to infinity, that will also be the same, right? So what is going to be the final answer for the potential energy of the system for this case? So again now see, just make pairs दोस्तों, ठीक है, alright. So for Q1 make pair with Q2, for Q1 make pair with Q3, for Q1 make pair with Q4. Then for Q2 make pair with Q3, for Q2 make pair with Q4. Don't again write for Q1, we have already done it. For Q3 just write it for Q4, and we have already mapped Q4 with everyone. So this is a quicker way to solve it, right? So it would be just K Q1 Q2 by A plus K Q1 Q3 by A root 2, that's A root 2 of course, plus K Q1 Q4 by A. So we have written everything with Q1, then write K Q2 Q3 by A plus K Q2 Q4 by A root 2 plus K Q3 Q4 by A. That's it. This is the potential energy of entire system. Are you getting it? Quickly write down in the chat box. Everything's clear till here, right? By the way, this is known as self interaction energy. There is also this is known as interaction energy, not self interaction energy. This is known as interaction energy of the system. There is something also called as self interaction, that's not in course, so we don't have to worry about it, right? All right, done. Can we move on to the next topic? We have completed this thing as well. Now let's talk about potential due to an electric dipole at a general point. Let me explain, because there were many students who were asking about do the derivation for a general point case, and then for axial and equatorial I'll leave it to you, because that would be quite easy then after the general point, right? What do we know till now? We know that potential due to a point charge is kq by r. Potential due to a point charge is kq by r, where r is the distance, right? So let's find out the potential due to an electric dipole. Got it? What's your name? What's your name? I'll take it your name. By the way, everything's clear till here? Quickly. So let's make a dipole. Let's quickly make a dipole over here. So I've got a dipole, something like this. Let's say this is minus q, this is plus q, and this is at a general point, right? For now I'm removing this thing. This is at a general point. Got it? Got it? So for at a general point it means that they have said that from this point, that means from the midpoint, at certain angle of theta, we have got a point at a distance of x somewhere over here. We have to find the potential at this point. First of all, for potential the life is quite easy. If you want to find out the potential at any point due to a dipole, it's quite easy. It's not like electric field that you have to find the vector sum, right? Potential is a scalar quantity. So let's suppose at a particular point potential due to one charge is 10 volt and due to another charge it's 20 volt. So what is the net potential? 10 plus 20, it is 30. This is what easy life is, right? Got it? Done? So we don't have to worry about anything about direction and all. But for this one, the problem over here is that we don't know what this distance is, dosto. Are you getting it? We must know the distance, right? So let's say this is actually R1 and let's say this is R2. So the net potential at this particular point is, this is R1 and this is R2. So the net potential at a particular point is going to be, don't write vector or anything, KQ by R1. So a positive charge has got a positive potential, that's what the sign basically means, and a negative charge has got a negative potential, that's it. So we just have to find out R1 and R2, that's what the problem is. Is it good? Right? Now what we are going to do over here is we are going to actually use a small approximation, and that small approximation is, that's what I have taken another slide so that you can understand first and then we can apply it. If let's suppose I have got two lines, something like this. Hopefully you can see that I have drawn two lines. Hopefully you can see that I have drawn two lines, and hopefully you can also, you will agree with me that this angle, the angle between these two lines is actually very, very small. This theta is very small. Is that correct? So if theta is very, very small, then can I say that these two lines are exactly in equal length? You are going to say, sir, please don't say exactly in equal length, say that it is approximately equal. Okay, that would be correct. So we are going to say because this theta is very, very small, but if this theta was not very, very small, then we could not have said that, right? So using this thing, I'm going to again apply the same logic over here. I'm going to say, see, these thetas are not looking very small in my diagram, but they are very small. The reason is that this dipole is not that big. This dipole is very, very small and this distance is quite large, right? But again, for drawing all sorts of thing over here, I am drawing it like that. Now please see. Now what I am going to do over here is I am going to drop a perpendicular like this. From here I am going to drop a perpendicular like this. What does it mean? It means that the length from here, please see again, the length from here till here is equals to R1 by that same logic. Is that correct? By that same logic, this distance is exactly equals to this one. By the way, this is A, this is A. So this length is going to be A cos theta, what I am talking about. This length is going to be A cos theta, right? So that means R1 can be written as x minus A cos theta. Is it correct? See, this is x, this is x, this is A cos theta. So what is this? This is x minus A cos theta, so that would be equals to R1. And similarly for hopefully you are getting it, what I am trying to do. Quickly tell me if you have any doubt. Now again for this one I am going to draw a line something like this, right? And then I am going to drop another perpendicular something like this on this one, and this is the 90-degree angle, right? Everything's clear? Again this thing is also A cos theta, right? So now for R2 I can write R2 is actually x plus A cos theta. So these are the two things that we needed to, we wanted to do. So the net potential will be KQ upon x minus a cos theta minus KQ upon x plus a cos theta. Don't have to, again I am always saying you don't have to worry about signs. KQ can be taken as common. This will be written as x plus a cos theta minus x plus a cos theta whole divided by x square minus a square cos square theta, right. So you can cancel out x, you will be left with the formula that you are going to get over here is the net potential is KQ, and you can just multiply this also, so that you can 2KQ a cos theta whole divided by x square minus a square cos square theta. Is it all good? Is it all good? Clear? Quickly say. Now the special thing about here is that you don't have to worry about now the other derivations. For example, if we are talking about axial point, just substitute theta equals to 0 or 180 degree. So if you are going to substitute theta equals to 0 degree, you will get KQA divided by x square minus a square. So you will get V net as 2KQA divided by x square minus a square, and which further can be actually written as KP upon x square minus a square, right. And again same thing, if you are going to say that it is a short dipole, a square can be neglected in front of x square, right. Of course k is a constant, buddy, right. And if you are talking about equatorial point, so for equatorial point theta will be actually pi by 2, that is 90 degree. So the net potential will be 0, and that's what it should be, isn't it? If you have got a perpendicular bisector over here, that means R1 and R2 are equal, and that means we have got a positive charge plus q, we have got a negative charge minus q, the net potential would be 0 over there, because the magnitude is same and we have got a difference of sign. Is that correct? Alright, can we move to the next topic? That is potential energy of a dipole in uniform electric field, right. We did study that the torque acting on an electric dipole is given something like this. That is, torque is actually written as PE sin theta. Now we have got something written over here as well. Let's suppose that initially it is at angle theta 1, and we have to actually change the direction in anti-clockwise from theta 1 to theta 2. We have to change the direction from theta 1 to theta 2. Everything's okay with the dipole derivation, right. Now we are talking about the potential energy, and the diagram is something like this. So we have got a dipole which happens to look something like this, and right now it is at certain angle theta 1, and we want to rotate it up to angle theta 2. That's what we need to do, right. So if you are rotating it, if you are moving a body, you would have applied a force. If you are rotating a body, you would apply a torque, right. The torque would be applied. But the thing is, please understand, the electric field wants to rotate this system in this direction, in clockwise direction. Why is that? The reason is because the electric field is applying the torque to do that, right, to align the dipole along its direction. Is that correct? So you will have to apply you will have to actually rotate it in anti-clockwise direction to move it from theta 1 to theta 2. So that means the work done, the small, first let's find out the small work done. So the small work done would be torque times d theta, and if you want to find out the total work done, let's just integrate it. So we are going to find it as Pe sine theta times d theta, and let's integrate it from theta 1 to theta 2. So integration of sine theta is minus cos theta. So finally you are going to get your answer as Pe, okay, I'll write it with all the steps. So Pe minus cos theta and theta 1 to theta 2. Now I'll just switch to the final answer. You are going to put the final limit of course, but here we have got a negative sign, and then we have got we are going to put lower limit using a negative sign, right? So let me first write it as cos theta 1 minus cos theta 2. Hopefully everybody is clear with this one, right? All good. Sometimes what happens that electric dipole is something like this. This is the electric field and electric dipole is something like this, right? And they tell you that what is the amount of work done, or what is the amount of work done to rotate it by a certain angle theta, right? So in that particular case, we are going to say that if theta 1 is 0, if theta 1 is 0, right, and you just want to rotate it up to a certain angle, then the potential energy stored in that dipole is actually minus Pe cos theta. This is important. This is actually important. Minus Pe cos theta. Is that correct? Right? Where these theta belongs to. This theta is there. Initially, okay, I'll explain what this theta is. Somebody has asked the doubt. The theta 1 and theta 2 are the angle between the dipole moment and the electric field. Are you getting it? So this was, if you remember, this was minus q, this was plus q, right? Now I'll look a little funny, but I'll explain it to you. So that means in this direction, we have got what? Dipole moment, right? In this direction we have got electric field. So this is the angle between theta. So initially the angle was theta 1. We want the angle to change from theta 1 to theta 2. So the change is between theta 1 and theta 2. So the amount of work done is this. Is that correct? Is it clear? Now I am saying that let's suppose initially the theta is 0. What does it mean? That the dipole is something like this, and electric field is also like this. Is that correct? This is minus charge, this is plus charge, so this is dipole moment. This is the direction of dipole moment, and this is the direction of electric field. So theta 1 is 0, and for theta 2, let me just write theta 2 is some theta. Is it all good? Or are you saying that what the theta? Tell me quickly. Is it all good? Quickly. So this is the potential energy of the system at that particular angle theta. Clear? Now this is actually very important. Why? Because if we are talking about potential energy, we are going to also talk about stable and unstable equilibrium, and also, well, neutral also, right? Well, if we are going to talk about when theta is actually equals to 0 degree, then in that case potential energy is minimum, and that is minus Pe. By the way, this thing can be also written as minus P dot E. For all of those students who have actually talked about dipole moment, no, Ramana, that's not correct dear. Dipole moment is always, it is not about positive x-axis, it is always from negative charge to positive charge. That's what the correct definition is, right? Now come back dosto. Now please understand, this is not electrostatics, this is work power energy. So for all of those students who are not getting all of these things, it means that there are some basic concepts which are not clear for you from work power energy. Alright, now come back. This is minimum potential energy. That means this is the case for stable equilibrium. What do you mean by stable equilibrium? It means that if we are going to disturb the system, disturb the dipole moment at this position, then a restoring torque will act, right? I'll explain it. It means that, let's suppose this is the this is electric field and this is the dipole moment. Here we have got a plus q charge, here we have got minus q charge, and let's suppose we are trying to disturb it, and we are trying to disturb it something like this. We try to rotate it something like this, right? Now what will happen? A force will act in this direction, a force will act in this direction. Well, force was also acting in this direction in this one, but these forces were also cancelling out each other, and also there was no net torque generated because they were collinear forces, right? But when you are going to disturb it, a restoring torque will get generated, which will try to align the torque, which will try to align the dipole in the original position. That's what the stable equilibrium means. Or you can also remember that, okay, when the potential energy is minimum, that is what the stable equilibrium is, right? If theta is actually equals to 180 degree, that means electric field is in this direction and dipole moment is in this direction. In that case, we are going to say that this is the case for unstable equilibrium. If you are going to disturb the dipole moment at this position, then there will be a torque which will actually bring the dipole moment into an entirely new position. There will be no restoring torque. Are you getting it, right? So the potential energy over here will be maximum because cos pi is -1, so this will be actually equals to PE. So remember this is actually the case for unstable equilibrium. Done. Hopefully everything's clear till here. Now after this, we have actually completed almost everything. There are certain notes for you, and these notes are actually quite important, some of which I would like you to note it down, right? Got it? What does negative and positive potential energy basically mean? So negative potential, if a system has got a negative potential energy, I am not talking about this one, right? I am not talking about this one. For this one, we can have a definition for this one as well, but I am giving you a general potential energy definition. If a potential energy of a system is negative, it is possible that there was some conservative forces acting like attractive forces, right? Like for example, as a positive and a negative charge. So if you are going to release a positive and a negative charge, they will actually come close on themselves, right? You don't have to apply an external force to make them come close, right? So what will happen is they will actually use their internal energy to actually increase their kinetic energy, and because of that, the potential energy will drop down from 0 and it will become negative. Are you getting it, right? That's what the reason is. Now after this, let's start with the electrostatics of conductors. This is pretty much basic things that you already know. A conductor is an object or type of material that allows flow of electrical current in one or more directions, right? And how is that possible? That it contains mobile charge carriers in the form of electrons. Hopefully you know what mobile charge carrier means. That means we are talking about, we know that current is rate of flow of charges, but what are those charges? So in a metallic conductor, those charges are electrons. So we are going to say those charge carriers are electrons, right? The valence electrons facilitate the flow of current in a conductor. Conductors have loosely bound electrons to allow current to flow. In an external electric field, they drift against the direction of the field. We are going to talk about all of these things in current electricity also, right? I'll share the PDF in the group. Don't worry about it, right? What else after this? The electrostatics field inside the conductor is 0. That we have already talked about, right? There is no electrostatics field inside the conductor. Why is that? Because the enclosed charge is 0. You can derive it from there. The enclosed charge is 0. So if enclosed charge is 0, that means electric field will be 0 using Gauss law. Got it? The electrostatics field at the surface of a charged conductor is normal to the surface at every point. I have already explained it when we were talking about the properties of electric field, right? I have already explained it, and we have got the written argument over here as well, that if E were not normal to the surface, it would have some non-zero component along the surface. That would actually that would actually give acceleration to the charged particles, and which is actually against the basic concepts of electrostatics, right. After this, the next part of this chapter is actually something that is known as capacitors and capacitances, right, capacitors and capacitance. First of all, let's figure out about what do we really mean by capacity of a conductor and why are we learning about a capacity of a conductor, right. So let's say that we have got a capacitor, we have got a body over here. Right now, let's not use the word capacitor. Let's say we have got a conductor over here, right? And we are constantly giving some charge to it. We are constantly giving some charge to it, right? So if you are going to give some charge, definitely its potential will increase. So Q is directly proportional to V. That means we can actually use a proportionality constant that we call as C, that is the capacity of any conductor or any body, that is C is written as Q by V. Now there are many ways to actually define it. The most proper way to define it using its formula, we can say that capacitance of a conductor is amount of charge. Please hear me out carefully, it's quite easy. It's the amount of charge required to raise the potential by 1 volt. So let's suppose if a body needs 5 Coulomb of charge to raise its potential by 1 volt. So its capacitance will be 5 Coulomb per volt, right? And the SI unit of this is, Coulomb. By the way, Coulomb is for Q, Coulomb per volt or farad, denoted by F, right? The amount of charge needed by the conductor to raise its potential by 1 volt, and that's how you got your formula is Q equals to CV, right? But you can also define capacity of a conductor as the amount of charge that it can hold. This actually sounds quite logical. This doesn't actually come very organically to you, but when I'll say that okay, this body has actually got a limit to hold a charge. After that, what will happen? After that, the charge will get leaked to the surrounding air molecules or whatever the molecule that we have got over there. So every body has got a limit. Up to that limit only they can actually store charge. After that, the charge will get leaked out. So that is the capacity of the body, right? But the technical definition is this: the amount of charge required to raise the potential by 1 volt or to change the potential by 1 volt. Got it? This is what the capacitance is. After this, we are going to actually say that this 1 farad is actually not a very practical unit. Why? You can figure it out that if you really want to find out how big this unit is, you just say that we want to actually make a capacitor. Let's suppose first let's talk about a spherical conductor. A spherical conductor and find out the capacity of that. So we have got a spherical conductor something like this of radius r. Right? You know that potential at the surface is actually K, Q, let's say the total charge is Q by R. So the capacity will be actually Q divided by V, that is K, Q by R. So Q can be cancelled out, that means capacitance will be 4 pi epsilon naught into R. Is that correct? Everything's clear? Right? So the radius is going to, if we want to make 1 farad of capacitor, the 1 farad of capacitor will have a radius of 4 pi epsilon naught times R, and R will be 9 into 10 to the power 9 meters. See how impractical this unit is. This was just to show you that 1 farad is not a practical unit. So that's why we are going to use units like 1 millifarad or 1 microfarad, units like this, 10 to the power minus 3 farad, or mainly we use microfarad, as you might know it, 10 to the power minus 6 farad, right? We generally use these units, and the reason is this, that if you want to create a capacitor which has got a capacity of 1 farad, a spherical capacitor, this should be the radius for that, right, which is not practical. Is that correct? All good? After this, we can now talk about a parallel plate capacitor. A parallel plate capacitor, I will also let you read all the notes that I have got, but first let me explain it. Why do we actually use a parallel plate capacitor, right? Let's suppose that I have got a, first of all, these are the spherical plates over here that we usually draw with a straight lines. Let's suppose that I have got a plate over here and it is being attached with a battery, something like this, right? And we are constantly trying to give some charge to it, right? Now, what will happen if I will take another plate similar to this and I will actually ground this plate. I'll actually ground it. So what will happen is initially what I'm going to do is, initially it will induce some charges on its inner surface, and on its outer surface it will actually have opposite charges. Then we are going to ground it, and when we are going to ground it, these charges are going to go into the ground, well, electrons are going to come up and neutralize them, right? And after this we will be left with a system, we will be left with an arrangement something like this, and that's how we are going to actually show it, right? That's how we are going to show it. So this is actually used to store, it's not stores charge, it actually stores electrical potential energy, right? So we have got plus Q charge over here, and we have got exactly negative times of charge over here, that is minus Q, and the net charge on a parallel plate capacitor is 0. So it stores electrical potential energy in form of electric field, right? That's what the use of capacitor is. But the use of capacitor is to actually supply charge to the system, charge to the circuit when the circuit needs it, right? That's what the basically use it. A capacitor is a type of a body which can actually act as a active element as well. It can act as a passive element as well. What I mean is, it can also get charged like what we can say an appliance. It can get store charge, so it can also use electrical energy, and it can also supply that electrical energy back into the circuit, right? That's what it is used for. Got it? Now we have got over here, as we have got two plates, right? And the electric field between these two plates is actually, it is going to be sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught, and the reason that we are using this as our formula is that electric field due to positive charge is sigma upon 2 epsilon naught, and it will be in this direction, and with a negative charge, negative plate, same direction, I mean the electric field will be in the same direction. So we are going to add them, so the net field will become sigma upon epsilon naught. Is that correct? And electric field is uniform over here. So if I want to write the potential difference between these 2 points, can I write it as potential difference will be net electric field times the separation. So net electric field is sigma upon epsilon naught times distance d. By the way, sigma is charge by area. So let's say total charge is Q, area is A, epsilon naught into d, right? So now finally the capacitance of a parallel plate capacitor will be nothing but charge by area, charge by potential. So let's say charge is Q and potential we have found out it is QD times epsilon naught into A. So Q can get cancelled out, and capacitance formula is epsilon naught A by D for a parallel plate capacitor. That's what the formula is, right? Are you getting it? Quickly write down in the chat box if this is all clear. By the way, you might have a little doubt over here that how can we actually write something like this? How can we write something like this? You might have a little doubt at this point. But other than that, tell me if everything's clear over here. I'll explain it all over again. I'm not this thing, but I'll explain this thing, that what is the relation between potential and electric field. I'll explain it. But other than that, this is the capacitance for a parallel plate capacitor. Clear? After this, actually we should have actually done the relation between electric field and electric potential. This is actually something really important. Relation between electric field and potential. So you must remember this thing, and the formula is, for this one, electric field can be written as negative times of dV by dr. A very important formula. Electric field can be written as minus dV by dr. What does it say? It says that electric field is along the direction in which potential decreases, right? So this is actually quite important. So if I am saying if electric field is uniform, I can write E equals to V by D, right? And from here I can write V equals to E into D. So that's how I have written it. Got it? This is known as potential gradient. Everything's clear? Yes, the ghost has come. Right? So I think after this there is one more important topic, that is effect of dielectric on capacitor. Now first of all, what is dielectric? This term dielectric is nothing but this is an insulator. This is an insulator that we are talking about. Alright. So if you are going to put an insulator inside a plate, what will happen? Let's first figure it out. And when the battery is disconnected and when the battery remains connected, they are talking about two different cases. I am going to explain each one for you, and by the way, this is actually really important. So for all of those students who want to prepare for NEET and mains, this is actually something very important. Lots of questions come from this small topic, right? Figure it out. Let's say first we are talking about a capacitor, a normal capacitor with a dielectric, and we are not talking about that whether we have connected the battery or not. Let's say we have got a capacitor which has got capacitance C. Initially, when there is air inside, the capacitance is C and it's written as epsilon naught A by D. Now when you are going to put a dielectric in it, a slab of dielectric in it, that means a slab of insulator between it, then we are going to say that now let's find out the potential. So now the potential will be new electric field times D. This dielectric actually reduces the electric field, and it reduces the electric field. Let's say E naught was the original electric field. It reduces the electric field by a factor of K. That is what is known as dielectric constant, right? So E naught by K times D. So now if you are going to substitute the new value of potential difference in the capacitance formula, we are going to get actually K times of epsilon naught A by D. So in any case you are going to talk about, the capacitance will actually, it becomes K times of original capacitance. This is what the thing is. The capacitance will increase by K times, right? If you have inserted a dielectric constant K, the capacitance will increase by K times, right? Now let's talk about when the battery is disconnected and when the battery remains connected. These are the two cases. Are you getting it? So we have got a capacitor. We are connecting we are putting the dielectric slab over here when the battery is disconnected. So what will happen in the second case is when the battery remains connected and we are putting the capacitor. These are the two names. These are the two things, right? So now for this one, let me explain it. When the battery is connected, right? When the battery is connected, or I'll use another page. So we are going to say if battery is connected, so the main purpose of this battery is to actually maintain potential difference. So if battery is connected, that means potential difference is constant potential difference, right? And I have told you that capacitance will actually increase, right? Capacitance will increase. So capacitance will increase by k times, that is for sure. After this, what I am trying to say is that potential will not change. So potential is actually, what is potential? Potential is actually Q divided by C. So Q dash divided by C, right? Q dash divided by C dash. So now according to this, we are going to say that Q dash will be C dash times V. V is not changing, C dash has becomes K times, so Q dash will also become K times. Please write down in the chat box if you are facing any trouble. So we have got three things. One is charge. Hi Manchu. One is charge. The another thing is Q dash. Another thing is C dash, and another thing is V. We have got three things. Potential is constant, so it can't change. Other than that, capacitance is increasing by K times. So what will happen with Q dash? It will also increase by K times. Are you getting it? Got it. Everything's fine. Can we move on? Right? After this, if the battery is disconnected, so if the battery is disconnected, now the potential difference can't be same, right? Potential difference can't be same. But one thing will remain same, that is charge. Now the charge will be constant. And why is that? Because it was battery from which the charge was coming. If you have disconnected the battery, now from where the charge will actually come? Are you getting it? If you have removed the battery, now there no more charge can come in. So whatever the initial charge is, that's it. Now no more charge can come into the capacitor, right? So after this, if charge is constant, and again we are going to say capacitance will increase by K times. So now we are going to say that V is actually Q by C dash. So if C decreases by K times, if C increases by K times, then I am going to say that V decreases by K times. So these are the two cases that we were talking about. That's it. Are you getting it? Quick. If you have any doubt, let me know. This was about the capacitance and the dielectric. Alright. Now if you want, we can also have a problem with capacitance with a partially filled dielectric. That is mostly asked in schools, right? That is mostly asked in schools. That is, we have got a capacitor, and in that capacitor we have got a partially filled dielectric. Got it? Done. When the battery is disconnected, what will happen? If the battery is disconnected, then charge will remain constant, potential will change. If battery remains connected, that means potential is constant, charge will same. In both the cases, capacitance will increase by K times. That's it, right? So think it like this, that why you connect battery? What's the purpose of battery? The purpose of battery is to actually maintain the potential difference. So if you have battery connected, that means potential difference will remain same. All good, right? Done. After this, I think we have almost completed the chapter. We have got some questions about, we have got some numericals about series and parallel. Now hopefully you know that in capacitance the formula for C equivalent is actually reverse of that in resistances. So this is for series combination. If you have any doubt, then obviously I can explain it to you, but this is actually quite easy, right? Quite easy. How you are going to solve it? let's suppose you have got a battery over here of V volt, and we have got some capacitors in series. The concept of series is same over here as well, that is the charge will remain same. So Q charge enters, it will move out over here, and finally the Q charge will come, right. This is capacitance C1, C2, C3. The potential drop over here is V1, V2, V3. The total potential is V. This means that we can write, instead of V, we can write V equals to V1 plus V2 plus V3. So for V1, I can write, V1 can be written as charge divided by capacitance, again charge divided by capacitance, again charge divided by capacitance. Is it all good? Does it make sense? Right? Got it, got it, got it. For V, I can write Q divided by C equivalent. I can cancel out this Q, and that's how we are going to get the formula of C equivalent. Now same you can apply it for parallel combination as well. So I think that's quite easy to do, right? After this, let's talk about energy stored in a capacitor. If you are storing some charge in the capacitor, we can find out the energy stored in the capacitor. Work has to be done in charging a conductor against the force of repulsion by the already existing charges on it. What do you mean by this? Let's suppose that you have got a capacitor something like this, and you are storing some charge. It has already some charge Q, and you are still giving some charge into it, right? So that means that the already charge that is present on this surface is going to repel this charge, the newer charge, right? So you will have to apply some work to store that charge. That work done will be stored in the capacitor in the form of potential energy. Is that correct? Is that correct? Clear? Right? So how you are going to write work done as, we know that potential can be written as amount of work done to bring a unit positive charge from a known point to another, from infinity to known point. That means dW can be written as V times dQ. If we are going to integrate it, we can find out the net work done. Instead of V, can I write it as Q by C times dQ, right? Let's say we want to do it, we want to charge it from 0 to some charge Q. So this will be Q square by the Q square by 2C. This is the potential energy of stored in the capacitor, that is 1 upon 2 Q square by C. Or if you are going to write, instead of Q, you are going to write CV, so you are going to write another formula, that is half CV square. So either formula that you want to use it. Got it? Either formula that you want to use it. Now let's start some problems and let's finish this chapter using the problems, right? So whatever the concept that we have still left, let's do it using the problems. Then I'll give you a little bit of break. Quick. For a uniform electric field E along the x-axis, the equipotential surface. So we have not done equipotential surface, but we'll do it using some quotients, right? For equipotential surface, what do we mean by this? Equipotential surfaces are those surfaces on which potential is same, all over the place, all over the surface. And what else do you need to know? That equipotential surfaces are perpendicular to electric field lines. These are the two of the most important thing that we must know, right? These are the two most important thing. Now using these 2 points, you find out the answer for this one. Quick dosto, find out the answer. Quickly look here, the uniform electric field E is along the x-axis. So you have got, this is your y-axis, this is x-axis, and electric field is along x-axis. This is electric field. Quickly tell me the answer in which direction the equipotential surface is going to be. I have explained each and everything to you. Quick. This is the electric field, right? Equipotential surface. So first of all, it must be a surface. Huh? Don't say y-axis or just z-axis. It needs to be a surface. So a surface which is perpendicular to positive electric field, positive x-axis. So this is the electric field. So this should be the surface. So what is this surface, dosto? So this is actually z-axis. This is z-axis. This is y-axis. So this is the yz plane. So parallel to yz axis. Is it correct? Is it correct? Clear? Don't say that it is perpendicular to z axis. Quick. Right? Good. All right. Let's check. So the correct answer should be B. View result. All right. Great. 80% of you have got it correct. Very good, Simran. Very good, Kirti. Good. Let's move to the next one. All right. Whatever we have studied till now, the question is according to that only. All right. Let's do. A capacitor has some dielectric between its plate and the capacitor is connected to a DC source. The battery is now disconnected and the dielectric is removed. Please understand the question is actually very good, right? Explain one more time. About the last one, friend. Quick, this one is actually a good one. So do it carefully. A capacitor has some dielectric between its plate. Now see, it's a reverse of whatever we have learned. We have learned that if you are going to insert a capacitor, if you are going to insert a dielectric into the capacitor, the capacitance will increase by k times. But if you are going to take it out, it will actually decrease by k times. Are you getting it? So first thing is for sure that if a capacitor is connected to the battery is now disconnected. So first of all, if battery is disconnected, I can pretty much say that the charge is constant. No matter what happens with dielectric, please understand one thing. Are you getting it? It's quite easy. If battery is disconnected, charge is constant. After this, then the dielectric is removed. If the dielectric was inserted, then the capacitance would have increased. But now the capacitance would decrease by 1 by k times. Please understand this thing, right? Don't get confused. We are removing the dielectric. So capacity will go down by k times, right? What about new potential? So new potential will charge remain same and new capacity. By the way, new capacity is going down by k times. It means that potential will go up by k times. So now we have figured out everything. It's up to you. You can just find out the answer for this. Capacitance will increase. No, it will actually decrease. So first option is wrong. Energy stored, we'll have to find it out, dosto. So let's write the energy. So U dash will be half C dash into V dash square. So half, instead of C dash I'll write C by K, for V dash I'll write KV. So it would be K square into V square. So energy is actually increasing by K times. So energy will decrease. So this is also wrong. Is everything good? Quickly write down in the chat box. Electric field will increase. Potential is increasing. Potential is increasing. Electric field, uniform electric field can be written as E dash can be written as V dash into D. So V dash is increasing. So electric field will also increase. So this option is absolutely correct. So C is the correct answer. But let's check for the last one. Voltage will decrease. That's wrong. That is wrong. Voltage will actually increase. Quickly tell me if you have any problem with this question. It was a good question. Usually the question comes like we are inserting a dielectric and then the battery is disconnected or battery remains connected. What will happen? Right? Right now they are saying the dielectric was in the capacitor and then we are removing it. Quick answer. Is it all good? Can we move on to the next one? So the correct answer is going to be option C. I think poll has gone. Okay. It is not showing up, but no worries. Alright, no issues. Let's move on. Hopefully you are able to understand it, right? Can we move on to the next one? Alright, let's see this question. Quick. Have I started the poll? 90 seconds. Start. Quick. Three charges capital Q plus Q and plus Q are placed at the vertices of an equilateral triangle of side L if the net electrostatic energy of the system is 0, right? We have talked about net electrostatics energy of the system. Let's quickly solve it. It's quite easy. First of all, net electrostatics energy of that system will be written as, I don't have to draw diagram and all, right? I'll just write it as K Q into Q. By the way, I have got similar Q. So what I'll do is I'll just write 2 over here. I'll write L plus K Q square by L. Everything's okay with this? Well, I've got 3 charges. So I'll have 3 pairs, right? Q with this one, Q with this one and 2 with this one. So these pairs are same. So that's why I've written as 2 times equals to 0. The net energy is 0. So K can be cancelled out or equated it to 0. One of the Q can be cancelled out. L can be cancelled out. So the Q is going to be minus Q by 2. That means capital Q is minus Q by 2. So minus Q by 2 is option D. Hopefully you have correctly done it, right? So option D is correct. Okay. Yes, now we can see the poll. 40% of you have got it correct. Simran good, Kirti good. Can we move ahead? Right? Chalo, let's move to one more question about the capacitor. Do this one correctly. Alright, a capacitor is charged by using a battery which is then disconnected. So this is the main point, that the battery is disconnected. A dielectric slab is then slipped between the plates which results in. Start. a dielectric is slipped, that means capacity will be increased. Battery is disconnected, means charge will be constant, which further means potential will decrease. Reduction of charge on the plates is wrong answer. Why? Because charge will be constant if battery is disconnected. Increase in the potential is wrong answer because potential will actually increase. Decrease in the potential across the plates, reduction in the stored energy. What about stored energy? Let's just write half QV. Q is constant, V is decreasing by K times, so U will decrease by K times. So far so good, but no change in the charge. Everything is correct in option C. Very good. I think now you are getting it. Tell me quickly, is it all good? 77.78%, very good. Simran, Snehal, good. Are you feeling better now? Solving these questions of dielectric getting inserted and then battery getting disconnected, everything's okay. So now let's take a break, but before taking break, let's do couple of questions more. Like for example, let's some questions like this. Let's do some questions of what we can say of these network questions, and let's find the C equivalent of these ones, right? Although these are quite popular questions, but let's do one or two. So for this one, I'll not use pole, but I'll first explain it. Then for some another question we can use pole, right? To solve questions like this, I'll tell you one strategy, and that is to name the points. Let's say this is point A, right? Now in between of these two we don't have any other thing, no more capacitor, nothing, no devices, no battery. Let's say this is also point A, right? This is point B, so this is also point B. Now I cannot name this as point B. I cannot name that as point B, I cannot name that as point A because I have got like some capacitors in between of that. So I'll name this point as point C. Similarly, now I can't name this as point A, B or C. So I'll name it as another point, that is point D. Now let's make this diagram all over again, and it would be something like this, that I have got point A over here. So this is point A, right? And A is connected with C. See, A is connected with C, and in between of that we have got a 20 microfarad. So let's make a 20 microfarad like this. This is point C, this is 20 microfarad. Then A is connected to another capacitor, which in turn is connected to another C. Are you getting it? Done? Right? So first A is connected with D and also D is connected with C. So do something like this. So A is connected with D, and this thing is actually 10 microfarad, and C is connected with D. So between these two, between C and D, we have got 5 microfarad. And then between C and B we have got, let's say this is B, so this is a 40 microfarad capacitor. And again between D and B we have got 20 microfarad. This is a 20 microfarad. So this is something that is called as Wheatstone bridge, right? You must have learnt it in current electricity as well. It comes in capacitance as well. So not a big thing. Just one thing to notice, that if the ratio of these two capacitance is equals to the ratio of these two capacitance, then we call that it is a balanced Wheatstone bridge. So yes, it is actually 20 by 10 microfarad is actually equals to 40 by 20. That is, the ratio is coming out to be 2. Right? So it means that the potential, if this happens, we imply that potential at point C is actually equals to potential at point D. And if these 2 points have same potential, I can actually remove this 5 microfarad capacitor from here. And after this, things becomes quite easy because these two are in series combination. These two are in series combination. And these two are in parallel combination. Are you getting it? Everything's clear till here? Quickly write down in the chat box if this diagram is clear to all of you. Right? You can find the answer by yourself. Do it by yourself. I have explained, I mean, we have almost completed it. Just use the C equivalent formula for this one, that is 20 times 40 divided by 60. Use the series formula, not the series of resistance, right? Same thing with this one as well. Then add them. Alright, moving on, let's do some different questions, something like this. In this one, we have got, this is actually a one capacitor. These are not two capacitors. This is one capacitor. The only difference is we have inserted two different dielectrics over here, and we have inserted two different dielectrics in such a way that they both occupy half of the length, right? Equal length. Absolutely clear? So how to solve questions like this? See, what I am going to say is that this is the plate that we were talking about, and still the area is A. So there is no change in area. Still here the area is A. And let's just suppose that this is an imaginary plate in between of them, which would also have an area A. Right? Clear? First of all, instead of considering it as one capacitor, assume that it is of two capacitors, right? So in reality it is just one capacitor. We are assuming that it is actually two capacitors. Got it? So this is capacitance C1 and this is capacitance C2. C1 is connected between, let's say this is point X and this is, let's say, point, let's just consider it as A. C2 is considered between Y. Can all of you see that these two capacitors are in actually series combination? Right? These are not in parallel. If they were in parallel, then we would have said that both the capacitors are connected between same points. They are not connected in between same points, right? So these are in series combination. Now if I tell you to write C1, what will you write? C1 can be actually written as dielectric constant is K1 times epsilon naught, area is A, and the D is actually D by 2, so I will write something like this. So solving it, K1 value is 1, so it will be 2 epsilon naught A by D, whereas C2 will be K2 epsilon naught A by D by 2 again, so something like this, and solving it, K2 is actually 2, so 2 times 2 is 4, so 4 epsilon naught A by D. Everything's clear? How we have got it? How we have got C1 and C2? If you have any doubt why we have written it as K1 times epsilon naught, please ask in the chat box, right? After this, they both are in series combination. So if they both are in series combination, that means 1 upon C equivalent would be 1 upon C1 plus 1 upon C2. So that means that 1 upon C1 is actually nothing but D upon 2 epsilon naught A plus D upon 4 epsilon naught A, right? So this one is going to be actually 2. So this one be actually 3D by 4 epsilon naught A. By the way, dosto, this is 1 upon C equivalent. It means that just do the reciprocal of that. So C equivalent would be 4 epsilon naught A divided by 3D. So this is your final answer. So because calculating this one wouldn't take time, that's why I have completed it. For the previous one, you do it, right? A. Everything's clear how to do problems like this? So after this, let me give you one more example of a different type of a question, right? For this one, what we are going to actually talk about is that we have got two points A and B, and we have to find out the capacitance of this arrangement. So for these types of questions, what we actually assume is, now this is about actually assumption. We assume that point A is at positive potential and point B is at negative potential. First step to solve questions like this: A is at positive potential, B is at negative potential. After this, we say what the plates which are connected with point A. Since A is at positive potential, just write plus signs over here, and B is at negative potential, so just write negative signs over here. Similarly over here as well, right? Now find out where you can find out the definition of capacitance is actually getting followed. What is capacitance? We have got two plates with equal charge but having opposite magnitudes. Is that correct? So something like this is actually one of the capacitance. Let's say it is C1, this is another capacitance C2, right? By the way, C1 is connected between, one of its plate is connected with A and the another is with B. So I am going to say that C1 is a capacitor which is connected between point A and B. C2 is another capacitance which is connected between point again A and B. It means that these two capacitance are in parallel combination, right? So C equivalent is going to be C1 plus C2, and C1 is actually epsilon naught A. Well, the area must be A, right? Area is A, epsilon naught by distance is D, plus again epsilon naught A by D. So the final answer is going to be 2 times of epsilon naught A by D. For questions like this, you have to follow this strategy. So correct answer is going to be option D. Is that correct? Clear? Quickly tell me in the chat box, is it all good? Good, very good. So now I'll give one question, this question in homework, right? Do this in homework, and I'll also give you a little break for, obviously, for dinner. So this one is in homework. Then we are going to start current, electricity and magnetism. So be quick, be quick, don't waste your time, take some rest of 5, I mean you won't be able to take some rest, but have some dinner and then come back immediately, right? So quickly write down in the chat box, are you going to come back? We are going to start current, electricity after this. We are going to start current, electricity after this, and again I am not going to leave derivation, the important, I am going to derive the important derivations over here as well, right, of all the drift velocity and all the things. Are you getting it? Is it all good? Clear? All right, all right, all right. Done. Okay, so we'll meet you in, how much time do you want? We'll meet you in 15 minutes. That would be correct? All right. Welcome back. Welcome back, friends. How many of you are still here? Quickly write down in the chat box. Hi, welcome back, welcome back. So now we are going to start current electricity. And remember, when we are going to talk about magnetism, the half portion of magnetism is much similar to electrostatics. So keep a note of that. Hi Kevin, hi, welcome back. Hi Kirti, hi. Hi Vimlesh, hi Anupama, hi Rana, hi everyone, hi. So now let's, without any delay, let's talk about current electricity. Very good chapter, quite easy. Some of numericals which are a little bit on a difficult end, we are going to do that in today's class, right? Hi Shavi, hi everyone. So let's start. First of all, when we are going to talk about current electricity, obviously we are going to define what do we mean by current. Is that correct? So for current, the definition is, most of you know it, it is basically the rate of transfer of charges, right? Rate of transfer of charges. And whenever we are going to talk about any rate, we are going to always define it as an average rate and an instantaneous rate. So average rate will be defined as del Q by del T, right? And instantaneous rate will be defined as, let's suppose this del T time is tending to 0. It is infinitely small, right? So average current is going to be it is equals to del Q by del T when del T is tending to 0. Is that correct? So hopefully you might come across some questions from this, like for example they might give you that the charge is actually flowing according to the equation something like this, let's say 2t square plus 2t plus 1, and you have to find out the current after 1 second, after 3 seconds and so on, right? So just differentiate it, substitute the value, find out the current. Or if they say that they have given you a particular value of current, or a particular equation of current, they are telling you to find out the charge. So to find out the charge, you will actually integrate the equation of current with respect to time. Is that correct? Quickly tell me in the chat box. Is it all good? Quick. So this is actually quite simple. Current is actually a scalar quantity and one of the fundamental physical quantity, right? So its dimensional formula is going to be I to the power 1, right? Other than that, SI unit is actually ampere, that is Coulomb per second. Basic things about current is quite easy. We are going to move to some of the more complex things. The direction of current is opposite to the direction of flow of electrons. This is something that you must have learned in grade 10th, I think, right? That at the time of when all of these things were happening, that scientists were talking about current, electrons were not discovered back then, right? So the direction of current is opposite to the direction of flow of electrons. This is again because of a convention, right? There is no solid reason behind it. Alright, moving on, everything we have covered it. Although current is actually a scalar quantity, right? But we have got one more thing which is actually not a scalar quantity, that is a vector quantity. That is actually known as current density, which is actually denoted by vector J. It is denoted by vector J, and it is actually current per unit area. It is actually current per unit area. So this area is actually the normal area that we are talking about. Right? And also you can, after this you can actually say that current can be actually written as J dot A. Of course, let me explain what do we really mean by current density. So by meaning of current density, we basically mean that let's suppose we have got a wire something like this, and after a certain point the width of this wire becomes really thin, something like this. So right now the current is at this particular point, it is 2 ampere. If you are going to talk about current at this particular point, still it is 2 ampere, right? But the only difference is in the current density. The current density has increased at this particular point. So if I am going to talk about an area something like this, right, over here. So whenever I am talking about an area, I am going to also define an area vector, right? So current density will be actually written as current per unit normal area. Is that correct? Everything's clear till here? Right? So current does not depend on area, but current density does, right? So this is actually very important, that current density does depend upon the area. So it is nothing but it is current per unit normal area. It is a vector quantity. After this we are going to actually move on and we are going to actually discuss an important concept of drift velocity. Now this is actually one of the first important topic of current electricity, right? That is drift velocity. So now please pay attention and understand this topic. Drift velocity. Now before starting or before defining what drift velocity is, let's first look at a conductor, right? Let's suppose that we have got a metallic surface over here, we have got a metallic conductor at this particular point, and it has got like various, you know that it has got free electrons, and these free electrons are moving in random directions, right, with very high speed, by the way. Hopefully you are getting it. This is at room temperature and no external electric field has been applied. So please make a note of it, that right now there is no external electric field, right? And that is why these electrons, which are actually the loosely bound electrons, and I am going to give you I am going to break it down from, that's why I am starting from when there is no electric field, right? So let's start it from here. So right now there is no electric field. So how why electrons are moving? They are moving because of the thermal energy that they are getting from the room temperature, right? And this type of motion is actually completely random, a complete random motion with very high velocity, high speed. All right, done. After this, the next point is that now we are actually applying external electric field after some time. So after some time we are applying external electric field, and the external electric field has been applied something like this. Let's suppose that we have an external electric field in this direction. In this direction we have got external electric field, right? Now the electrons which were moving, let's suppose this, let's talk about this electron, dosto. This electron was moving in this direction. Now suddenly a force is acting on it in this direction. And this force is actually the electric force, right? QE. Similarly, on every charge, this force is going to act, right? Got it? Because of this, these electrons are going to change their path by a bit. So this electron, instead of moving in this path, this electron is going to move something like this. So this was the initial path of this electron, right? Now instead of moving in this direction, this electron is going to move in this direction, right? Similarly, every electron is going to drift in this direction. Why we are using the term drift, I am going to let you know. So what really happens? Understand what really happens when this electron moves. It actually, after some time, it collides with another electron. another electron or another what we call as the lattice, that the high mass positive ion, right, that's what we call as lattice. Other than the free electrons, there are also positive ions, right, fixed positive ions. So these ions, these electrons actually gets collide with another particles, and that's how we actually say when you apply an electric field, some part of energy is also gets into the heat energy because of all of these collisions, right. So but the true fact is that these electrons really move in this direction, so they drift in this direction, right. It's not like all the electrons are going to start moving in this direction. They are drifting towards this direction because certainly a force has started to act on it. So this again, this force is going to move, this charge is going to move in this direction, this charge is going to move in this direction, this charge will actually, it will stay on this path, and they will collide. After some time they will collide with another particles, right. Hopefully you are getting it what I am trying to say. Then I am going to say the average of the velocities of these electrons after applying the electric field. The average velocities of these electrons is called as drift velocities, right. Again, let me explain it. The average velocities of all of these electrons after applying the electric field is known as drift velocity. Now the drift velocity has come really down. Initially, when there was no electric field, they were moving with they were moving in random direction, but with very high speed. Now they are moving in one particular direction but very less speed. The reason is because of frequent collisions, because now every particle is moving in one direction. Are you getting it? I am not saying they are moving in a straight line or a straight path. They are moving towards this path, this side, right. Alright, hopefully this thing is clear. Now we are going to actually use a little bit of kinematics, and before using this kinematics, I am going to give you what we can say a little bit of caution. That caution is that all of these things, again we are learning it on a macroscopic level. These things are more complex than using a kinematics, but still up to our level we can actually use these kinematics equation. And then how to use it, let's see. After applying electric field, what is the force on one electron? What is the force on electron? So the force is, obviously you are going to say, so the force is actually equals to, the magnitude is at least E times E. This basically means that acceleration acting on an electron will be E times E divided by m. Is that correct? Right? Is that correct? E times E divided by m, and if you are going to write the negative sign also, you can write it. For if you are using the vector, if you are using, I just written magnitude. So now let's suppose that I am using the kinematics equation for n number of electrons. So now I am going to write, for the first electron I am going to write V1 equals to U1 plus A1 times T1. Now let me explain each thing for you. U1 is the initial velocity, that means over here, right. So this is the t equals to 0 when there was no electric field. So U1 is, let's suppose we are talking about this. So this thing is U1 dosto, right. U1 is the initial velocity of the first electron. There are many electrons, but it is just first electrons, right. My friend, I cannot use Hindi language because this is an English medium channel, right. Got it? Then next thing is, let's talk about another electron. So by the way, sorry. So U1 is the initial velocity, and after electric field is applied, now acceleration is acting on it, right. If acceleration is acting on it, that means after time t1 it will have velocity v1 and it will get collide with some another particle. So this is the most important thing, that after time t1 this first electron gets collide with some another particle. So let's write it for some another electrons as well. So let's write it for v2. So for v2 I am going to write it as u2 plus a2 into t2, and so on. I am going to write it for n electrons, un plus an times tn, right. Let's add them and take an average of these values, right. So if I am going to add all of these values, I'll have v1 plus v2 so on vn whole divided by n
right, equals to, I'll also add them and take an average of it. Well, taking an average basically means just divide them by n, right? So it's nothing like we have done anything wrong as far as maths is concerned. Whole divided by n again. Well, sometimes you might see that in some of the books they use second equation also, right? So this one is also holds good. Plus every electron will have this acceleration only. So acceleration is constant for every electron. Acceleration doesn't change, right? So we are going to say now, I'm going to remove this thing from here so that I can write. So plus, and by the way, I'll use the negative sign because I'm using vectors, minus EE by m. Hopefully you can see that this is actually, and then again I'll write T1 plus T2 plus Tn whole divided by n. Now after this we are going to use one or two things, so please understand. First of all, tell me, is everything clear up till here? Quickly write down in the chat box if everything's clear till this point. Quick. Everything's clear till this point? Can we move ahead? Quick. All right, good. If no, then please ask your doubt. If no, then please ask your doubt. After this, let's look at this vector sum, that is u1 plus u2 and so on and plus un, right? Got it? u1 plus u2 plus u3 plus un. Look at the vector sum of all of these quantities. First of all, what were these u1 plus u2 plus un? This was the initial velocities of those electrons when there was no electric field, right? And at that particular point, if you remember, they were moving at random directions. Now we are going to say that if they are moving at random directions, then if a particular electron, see the logic behind this. If a particular electron is moving in this direction, there must, we can say safely that there must exist an electron which is moving exactly opposite to that, right? That is exactly moving opposite to that. So if an electron is moving in this direction, there must exist an electron which is exactly moving to opposite to that electron, because it is moving, because they all are moving in random directions, right? Having said that, we can say that therefore the vector sum of all of these quantities is going to be 0. The reason is that they are moving in completely random direction. Got it? Next is, this is what I was talking about, that this is what the drift velocity is, that the average of all the velocities. So this is the drift velocity equals to, this is minus E by m, and the average of all the times is known as relaxation time, that is tau. So this is the formula for drift velocity. Now please understand. Again, hopefully you have understood that what do we really mean by E, capital E, m. This is all good. What is this tau? This is actually the average of T1, T2, T3. What was T1? Time taken by this was the time to travel the mean free path for the first electron. That means after T1 time the first electron gets collided. After T2 time the second electron gets collided. After T3 time the third electron gets collided. So what is the average time between two collisions? That is tau. This is tau. So this is known as relaxation time. Relaxation time, that is average time between two collisions. Average time between two collisions. Alright, this is the average time between two collisions. So this is your formula for drift velocity, a very important formula. We are going to use it quite often, so please remember it, right? You are going to come across many questions in which you are going to use this. After this, let's move to the next important topic, that is relation between current and drift velocities, right? Although the relation is actually, even if I don't derive it, we can move away, but I'll explain it to you. Let's suppose that we have got a wire in the cylindrical shape, and the area of this cross section is A. Area is A, right? Just hear me out. Everything I am going to explain it to you. The length is L, right? N is the number of electrons per meter cube. That means in 1 meter cube there are n number of electrons. Got it? Done? In 1 meter cube there are n number of electrons, and let's suppose that here is the positive potential, here is the negative potential. That means electric field is in this direction. So electrons are going to drift in this way, in this direction, with let's say drift velocity Vd. Now I can draw a diagram like this and I can say drift velocity Vd, but you must understand it that that's not how it happens, right? The previous diagram that I drew was actually the correct diagram. Are you getting it? Hopefully everything's clear, right? After this, let's say the length is L. We have written everything for you. We know that current can be actually written as the amount of charge that has been transferred in del t time. Now what is the total amount of charge, dosto? Total amount of charge would be, in 1 meter cube there is n number of electrons in 1 meter cube. So what is the volume of this entire cylinder? The entire cylinder has volume equals to A into L. So A into L. If we are going to multiply n with it, we are going to get the total number of electrons multiplied by E. So this is the total number of charge that we have got, divided by del T. What is the time taken by these electrons to go from this point to this point? So time is just going to be L divided by drift velocity. So L can be cancelled out, and that's how easy the derivation is, and this is going to be NEA Vd. A very important relation, please understand it. This is the NEA Vd kind of relation between current and drift velocity, right? Please, again, I is current, N is number of electrons in 1 meter cube. That means number of electrons per unit volume. E is charge of electron, A is area of cross section of the wire that we are talking about. Vd is the drift velocity, right? Got it? Next is, let's actually derive, and let's see if we have got another. The conductor remains uncharged when the current flows through it, because the charge entering one end. So this is actually a note, a simple note, right? A simple note in which they are saying that a conductor will remain uncharged even if the electrons are flowing, right? So this is very important. We are going to do Kirchhoff's law, so don't worry about it. We are going to do it. I'm going to teach that in today's class only, right? After this, when we are going to talk about the Ohm's law, right? Let's talk about the Ohm's law using these two formulas. So till now we have discussed that Vd, drift velocity's formula is EE tau by m, and right now I am not writing minus sign because I don't have to, right? EE tau by m. So this is one of the formula. The another formula is I equals to NEA Vd. NEA Vd. This is the another formula, right? By the way, this was from your grade 10th that you have learned this thing, that V is directly proportional to I. Under constant physical condition, voltage is directly proportional to current, and current can be actually written as V by R. Current can be written as V by R. So we have some relation for current over here. Let's just put the values for the drift velocity in this formula. Let's figure it out. What answer are we getting? Let's see. Come here. So I'll write current equals to NEA. Instead of Vd, let me just put the value, that is EE tau by m, right? So current will be, now please see, we have got NE square, right? NE square A tau by M. And दोस्तों instead of electric field, can I write again, because electric field right now is also uniform across that conductor, instead of electric field can I write potential times potential divided by length, right? Can I write it like that? So I'll write potential V, that is the potential difference divided by length, right? This is actually one of the most important relations, because after this almost we have covered it. If you remember, resistance was written as rho L by A, if you remember it, right? Resistance was written as rho L by A, and if you are going to closely see this is now quite easy. I have written as current equals to voltage, and anything that is in the denominator, that is the resistance. Isn't it correct? Isn't it correct? I have written current equals to voltage, and whatever is in the denominator, that is nothing but that is resistance. So write everything that is in the denominator, that is M times L whole divided by NE square tau by A. So this whole thing is nothing but this is resistance. So we have found out the value of resistance, and by the way, this is actually the Ohm's law. This is actually the Ohm's law. How? I'll explain it. Let's suppose this is the wire that I am talking about. This is the wire that I am talking about. So for this wire, length is constant, area of cross section is constant, the number of electrons per meter cube is constant, right? So please see, N is constant, E is charge of electron, that is constant, A is area of wire, area of cross section of wire, that is constant, tau is basically relaxation time. Now whenever we quote Ohm's law, we always say under same physical conditions. That means we are not changing temperature. So it means that if we are not changing temperature, then tau will also remain same, right? M is mass of one electron, that will also remain same. L is length of the conductor, that will also remain same. It means that I is equals to a constant times voltage. That means for a given conductor and under same physical conditions, voltage is directly proportional to current. That's what the Ohm's law is, right? After that, just we are going to write that R can be written as M into L divided by NE square tau by A. So this is the relation for resistance. And moreover, if you are going to talk about what is resistivity, so resistivity is going to be just M divided by NE square into tau. So this is actually now again very, very important. Quickly tell me if everything's clear. Quick. Quick. How many of you are still present from batch? Is it all good? We are going to use these relations to actually answer some of the questions. Like for example, is if you are going to increase temperature, what will happen? If you are going to increase temperature for a conductor, right? If let's say for a conductor, we have found out that rho is actually M divided by NE square tau. M, we have found it out, M divided by NE square by tau, NE square tau. This is what rho is, right? Now see, if we are talking about a metallic conductor, clear, very good, good. All right. We are going to start the poles, don't worry, we are going to start the poles. If we are going to talk about a metallic conductor, for a metallic conductor, see what happens. If you increase temperature, then relaxation time will go down. Well, we really can't comment on the relation how it goes down, but I'll write it something like this. If you increase the temperature, this will actually drop down the relaxation time. Why that will happen? The reason is that if you are going to increase the temperature, because of increase in thermal energy, the particles will collide, and they will collide more often than they were colliding before, right? So the relaxation time, which was actually the time taken by the particle for the mean free path, it will get reduced now, because they are now colliding more often. So tau goes down. If tau goes down, we are going to imply that using this relation that resistivity is inversely dependent on tau, resistivity will go up. So this is the point that if you are going to increase the temperature of a conductor, it will become a bad conductor, right? It will become a bad conductor. Alright, got it? Done? Well, this is not same for semiconductors. For now, just remember this, that this is not same for a semiconductor. Reason being, this statement still holds good for semiconductor, but for semiconductor n changes, right? But that's part for next chapter. We are not going to go to that till right now, right? Right now, let's just say that for conductor, if you increase temperature, resistivity goes up. After this, I think we have almost done everything. Limitations of Ohm's law. This is actually the graph of semiconductors that I was talking about, right? So when we are going to complete semiconductors, or when you are going to study semiconductors, this is what you are going to see. This basically shows that voltage is not always proportional to current, right? Also, in somewhere over here, this was the region where the voltage and current is actually directly proportional. After it, this is a non-linear region, and this is a negative resistance region. So this is also something that in this we say that Ohm's law is not applicable, right? So there exist some materials and devices used in electrical circuits where the proportionality and V and I does not hold. The deviations broadly are one of more types. First one is for semiconductor, and this one is for diodes, right? So this is actually very, very important. Alright, dosto. So after this, to explain this temperature dependence of resistivity on temperature, we have got actually a formula which is actually something like this. So this is the formula which you might have seen it before as well, which is actually rho t equals to rho naught times 1 plus alpha times delta t. This is not that difficult to understand. Let's suppose at temperature T naught, this is the initial temperature. At temperature T naught, the resistivity is rho naught. And at temperature T, we want to find out what is the new resistivity, right? So the formula goes something like rho equals to rho naught. So this is that resistivity at temperature T, right? Times 1 plus alpha times delta T. So delta T is the change in temperature and alpha is the temperature coefficient. It basically means that what is going to be the change in rho if you are going to increase the temperature by 1 degree Celsius, right? So after this, yeah. So the resistivity of the material is dependent on temperature over limited range of temperatures, and the formula is something like this. Rho T is the resistivity at temperature capital T. Rho naught was the initial resistivity, right? Here alpha is called the temperature coefficient of resistivity, and its unit is 1 upon degree Celsius. And please remember, these dimensional formulas are quite important. Why? Because usually the easier dimensional formulas are quite easy to understand. For what if you are going to talk about resistivity and all, these are actually quite important and not that difficult to understand, right? Hopefully everything is clear. Can we move on? Can we move on to some new topics? Hopefully resistance in series and parallel is actually quite easy, so I am not going to waste your time in that. Rated power and rated potential is a topic in on which actually lots of questions comes, and still some of students have doubt in these things. When we say rated power and rated potential, the best way to understand this topic is, let's suppose that we have got a bulb which was manufactured at let's say we have got a bulb which was manufactured at a factory, and when it was manufactured in such a way that it will actually consume, it will actually require 220 volt of potential. And if you give this bulb 220 volt of potential, it will actually consume a power of, let's say, 50 watt. So these are rated power and rated potential, right? No ohmic resistance are those resistance which do not which do not follow the linear curve, right? So when we are talking about rated power and rated potential, that's what we mean, that if you are going to supply this, if you are going to actually apply 220 volt of potential to this bulb will actually consumes 50 joules of energy per second, right? This is what rated power is, this is what rated what we can say rated power and rated potential is. This is absolutely correct, that this is actually this is being written on the bulb, or the bulbs are manufactured in such a way because so that they don't, you don't run those devices or run those bulbs above the rated voltage, else they'll malfunction obviously, right? They'll get destroyed. So using these two relations, we are going to actually say, we already know that power can be actually written as V square by R, right? So rated power can be written as VR square by R. So from this we can find out actually the resistance, that this is what the use of these two things. We can find out the resistance, and after this, whenever whatever they say, that let's suppose that now we have applied, we have not given it as a 220 volt, but we have given it as 110 volt. So what is going to be the power consumed? So first of all, from this information find out what the resistance is. So resistance is going to be square of 220 divided by 50. So this is what resistance is. Now if you want to find out the power, again use V square, that is 110 divided by R, right, divided by R, and R is 220 times 220 times 5. Is that correct? So this is going to be 2, this is going to be 2, so the answer is 5 by 4 watt. Have we done anything wrong? Everything's clear? Right. Is it all good? By the way, this is 50, sorry, so this is going to be 50 by 4. Good, clear? See, this is the thing, over here you can't use VI, over here you can use any formula. You can first find out the current, then you can find out the power, but how you are going to do it? First you will find out resistance from this equation, then you are going to use it over here, that's it. Is that correct? Clear? So this is the only case for rated power and rated potential, nothing else. So it's not a big deal. Hopefully everything's clear. Okay, good. Very good. Next is EMF of a cell, right? Now when we are going to actually talk about EMF of a cell, what do we really mean by it? Let's break it down, because again you are going to use it, in many cases. When you see a battery, right, whenever you see a cell or a battery, let's suppose you see a cell something like this, and they write that it has got EMF as E, and the current in it is flowing as whatever the current is, it is flowing, right? Let's just assume that right now the EMF is E. That's what we actually need to define, that what do we really mean by EMF, right? Hi. So right now this cell is actually, in reality it would be looking something like this, and it must have some electrodes, like positive electrodes and negative electrodes, right? So the most basic definition for EMF would be, it is the potential difference between the electrodes of this cell, right? Potential difference between the electrodes of this cell. Or what you can say is that EMF is the potential difference across this battery or a cell when there is no current flowing in the circuit. When there is no current flowing in the circuit. What's the reason behind it? Because when the current will flow in the circuit, there is going to be internal resistance, right? And because of that internal resistance, there will be a potential drop, a very small but significant potential drop inside the cell only. So that's why EMF is not equals to the potential difference across the cell when current is flowing in the circuit. Are you getting it what I am trying to say? So let's suppose we are saying that we have got a battery, we have got a circuit something like this. We have got a circuit, and over here we have got a resistance R, and we have got a battery whose EMF is E, right? Now if I'll ask you that what is the potential difference across this resistance? So you are going to say that let's say the potential difference across this resistance is V, and let's say the current flowing in the circuit is I, right? So that would be actually that would be V would be actually equals to E, but not just E, it is actually E minus I into the potential drop in because of this internal resistance. And let's say that internal resistance, we are saying it using a letter small r. So I am going to say this is the value of potential difference across the cell or a battery, right? And that's why we are going to write EMF is V plus IR. And now you can actually see that when I defined it, that EMF of a battery or a cell is equals to the potential difference across the cell when no current is flowing through it. So when I is 0, then V will be equals to E. But when there will be current flowing into the circuit, then we can't say that E is actually equals to V. There is going to be certain potential drop in the cell only because of internal resistance. Quickly write down in the chat box if this concept is clear to all of you. Then I have got some notes on this one. EMF is defined as the potential difference between the electrodes when there is no current in the cell, right? Cell is in open circuit. The electrolyte through which a current flows has a finite resistance are called internal resistance, right? The maximum current that can be drawn from the cell for R equals to 0 is I max, that is E by R. Quite easy dosto. So let's suppose that this R is actually equals to 0. So what is the total resistance in the circuit? So total resistance in the circuit is just small r. So maximum current that can pass through this circuit is actually E divided by R. That's it. Alright, clear? Done? EMFs of the cell. So we have done the last point is that in practical calculations, internal resistance of the cell in the circuits may be neglected when the current I is such that E is far more greater than IR. So in all of those problems in which you don't consider internal resistance, the reason might be that E is far more greater than IR. Alright. So this is the reason. So after this, I think now all the things that we are going to do is pretty much same. First let's complete the Kirchhoff's law, then we'll talk about that cell series and cell parallel. First let's complete Kirchhoff's laws, right? Now the first law says, when we are going to talk about Kirchhoff's junction law, first of all it is based on conservation of charge, right? What does Kirchhoff's first law says? Kirchhoff's first law says that if you have got like different wires and they are getting connected or they are meeting at a point, something like this. So first of all, this point will be called as a junction. This point will be called as a junction. And let's say we have got like different currents over here like I1, I2, I3, I4 and I5. So according to conservation of charge, we can say that the amount of current entering, that is the summation of incoming current will be actually equals to the summation of the outgoing current. So according to this, incoming current is I1 plus I2. And that will be actually equals to, and by the way I4 is also incoming, so plus I4, and that will be actually equals to I3 plus I5. So this is because of conservation of charge. That means the total amount of charge that is entering. What is current? Current is rate of flow of charge, right? So whatever the total amount of charge that is entering, it will be equals to the amount of charge that will going out of the junction, right? Conservation of charge. Everything's clear till here? Quickly write down in the chat box. Quick. So some points about this. It states that at the junction, sum of current entering the junction is equals to the sum of current leaving the junction. Junction is any point in the circuit. From the standard point of physics, KCL is a statement of charge conservation. This is just for the charge conservations, right? We are going to talk about quotient. Just now we are going to talk about quotients, and for junctions law, I can actually explain one particular question, but I'll explain it after 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 KVL, Kirchhoff's loop law. After that, right? Got it? Now for Kirchhoff's second law, now this law is based on conservation of energy. Right? What does this law says? This law says that the algebraic sum of the potential difference around any closed loop in an electrical circuit is 0. Right? It means that, let's suppose that we have got an electrical circuit something like this. So we have got R1, got R2, we have got a battery, we have got another battery. Let's say this is E1, this is E2, right? And the current flowing in the circuit is I. So the potential difference, the sum of potential difference across each of these what we can say elements, if you are going to take the sum of this along a closed loop, that will come out to be 0, right? And for this we will first have to find out the sign convention, and for sign convention let me just explain it to you. After this applying KCL will be much more easier. Sign convention, right? Now this is again, this is based on your what you want to do it, how you want to do it. It's not like a rule or anything, right? So how I always teach this topic is, let's suppose that you are moving through a battery. First let's talk about a battery. You are moving through a battery and also you have got a resistance like this. Resistance is R, battery is E, and the internal, the current is flowing is I, right? Right now the current is flowing something like this. That means the battery is getting charged, right? So if we want to write out the potential difference from point A to point B, and let's imagine that we have a closed loop like this. So first let's write the potential A, then let's move on, and my sign convention is that whenever there is a potential drop, you write it with a negative sign. It's quite easy to understand, right? It's quite easy to understand. Whenever you have a potential drop, you write it with a negative sign. Whenever you have got potential gain, you write it with a positive sign. That's how easy it is, right? So according to this, what we are going to do is, when you are going to actually go from a positive terminal to a negative terminal, there is going to be a potential drop. So whenever there is a potential drop, write it with a negative sign. That's it. So if you are moving from B to A, right now I am going from A to B. So this is actually important to say that right now we are reading these values from A to B. So VA, then pause from positive to negative, that means minus E. Again then we'll pass through the resistance. Now please see what will happen. When you are going to pass through the resistance is going to consume some of the potential. So again there is going to be a potential drop, and the value of that potential drop is going to be minus I into R, and then you will reach back to your point B. Are you getting it? And this is actually the same thing. So I'll write it as E equals to VB. Alright, are you getting it? Are you getting it what I am trying to say? So whenever there is a potential drop, write it with a negative sign. Whenever there is a potential gain, write it with a, and sorry, this I will write it as plus VB only, equals to 0. Done? Everything's clear? So in reality, if you are going to say that, okay, so see these 2 points are actually same, so we can just write that the potential difference between these 2 points is minus E minus IR. And now if you are going to go from B to A, then you are going to go from this in this direction, then see what you will write. The current is passing through the resistance in this direction, and you are actually going from B to A. So according to you, it's not potential drop, it's actually potential gain. Are you getting it what I am trying to say? Right? So from this point I am going to write it as plus IR, because now it is a potential gain. At this particular point the potential was less than this point, right? And then again I am going from minus I to plus I, so I am going to write as plus E. So this is how I am going to write for the next case, right. After this, let me define both laws using an equation, using a quotient, right. That would be the best thing to do. And I'll just write the equation for you and you find out whatever the values is, right. So this is actually one of the famous questions for board exams that we usually see, right. Now see, what is the first thing that you need to do. Sometimes what will happen is you will get the currents already drawn in your question. Sometimes you will have to draw it. So the first step is to follow the Kirchhoff's current law. That is how to actually mark the currents. Now see how I am doing it. I am just assuming that I have got a current I1 over here. And see, I am not using any particular rule. I am saying that current I1 is flowing in this direction. Let's just assume. So current I1 is flowing in this direction. I1 or I, whatever you want to consider. The only thing is, try to reduce the number of variables, right. The number of variables that will be in your what you can say in your equation or in your this figure, the number of equations you will need to solve that is the mathematical problem, right. So let's say the current is I. At this particular point, here is the junction. Now I really don't know is really the current is flowing in this direction or not. I have assumed it. When we will solve it, if my assumption is wrong, let's suppose my answer is coming, the I is coming as 10 ampere or my answer is coming as minus 10 ampere. So it means that 10 ampere is good, but the direction is like this. That's it, right. At this particular point, what will happen? So I was assuming that I current is coming like this. So at this particular point, let's suppose that one of the current goes in this direction and the another amount of current will go in this direction. So let's suppose at this particular point, I1 current goes in this direction. So according to Kirchhoff's current law, the remaining current will go in this direction. So the total current was I. Out of it, I1 goes in this direction. So the remaining current, that is I minus I1, goes in this direction. So according to this, we have only used two variables, that is I and I1. Are you getting it what I am trying to say? Got it? Everything's clear till here, right? Now, how many loops do I have got over here? How many loops do I have got? Do I have got 2 loops or 3 loops? Well, we have got 3 loops. One is actually, you can consider this thing as a loop. That is this one as a loop. You can consider this one as a loop. And you can also consider this one as a loop, that 𝐒𝐴 BFE. This one is also a loop. So the first step was to correctly write down the current values. After this, let's quickly write down the loop rule. I am choosing the first loop just to write down the equations. Okay. So loop 1 and the loop's name I am going to use is ED C F and coming back to E. Right. So let's also start from E. Let's go at this point. There is nothing, there is no resistance, there is nothing. So we don't have to worry about, right. After this, let's go in this direction. We have got resistance of 40 ohm and we are moving along the direction of current. Got it? We are moving along the direction of current. That means there is going to be potential drop. So according to my sign convention, I am going to write it with a negative sign. Are you following it what I am trying to say? You are moving along the current direction. So I am going to write it something like minus 40 times I minus I1. Done. Let's come back over here. In this whole of this wire, I current was flowing, right. So over here as well, the current was flowing as I. So you don't have to worry about. I current was flowing. Again, you are moving along the direction of current and it is moving through 10 ampere, sorry 10 ohm. So we are going to write as minus 10 into I. Then again, we are going to go from negative terminal to positive terminal. So we are going to write it as plus 40. And since we have reached back to the same point, equals to 0, this is the equation number 1. Are you getting it? quick दोस्तों, is it all good? Is it all good? Let's talk about another loop. Let's talk about loop 2. We only need 2 loops because we only have 2 unknowns, I and I1, right? So for loop 2, let's name that loop as A, B, C, D, A, right? Again, let's go from A. According to my sign convention, you are moving from negative terminal to positive terminal, so there is a potential gain. So let's write it with a positive sign, that is 80 volt. Then in this wire, I1 current is flowing, passing through 20 ohm. So again potential drops, so minus 20 I1. Coming back, now see, this is will clear your doubts. You are coming back and you are moving in this direction, and current is moving in this direction, right? So this point has got a higher potential as compared to this point. Are you following it? Because whenever current passes through a resistance, there is a potential drop, right? So when we are going to read this, we are going to write it as plus 40 I minus I1, and then again we have reached back to the same point, so equals to 0. So this is how we are going to write the two equations. Now I hope you can easily actually find out the answers of I and I1 using these two equations. Are you getting it? Quickly tell me in the chat box. Everything's fine? Quick दोस्तों. This was just to show you that how to use sign conventions, right? How to use sign conventions. So this was my way. Well, again, if you are going to completely change the signs, if you are going to say no sir, I am going to actually use potential drop as positive and potential gain as negative, it won't make any change. It is just maths, right? You are going to just multiply negative sign to both the direction. It won't make any change. So after this, I've got one more question like this, but let's solve some another questions first. This one is quite easy, but let's go. I want you to solve some more. Quick, let's do this one in polls. 90 seconds would be more than sufficient. Quickly find out the answer. Find out the answer quick. Please, last step once again. Okay, after this, after this. Is it good? So we have got 2 and 2, and this is a junction. So this is going to be definitely 4. This is another junction. This is 1. So this is going to be 3. Is that correct, my friends? This is 1.3. So this is going to be 1.7. This was an easy one, right? Now tell me what doubt you have got in this one. I'll again explain it. In the last step you are talking about, in the last step what I said is that the current is moving from C to D, and we are reading the potential differences from C to D, and the current is moving from D to C, right? So according to that, I am going to say that if current is moving in this direction, there is going to be a potential gain for us, right? Is that correct? Because this point is actually at the higher potential as compared to this point. That's what I was saying. Correct? Absolutely correct. Can we move on? So we have got one more question, something like this. So this, you can take this as homework, but I'll again write the equations for you in this one as well, right? We'll again use 2 currents only. There's only need of 2 currents. So what I'll do is, I'll actually say to you that let's suppose we have got I1 current in this direction, right, and I2 current in this direction. So in this direction we will have I1 plus I2. Alright, got it? So according to this, now let us say that this is loop 1 and this is loop 2. So again let us write the equations over here. So loop 1 I am just writing it, loop 1 I am writing the name as DA BD, DABD, right. So from D I am assuming that I1 current is flowing. Now please understand, along this line I1 current will flow. Is that correct? Along this line I1 current will flow. So it means that we have got also internal resistance. So first of all 1 ampere, 1 ohm of resistance is there. So it will be minus I1, sorry, minus I1 and plus 1 volt. Why plus 1 volt? Because again you are going from positive negative terminal to positive terminal. So there is a potential gain, right? Again now going on from positive terminal to negative terminal, so minus 2 volt and minus 2 I1. Then coming back to this one, so this is again potential drop, so minus 2 I1 plus I2 and equals to 0, right. Then loop 2 is actually loop 2, let us consider it as DB CD. So for loop 2 again we are going to go from D to B, so this will be plus 2 I1 plus I2, right, and then plus 1 volt minus I2 into 1 and then plus, sorry not plus, minus 3 volt and minus 3 plus 3 I2 is equals to 0. Tell me in the chat box if you have got any doubt. Tell me. In just writing the equations, you can just solve it by your own. In writing these equations, if you have any doubt, tell me, else we will move on. Quick. Quick. No more doubts. All right. Great. In that case, let's do one more question for current electricity. Then let's start a new chapter, that is moving charges and magnetism. Right? Let's do one more question and write down the answer in the chat box. Quickly. Let's write down the answer in the chat box. Giving you 2 minutes of time. Write down the answer in the chat box. By the way, we were supposed to answer this. What was this question? Okay, just a second. Let me check. This was 1.7, right? So A was correct. Okay, great. 75% of you have got correct. Good. So this is the next question. Let's see if we can actually. This is actually an integer type, right? 90 seconds. Solve it, dosto. Quickly solve it. You have got the answer. So 2 ampere of current flows in this conductor as shown. Okay. So see, if 2 ampere of current flows, 5 ohm of resistance is over here, 5 ohm of resistance is over here, right? Is that correct? This means that you must remember it, that current chooses the least resistive path. But if resistance is same on both the sides, on both of these branches, then current is going to distribute equally. So that means 1 ampere of current flows through this part and 1 ampere of current flows through this part. 1 ampere and 1 ampere, right? Now let's say that potential difference at the potential at this point is D. So I am going to write VD minus VA equals to 1 ampere into 2 ohm. Is that correct? And for the next one I am going to write VD minus VB equals to 1 ampere into 3. And we need to actually find VA minus VB. Is that correct, dosto? So this is the equation 1. So rewrite the equation 1 over here. So VD minus VA equals to 2. So this is equation 1. This is equation 2. Just subtract them. So this will get cancelled out. This will become VA minus VB equals to, again this is 3 minus 2, that is 1 volt. So 1 volt is the correct answer. Is that correct? Quickly tell me in the chat box, is that correct? Right? Alright, so 1 is the correct answer. Is it all good? Quickly write down in the chat box. Why? Why no one has got it correct? Tell me. Now is it clear? Quickly tell me in the chat box, is it clear now? Then we are going to move to the new chapter, that is moving charges and magnetism. See, we have done nothing, we have just used Ohm's law. There is nothing about it, right? We have just used Ohm's law. VD minus VA is just 2 into 1 ampere, VD minus VB is just 3 into 1 ampere, that's it, right? Now let's start another chapter, that is moving charges and magnetism. Now before starting this chapter, let me first give you an idea why we are learning this chapter and what has actually made us to learn this as another chapter, right? Why we are talking about moving charges and why we are talking about magnetism, what it is about. The thing is, if let's suppose I've got a current carrying conductor over here and it has got current I, right? You must have gone through that Orested experiment that we have done in what we can say in grade 10th, right? You might have seen that experiment, that a compass was kept in close to a circuit, and when the current was flowing through the circuit, the compass shows some deflection. Quite similar to that, we are talking something. So let's suppose we have got a charge and the charge is at rest. So what difference are you going to observe? What will happen to this charge which is at rest? The answer is nothing will happen. The charge will remain at rest, right? Nothing will happen to this charge. Current will flow, the charge will remain at rest. You are going to observe no difference. But as soon as you are going to give this charge velocity, and let's say you give this charge a velocity of v, then you are going to notice that instead of going into the straight path, something like this, which it should have, the particle actually turned like something like this. That means a moving charge in presence of a current carrying conductor changed its path, right? What does it mean? So if velocity is changing, that means there must be an acceleration acting on the charged particle. It means that there must be a force acting on the charged particle. This is what we are calling moving charge in a magnetic field, right? So the first concept that we are going to learn, one of the first concept that we are going to learn in this chapter is going to be this. Moving charges or current produces a magnetic field in the surrounding space. So this is the most important thing, that not only naturally occurring magnets, but moving charges and currents also produces the magnetic field, right? Magnetic field exerts force on moving charged particles like electrons, protons and current carrying wires. And this is because the charged particle actually change its direction, right? After this, the region surrounding a moving charge in which its magnetic fields are perceptible on a moving charge, right? So this is what a magnetic field is going to be. Magnetic field intensity is a vector quantity and also known as magnetic induction. What are its SI unit? Weber per meter square, and I am going to explain all of these to you. But first of all, let me explain how we are going to actually read magnetic field intensity. So we are talking about magnetic field intensity, which is generally denoted by vector B, right? And I'll tell you why we actually use some of the units that we have just seen in the last slide. When we are talking about magnetic field intensity, again the definition is going to be similar to what we have learned about the electric field. I have told you this chapter is quite similar to the electric field chapter, right, or the whole of electrostatics. Now when we are talking about magnetic field intensities, we are going to talk about two things. One is the magnitude of magnetic field, and the another thing is the direction. The direction of magnetic field, right? For magnitude, we have got actually two laws for it. We have got two, I mean, not like just like magnitude, but for magnitude as well as direction, we have got two things, which are, first one is Biot-Savart's law. So let me again clarify myself. In Biot-Savart's law, you get magnitude as well as direction. It's just not about magnitude, right? So it's Biot-Savart's law that we are going to learn it in this class only, but after some time. Then we have got Ampere's law. Like we studied Gauss law, over here we have got Ampere's law. And the reason is that I explained direction to you in a separate way is that we are going to use right hand thumb rule or right hand palm rule, right hand thumb or palm rule for finding out the direction of magnetic field, right? Got it? Now Biot-Savart's law and Ampere's law, we are going to deal it some time after. First let's talk about the direction of magnetic field, and also if you are going to talk about something that is called as magnetic flux. Do you remember what was electric flux? It was E dot A. Magnetic flux is going to be B dot A or BA cos theta. BA cos theta. So that means B can be written as phi upon A cos theta. It means that the SI unit of phi is magnetic flux is actually Weber divided by meter square, right? Cos, obviously cos theta has got no units. So the reason that I told you, or I told all of this thing, is that SI unit is Weber per meter square, or also known as Tesla, right? Also known as Tesla. And by the way, the another units are 1 Tesla can be written as 10 to the power 4 Gauss. So this is also an important thing. Dimensional formula, again you need to remember all the dimensional formula, whether you are talking about CBSE board exams or NEET or any state board exams, right? This is important. So I told you that we are going to actually discuss magnitude and direction in Biot-Savart's law and Ampere's law again. But for now, let's just understand what do we really mean by right hand palm rule. This is very, very important, right? So let me explain how to find out the direction of magnetic field lines or direction of magnetic field. So let's suppose this is, we have got a wire like this. We have got a wire like this and current is I flowing on it. Now this is the plane that I am talking about. This is the plane that we are talking about, right? On this plane, the wire is kept like this and the current is flowing in this direction. Keep your thumb along the direction of current. Keep your thumb along the direction of current. Now this is the palm rule that I am talking about. Open your fingers. Let's suppose you want to find out the direction on this side. Open your fingers in the along this side, and if your fairer end of your hand comes like this, right? So this means that on this side the magnetic field is cross. That is, it is going into the board. Again, let us do it. Thumb is in the current direction. We are finding the magnetic field into this side. Let's open our palm to this side. Fairer end comes out of the board. So that means magnetic field is something like this. And the reason behind it, you can also talk something like this, that thumb is in the current direction, curl your finger something like this, so the fingers will curl, it will go inside the board along this, then it will come out of it. So here we have got cross, here we have got dot, and if you want to find out the direction of magnetic field, it would be something like this, right? Hopefully you are getting it. So concentric loops somewhat like this. Done. And the direction of magnetic field is, although we are only concerned with cross or dot, right? We are concerned with this thing only. Hopefully this is all good. I have actually already discussed this thing because I will need this thing in motion of charge particle in magnetic field. This is actually very, very important, right? So when we are talking about motion of charge particle in magnetic field, what we really mean to say? We mean to say, now let's suppose that we have got a region of magnetic field something like this. Something like this, and the magnetic field is in cross. What do you mean by cross, doston? Quickly write down in the chat box. Cross means the magnetic field is directed into the plane, right now into the board, right? Something like this. Now we have already discussed that if a moving charge particle is in presence of magnetic field, there will be some force acting on it. That force is actually given as Fm, that is the magnetic force. It is given, if magnetic force, it is given as Q times V cross B. Q times V cross B. This is the value of magnetic force. We don't have to actually derive it. This is the formula that we must know. Using this we are going to derive lots of things, right? Using this we are going to derive lots of things. So this is the formula that you must remember. What things you can actually take out from this formula, that the magnetic force will be perpendicular to the plane of velocity and magnetic field. Magnetic force will be perpendicular to the plane of velocity and magnetic field. It will be perpendicular to both velocity and magnetic field. Got it? Now let's see how it works. Let's suppose a charge particle enters into this. A charge particle was moving in this direction into a straight line path, right? And at this point it enters, and let me actually draw it something like this. At this particular point it enters, it has got the charge is Q, it has got velocity as V, that means speed is V in this particular direction, right? And the magnetic field intensity is B, right? Now see how we are going to use. Now you might have seen this rule in grade 10th, Fleming's left hand rule. This is what Fleming's left hand rule does basically, right? It basically tells you the direction of force when a moving charge particle enters in a uniform magnetic field. Are you getting it, right? So these three are perpendicular, right? So that's what I was talking about. So these are all three perpendicular. So this is an easy rule, but what I'll actually ask you is that use the right hand rule that we have always talked about. What is the right hand rule, dosto? I mean perpendicular to this V cross B, right? So V cross B basically means that this is the V and cross B, because hopefully you can understand it. Right hand rule says this is the magnetic field, this is the velocity, right? Cross B. So thumb is getting up. So that means the force acting on this charged particle will be in this direction. So this is the direction of force, and this is the magnetic force. You can also use Fleming's left hand rule. See, magnetic field is inside and I am considering this to be positive charge, so motion of charged particle is in this direction, so force will be in upward, right? So instead of moving over here, the charged particle will actually start to move in this direction. And as soon as the charged particle starts to move in this direction, again the force changes its direction and hence it moves in a circular path. It moves in a circular path, right? And actually if you are going to actually throw a particle in a complete magnetic field, it will actually start moving in circles, something like this. This is the direction of motion. This is how the motion of a charged particle is going to be. Why? Because now the magnetic force will actually provide the necessary centripetal force. Are you getting it what I am trying to say? Are you getting it? So for this particular case, we can say that magnetic force is, the magnitude of magnetic force is QVB sine 90 degree or just QVB. Is it correct? Quickly write down in the chat box if you are following it what I am trying to say, that why it will move in a circle or why it is constantly moving and this is acting like a centripetal force. Have you got it? Because as soon as it will change the direction, the magnetic force will always change the direction, it will always point towards the center, right? Got it? Is it clear? And now if you want to find out what the radius is going to be, everything about that, so we are going to just say that okay, it means that now the magnetic force will provide the necessary centripetal force. That means this is going to be equals to QVB. This is going to be equals to QVB. So one of V can be cancelled out and the radius of curvature that is going to be covered will be written as MV divided by QB. Now again this is actually quite easy, very easy, but quite useful as well. You are going to find numerous of questions in your board exams and papers like NEET and JEE mains from this. Alright, is it all good? Clear? After this, after finding out the radius, we are going to also find some of the variations of it. That means R is written as, this is nothing but this is momentum, right dosto? This is momentum, so this can be written as P divided by QB or under root 2m KE divided by QB. You can rewrite this thing as something like this as well. Also if charge is accelerated in potential difference D, then instead of kinetic energy I can also write it as, so the radius of curvature will be written as under root of 2m QV, hopefully you can get this one, times QB, right? So this is also another formula. After this, let's also write the formula for time period. Time period is nothing but 2 pi R by V. So R was nothing but 2 pi mV by QB divided by V. So from here we can say that time period is nothing but 2 pi m divided by QB, and this is a very important relation. It tells us that time period does not depend upon the speed. Time period does not depend upon the speed, right? So if you have got two particles of same charge, one is moving with v speed and the another is moving with 2v speed, in same magnetic field, the time period is going to remain same, because time period only depends on the mass of the particle, charge of the particle and magnetic field intensity. Are you getting it? Quickly write down in the chat box if this is all good. If this is all good, quick. Fine, everything's fine. Do we need to write any more formulas for this? You can write it for frequency as well, but that's all fine, right? We have written almost every formula for radius of curvature, for time period. So after this, let's now there are going to be some more important points. And what are those? I already told you that this will actually, the magnetic force, I told you that the magnetic force will provide the necessary centripetal force. Is that correct? And if you remember, centripetal force does no work. Centripetal force never does work, right? So work done by centripetal force is 0. This means that work done by magnetic force will be also 0, right? So magnetic force is perpendicular to the velocity of the particle, so no work is done and no change in velocity. That means change in kinetic energy is also 0, which is basically work done. So even the particle is moving in circles, the speed is never going to change. Only the force, the only job of force is to change the direction of the motion. Got it? Alright, the perpendicular force 𝐄𝐍𝐵 cross acts as a centripetal force. I have already explained each and everything to you, right? The larger the momentum, the larger is the radius, absolutely, because radius is actually equals to mv divided by qb, where mv is the momentum, right? Time period and frequency are independent of the velocity. I have covered it. Is that correct? Clear? Everything's clear, doston? Quickly tell me. So we have come to the Biot-Savart's law that I just told you, right? So what is now Biot-Savart's law? We have completed the moving charges part. Although I'll actually not skip one more thing. There is also one more point. That point is actually sometimes the particle travels in a helical path, right? Although it is not given, I think it is given in NCERT. So now instead of drawing the magnetic field into the plane, I will draw magnetic field as something like this, because it will be easier for us to actually draw the diagram. So let's suppose this is how the magnetic field is, right? And now the particle, if you remember initially, what was the case over here? I'll also draw the case. The case was, dosto, that for this one, the velocity was perpendicular to magnetic field. This was the case. I mean, this is not always, right? I mean, see, force is perpendicular to velocity and magnetic field, that is always. Because that is basically the rule of cross product. But velocity is perpendicular to magnetic field, this is just one of the case. The another case can be when velocity is not perpendicular to magnetic field. Let's look at that case as well. So if velocity is not perpendicular to magnetic field, this is the another case. So if it is not perpendicular, that means it will make some angle. And if this is the magnetic field that we are talking about, then let's say the velocity is something like this. This is V. And this is the charged particle Q. Is that correct? Is that correct, my friends? Quick. So now what we are going to do is we are going to just break down the components of this velocity. So this is the x component, this is the y component. So this I'm just going to write this thing as, let's say this is actually angle theta, so I'm going to write this as V cos theta, this is V sin theta, right? I think it's clear. There is going to be no change in this velocity. I am talking about the velocity. And for this one, the magnetic field will change the direction of this component, right? So because of this component, the particle will, please understand how is this happening. This is the magnetic field, right? This is the magnetic field, like my hand. and this is how the particle was trying to enter the magnetic field. This is how the particle was trying to enter the magnetic field. So if there was only like this velocity, if there was only this velocity, then the particle would have moved something like this. Are you getting it, dosto? This is a circular motion, na? This is a circular motion. See, just now we actually talked about if there was magnetic field like this, the motion was something like this. So if you are going to see from front, it would look, wouldn't it look something like this, isn't it? Quickly tell me in the chat box. And also we have got a velocity in this direction. So there is also one more velocity, and this is something like this. So motion would be something like this, right? So this is something that is known as helical path. Right? So because of this, the particle is going in this direction, and because of this velocity, the particle is moving in circles, right? So that's it, dosto. So R will be written as mv sin theta by qb, right? Or everything will be same. Time period will be time period. Anyway, time period does not depends upon the upon what? 2 pi r, right? So everything correct. qb. It does not depend upon the velocity. If somebody tells you to find out the distance about this, is actually known as pitch. So just multiply if you want to find out this. So just write v cos theta times the time period. Is that correct? Quickly write down in the chat box if everything's good. Then let's move to Biot-Savart's law. Now, when we are going to talk about Biot-Savart's law, it is a law, so we'll just have to remember it, right? We are not going to go after its derivation and all. So we are going to just remember it. We are going to say, let's say that we have got a wire of length. We have got a wire of length of any length. Let's say current is flowing I, and we are taking out an element out of it, and that element is, let's say, dl, a small element dl. And by the way, dl is a vector quantity. So you are going to ask me, sir, then what is the direction of this vector quantity? So direction of this vector quantity is the direction of current at this particular point. So this is the direction of current, right? So this is the direction of dl, all right? And let's suppose we want to find out the magnetic field at a certain point, that is somewhere over here at r, at this point, which is actually at a distance of r. First thing first of all, tell me the direction of magnetic field. So you are going to just do one thing, sir, thumb like this, open your fingers along this point. Your fairer end is coming towards this point. That means magnetic field will be written as dB. Why dB? Because of a short a small element, magnetic field will be also small, and that will be written as dB. Is that correct? Right? Now the angle between vector r, this is by the way vector r, and this dl is angle theta. So Biot-Savart's law says that this dB is directly proportional to I dl cross r divided by r cube. This is what the Biot-Savart's law is. Now you will have to remember it like that, right? And that's why I said, when I was talking about the direction of magnetic field when we started this chapter, I told you that it's not like Biot-Savart's law doesn't tell you the direction of magnetic field. It does. Well, dl cross r, so it tells you the direction of magnetic field, right? So it's not that we can't find out the direction from here. By the way, this is a vector quantity, and removing the proportionality sign, we are going to use a proportionality constant, that is mu naught upon 4 pi, where mu naught is permeability of free space, and we are going to write it as dl r sin theta divided by r cube, and this can be cancelled out, and this is what we are going to use, that dB is actually equals to mu naught upon 4 pi and by the way I have got I also, so I mu naught I dl sine theta upon r square. So here r square we have got, right. So this is the formula that we are going to look for. Quick, tell me if everything's correct till here. This is what the Biot-Savart's law is, right? After this, let's look at some of the important points. Biot-Savart's law gives the magnetic induction due to the infinitely small current element, right? Then we can integrate it. The direction of magnetic field is perpendicular to the plane containing the wire and the perpendicular from the point, right? Alright, so after this I think almost we have done everything. We can also find out, we can use one of the what we can say, it is actually one of the Biot-Savart's law use, right? So we can use Biot-Savart's law to find out the magnetic field due to a circular current carrying loop. And how does it works? Let's see. So let's suppose we have got a current carrying loop, something like this, and we have got an axis, and by the way this axis goes something like this, that it is actually passing through it, something like this, right, and the current is flowing in this direction. So I current is flowing over here. I'll again explain it, right. This is the loop and this is the direction of current. So at this particular point the current is actually moving towards you, right. You can just draw a tangent at any point if you want to find out the direction of current, right. So at this particular point the direction of current is at this here, right. Hopefully you are getting it. Now let's suppose we want to find out the magnitude of magnetic field at a distance of x from here, at a distance of x from here. So this is x, right, and this is the dl element. This is the dl element, let's suppose. This is the dl element that we have got, right. So now first of all tell me that if I am going to join this line, what is the angle theta over here? What is the angle theta over here? Write down in the chat box. Write down in the chat box what is the angle theta over here. And first of all tell me what is theta. Quickly, what is the angle theta over here? Quick. See, this is the ring, this is the coil, right. At this particular point this is the current and this is the current, and we are joining it something like this. So what is this angle between these two things? Just think about it. This angle will always be 90. This angle will always be 90. Very good. This angle will always be 90. This is, I'll draw it something like this. So this is the current element. And this is the direction of the current at this point. So this angle will be always 90 degree if you will think about it, right. This angle will be always 90 degree. Now again hear me out. Because of this current element, what is the magnetic field at this particular point? So this is the axis. At this particular point the current is something like this. So I'm going to place my thumb, I'm going to open my fingers, this fairer end is coming something like this, right. So at this particular point the magnetic field is in this direction. This is the magnetic field direction. Got it? Let's just suppose that the radius of this this loop is actually r. So let's suppose the radius of this loop is actually r. Now many students have doubt that how you have found out the direction of this one. Again, just use the right hand rule over here. That's it, right? So because of the small element, magnetic field will be also small. Alright, let's suppose that this is angle theta. If this is the angle theta, then this angle will be theta. it means that this is going to be dB cos theta, sorry, dB sin theta. And you know what, let me use phi over here because we already used theta, na? So let's use phi. So this is phi, this is sin phi, and this is cos phi, this is also phi, this is dB cos phi, right? And this is also dB cos phi, right? So these are going to cancel out. And by the way, sorry, first let me explain it how we have got this dB cos phi. Write down in the chat box if you have any doubt how we have got this as dB. If you have any doubt, let me know in the chat box how we have got dB in this direction. Because the next thing that I am going to say is that doston, symmetrical to this element, we have got another element over here as well. This is also a symmetrical point. So because of this, we are going to say that the dB is going to be something like this. And because we are talking about a symmetrical object, this angle is also going to be phi. So now we can say that this is going to be dB cos phi, right? So now we can say that because of symmetry, every component of dB will get cancelled out, which is in the vertical, which is a vertical one, right? Got it? Which is along vertical line, they will all get cancelled because of symmetry. Everything's clear? Quickly tell me which part, you tell me which part I have to repeat it. Which part I have to repeat it? Equal and opposite is quite easy dosto. If this is the point, the diametrically opposite point of that will be over here, and because of this, if the magnetic field was like this, then because of this the magnetic field will be something like this, making an equal angle phi, right? So dB cos phi can cancel out, and we will to find out the net magnetic field, we'll just integrate all of these dB sin phi's. That's it, that's what I'm saying. So the net magnetic field will be dB sin phi and the integral of that, right? And after this, let's write dB, so it would be mu naught upon 4 pi I dl. I already told you that we have to use sin 90 over here, but I'll write it for you. Please don't get confused what this sin 90 is, right? That sin 90 is the angle between dl and this r. What is this r doston? This is the r, and this r is actually r square plus x square and root of that, right? This r vector divided by the r square. The r square is actually capital R square plus x square times sin phi, and dosto sin phi right now is going to be, sin phi is actually going to be r divided by r square plus x square and root of that. Quite similar to what we have done in those dipole things, right? So r divided r square plus x square whole raised to the power 1 by 2. Is it good? So after this, we will be left with mu naught I r divided by 4 pi r square plus x square whole raised to the power 3 by 2 times dl. And when we want to integrate each and everything, please see that all of these things are constant, and all we have to do is we just have to integrate this dl, right? So we will be left with mu naught I into r whole divided by 4 pi r square plus x square raised to the power 3 by 2 times, what is the length, what is the total length of this loop? That's going to be 2 pi r, and this is your final answer dosto, right? This is your final answer. Well, you can rewrite this thing as the net magnetic field will be, mu naught upon 4 pi you can write it as 2I pi r square divided by r square plus x square raised to the power 3 by 2. So this is the final answer. And now we can use it again and again for different things. Let's suppose you want to find out the magnetic field intensity at the center point. Just substitute x equals to 0 dosto. So if you are going to substitute x equals to 0, you will get the answer. I will write it here for you. So if at center, so what happens at center? At center x is equals to 0. So at center I am going to write that net magnetic field okay, I've got some less space, so I'll write it over here. Mu naught upon 4 pi into 2 I pi r square divided by r cube, right? So this can be cancelled out by this, pi can be cancelled out by this can be cancelled out by this. So finally the answer comes out to be mu naught I upon 2r. So this is the thing that you need to actually remember, that this is at the center. Alright, this is at the center, that is mu naught I upon 2r. Now tell me dosto if everything's clear. Quick. Circular current loop is all good. So this is the graph for this equation, for this equation, for this formula. You can also look at the graph, and at the center the magnetic field is maximum. Remember it, right? Remember this thing, that this is actually maximum at the center, and direction of magnetic field is given by right hand thumb rule. Everything is similar to whatever we have learned so far. After this, field at the center of the coil, field at the center of the coil is mu naught I upon 2r. That's what we have found out, right? Nothing new. Now I told you that everything will it's going to repeat. Like we did in electrostatics, we first studied finding electric field, then we studied Gauss law, now we are studying Ampere's law, right? Now Ampere's law says that if you have got a loop, the line integral of B dot dl will be actually equals to mu naught times of I enclosed, right? And how does it works? It works something like, let's suppose that we have got a wire, an infinite wire, something like this, on which current I is flowing. So let's make a loop, let's make an Ampere loop, right? So this is an Ampere loop that we are talking about. Alright, and we want to find out the magnetic field at this particular point, let's say at a certain radius r, right? Got it? At a certain radius r, we have got we have drawn the Ampere loop. Now this is not a surface. You must understand the difference between the Gaussian surface and an Ampere loop. This is just a loop, right? So I am going to say that, well, magnetic field is constant at every point, right? Plus please understand that I am going to write it as B dl cos 0. Why cos 0? Because again at every point the element dl will be same as the magnetic field, right? Right now here the magnetic field is actually is inside. Over here the magnetic field is actually outside, right? So now if I am going to integrate it, we are going to write mu naught times I enclosed is I. So we will write B into the total length of this loop is 2 pi r equals to mu naught into I. So for an infinite wire, the formula comes out to be mu naught I upon 2 pi r. So now this is very, very important. Or sometimes they write it as D. So mu naught I upon 2 pi d. Are you getting it? Is it clear? Quickly tell me in the chat box if it is clear. Quick. Then we will move on. All right, fine, great. So we have to have infinitely long straight wire. After this, I mean, you also have got solenoid, and we can also find out the magnetic field due to a solenoid. Hopefully you all know what solenoid is, right? This is how a solenoid looks and magnetic field of solenoid looks. Well, in generally in books, you must know that solenoid, must be knowing that solenoid looks something like this. And the current flows like this. Alright. Now the thing is that solenoid, what do we really mean by solenoid? Solenoid is actually, it is a wire which is actually wound up on a non-conducting core. So this is actually a non-conducting cylinder, right? This thing is a non-conducting cylinder or non-conducting core, because we don't want that while creating magnetic field by the wires, we don't want that our core becomes magnetized, right? Or we don't want our core starts giving off magnetic field. Why? Because actually we want is that because of this solenoid, it actually creates a magnetic field which is much similar to a bar magnet, right? So, and it actually looks something like this. And how to find out the direction of magnetic field? The direction of magnetic field is given by, again, right hand rule, but now we are going to actually say that this is actually something that is known as clock face rule. And this is again quite easy. Again, this is quite easy. This is the solenoid. Try to hold this solenoid with your right hand. Try to hold this solenoid with your right hand in such a way that the fingers are going to be in the direction of current. Can you see that this is a solenoid and current is going something like this? So my hand should go in this direction and thumb will be pointing in this direction, right? So thumb will tell you that here is the direction of magnetic field. So that means this will act as a north pole of the this will act as a north pole, this will act as a south pole. That's why you are seeing that magnetic fields are moving something like this. And in between of this solenoid, you are going to have almost parallel magnetic field. That means almost uniform magnetic field. All right. And after this, again, just like bar magnets, magnetic fields are going to be something like this. All right, everything's clear? And if using Ampere's law, we want to find out the magnetic field of a solenoid, then we can do it. All we have to do is we have to actually draw the cross section of this solenoid. So what we are going to do is we are going to actually draw the cross section of this portion, of these two portions. I'll actually use this as the color. Okay, not this. Let me use red color. So we are going to draw this portion and we are going to draw this portion, right? And how we are going to do it, let's see. So we are going to say that, let's suppose this is the solenoid, this is the cross section of the solenoid, and it looks something like this. That here the current is moving out, right? Here the current is moving out, so I am making dots. So these are currents coming out, wires coming out from here, and here I've got cross. And inside of it we have got magnetic field in this direction. So let's make a loop which is something like this. Let's make a loop something like this, and let's name it, like A, B, C, D, and the direction of loop is from A to B, B to C, C to D, and D to A, right? Let's make a loop like this. Got it? Now please see over here. If I am going to talk about again the Ampere circuital law, the what I am going to say is that B dot dl, right? We are talking about the B dot dl. The net B dot dl will be actually because of AB plus BC plus CD plus DA. Now please understand, for BC, for BC part, DL is actually perpendicular to magnetic field. So that means cos 90 will be 0. Over here, there is no magnetic field. For this one again, theta is 90 degree. So this is, the magnetic field is only because of AB part, right? So I am going to just write this thing as AB, and we are going to say that, okay, so magnetic field is B and DL is actually, let's say the length of this thing is L, and we are going to write it as mu naught times I enclosed. First tell me if everything is clear till here. Is it all good? Right? After this, I am going to actually say one more information. That N is the number of turns per unit length. N is the number of turns per unit length, right? So if that is the case, then we are going to say that B into L equals to mu naught times, in L length, if this is the length of the that is AB, so we are going to write mu naught times L into N into I. So L can be cancelled out, so magnetic field comes out to be mu naught Ni, and this is the magnetic field that you are going to use 90% of the time for solenoid, almost like every time, right? Although we have got another formula also for solenoid, which we derive it using again integration, but that's rarely used in your school exams or even in NEET, right? First tell me if everything's clear till here. Quick. Done? Shall we do some questions from this? By the way, we have got one more topic, that is force between two parallel current carrying wires, which is actually useful for your school exams. So I'll explain this one as well, right? What is this about? That let's suppose that we have got two wires which are parallel to each other. Let's say this is current I1 and this is current I2. Now, one of the prerequisite that you need to know for this one is, please repeat the magnetic field due to a coil on its axis. Buddy, that's we have completed that quite ago. You just watch a re-recording of this one. Right? You can just move back to that time. Right. The prerequisite is that you must understand that what is the force on a wire kept in magnetic field B. And by the way, this is a current carrying wire, so the force is actually BIL sin theta. This you must know. And the distance between these two is let's say it is D, right? Now the thing is, which part? So negative direction is denoted by where? Which part should I repeat it again? Quick. See, for this one again, when we are going to talk about the force force between two parallel current carrying conductors for these two conductors, we are going to say one more thing. We are going to say that there is a magnetic field produced by this wire, that is wire 1. There is magnetic field produced by wire 1 at the place of wire 2 and vice versa, right? But let's first talk about this. There is magnetic field produced by wire 1 at the place of wire 2, and the direction of that magnetic field is, thumb is like this, we'll open a finger over here. So this is the magnetic field that is being produced by wire 1, that is inside, right? Now again let's talk about this wire. So this is a wire kept in external magnetic field, and this is a current carrying wire. So it will experience a force, and the force will be given as, so I'm going to write force on wire 2. So I'm going to write it as F21. Is that correct? Force on wire 2 due to wire 1. अच्छा, how current is equals to NLI? अच्छा ठीक है, how current is equals to NLI beta? Okay, let me go it over there again. You tell me one thing. If for a unit length there is n number of wires, that's what I have said. For a unit length there is n number of wires. So if there are n number of turns, right? There are n number of turns for a unit length. So for L length there are going to be n number of turns, and for every turns the current is I. Like this is I, then I, then I, so it becomes 3I. So for n turns the current will become Ni, correct? So for L amount of length, the number of turns would be n into L, and the current is I. So that is it. Is it all good now? Clear, clear, clear? Can we move on? Alright, great. So now force on 2-1 is going to be magnetic field due to 1 times current of that wire times length of that wire, and right now the sign is actually 90 degree. By the way, if you want to find out the direction, I can find it out for you. See what is the direction of force on it using your simple class 10th rule. This is the direction in which the magnetic field is. Current is in this direction, so this is the direction of force. So that means this wire is trying to attract this wire. So this is the direction of force. So this is force on wire 2 due to wire 1. And similarly, if you are going to find it out, this is going to be the force on wire 1 due to wire 2. Is that correct? Is that correct? So after this, let's find out what B1 is going to be. Now I have, you know that this is going to be mu naught I1 divided by 2 pi d times I2 times L. So if you are going to, again I'll write it as F21 divided by L. So this will be force per unit length, and the formula is going to be, I'll rewrite this thing as mu naught upon 4 pi d 2 I1 I2. So this is something which is actually important for your numericals, right? And also the derivation is important for your understanding. By the way, after this, let me just write this thing as well, that these two forces they exist in pair. So F12 is actually equals to the negative times of F21. Alright, is it all good? Clear? This part is all good. Then again we are going to talk about, we are going to talk about magnetic dipole. We are going to talk about torque acting on magnetic dipole. So those all things are quite similar to what we have done in electrostatics, right? Hopefully that would be all good for you. Then we have got, again we have got galvanometer. That thing is also quite easy to understand. Let's move to some questions. Let's move to some questions quickly. Everything is perfectly clear, fine. A wire is parallel to one arm of a square current carrying loop which also carries current Now at any point A within the coil, the magnetic field will be, alright, at any point A within the coil, the magnetic field will be, okay, let's find it out. 90 seconds. Quickly, let's find it out. A wire is parallel to the arm of a square current, okay, which also carries current. Now at any point A within the coil, the magnet is okay, ठीक है. See, if we only have got loop, then because of loop, magnetic field due to just loop, magnetic field due to just loop is actually inside cross, and magnetic field due to wire is also cross. So we are going to say that the net magnetic field will be more, right? More than the magnetic field produced by the loop only. So it should be option B. Is that correct? Is that correct, friends? It would be option B. Absolutely. Very, very good. Good, good, good. What about this one? Radius of current carrying coil is R, then the ratio of magnetic field at the center of the coil to the axial point, which is R, which is at R by root 3 distance away from the center of the coil. You do it by yourself. I'll tell you, this is quite easy. So they are saying that they have to find out the ratio at center. So we know that the magnetic field at center is actually mu naught I upon 2R, and divided by magnetic field at the axial point, which is actually mu naught upon 4 pi 2 I pi r square. By the way, there is one more thing, dosto. If there are n number of turns in a circular coil or any sort of a coil, if there are n number of turns, then you have to find out the total magnetic field just multiplied by capital N. That's it, right? So 2 pi r square divided by r square plus x square whole raised to the power 3 by 2, and right now that x is actually equals to r root 3. Can you do it? Can you do it? Can you do it? Tell me if is it all good. I can move on, right? Something like this. For the given current distribution, the magnetic field at point B will be. Find it out quickly. All right, let's see. So magnetic field due to, let's say this is wire 1, this is wire 2. First of all, also please pay attention at the directions of these wires, right? Directions of the magnetic field produced by these wires. So magnetic field due to wire 1 will be written as mu naught upon 2 pi, and the current is actually 5 ampere divided by D is actually 2.5, right, and the direction is going to be cross, which that's why we are going to write, when we are going to find out the final magnetic field, we are going to write it with a minus sign, that is mu naught upon 2 pi. This is actually just 2.5 and this is actually also 2.5. Is that correct? So this is going to be 1, right, and this is going to be 2. So this is going to be mu naught upon 2 pi. That's it. So this should be the answer, mu naught upon 2 pi. By the way, direction is going to be cross because this was cross and this was dot. So this direction is going to be cross. Please tell me if you have any doubt. Mu naught upon 2 pi cross. Is that correct? So correct option is option C. You all have opted for option option B. Why is that? Is it clear now? Quickly tell me in the chat box, is it clear now? If not, then ask your doubt. We have just done one thing. Okay, I'll explain it again. We have just done one thing. We have used the formula mu naught I upon 2 pi d, right, and I have said that use the direction for use right hand thumb rule for the direction. Thumb is in this direction, current will be, because of this magnetic field will be in cross, because of this magnetic field will be in dot, right. But the only difference is, well, current is double of this value, so magnetic field produced by this wire will be doubled, right. Tell me if you have any more doubts. Clear now? So after this, I have got some more questions for you. Let's start with this one. A very long straight wire carries current I, alright, at the instant when the charge plus Q is at point P, has a velocity v, the magnetic force on the charge is. Quite easy. Quickly solve it. How, sir, the direction will change? See, the direction will not change. What I am saying is, we have got two wires, we have got two different magnetic fields, magnetic fields in two different directions. All I have said is the magnetic field which has got a greater magnitude, the net magnetic field will be in that direction. That's what I have said. Quick. Because of this wire, again the magnetic field will be in this direction, right. So if magnetic field is in this direction, then again the force will be magnetic field in this direction, charge plus Q is moving like this, so it will be like OY, it will be along OY. Is that correct? Option C. It will be option C. Tell me quickly in the chat box. Option C, right? All right, okay, great. So now, although we have completed magnetism till here, but still we are left with 3 more chapters, right? So now we can do one more thing, that we can either complete 1 or 2 chapters right now, or we can either I can come up with another one shot lectures for all of those chapter at a straight. So what do you guys want? Quickly write down in the chat box. What do you guys want? Well, we can do magnetism and matter. That's not a big chapter. That is not a big one. And till here, tell me if you have any more doubts in moving charges and magnetism. In moving charges and magnetism. Moving charges and magnetism, no more doubts. Can we start magnetism and matter then? Right? See, in magnetism and matter, all right. Now. All right. Okay. Let's continue then. Let's continue with magnetism and matter then. And I'm going to explain, first I'm going to explain what are the different things that you must learn in magnetism and matter. The first part of magnetism and matter is actually learning about bar magnets. Learning about bar magnets and learning about the magnetic dipole, moment, torque acting on magnetic dipole, right? All of these things. This is what I was saying, that this is actually pretty much similar to whatever we have learnt in electrostatic, but let's once again actually talk about it. Let's once again see what are the different things that we can learn in this chapter. So a magnet has two poles, north and south. Like poles of two magnets repel each other, unlike poles of two magnets attract each other. Basic things. The important thing that we must remember over here is that if we have got a bar magnet, something like this, then the poles have some pole strength. Let's say this is north pole, this is south pole. So the pole strength is a physical quantity which will tell you the strength of the magnet. It is much similar to what we have learned in electric dipole. Like in electric dipole, we talked about two isolated charges. The only difference is, well, the two charges which were kept at a short distance. The only difference is over here we can't have isolated poles, right? You won't be having any north pole or south pole alone. They will always come in pairs, right? So this is plus m, this is minus m, similar to what we have learned in electric dipole, and let's say the distance between them is actually d. So the magnetic dipole moment, which is actually written as capital M, it will be written as the pole strength times d. So this is one of the formula. By the way, the direction of this will be again similar to what we have learnt in electric dipole. It will be like from minus to plus. So this is the direction of dipole moment. Alright. By the way, one more thing that you must remember, that we have got one more formula for magnetic moment, and that formula is I cross A, and this formula looks something like this. Let's suppose that you have got a loop, a current carrying loop, and this is the axis, and this is the current I, right? So just use again the right hand rule, in this, in some way like this, right? So thumb is going to tell you the direction of magnetic moment. This is another way, right? So everything will now repeat itself, like we have done in previous. We have talked about like electric dipole moment, then torque acting on an electric dipole moment, right? So torque over there was PE sin theta. Here the torque will be actually MB sin theta. Where M is the magnetic moment, or torque will be written as M cross B. Are you following what I am trying to say, right? Potential energy will be written as minus M dot B, or MB minus MB cos theta. Are you getting it? Quickly write down in the chat box. Quick. So these are some of the things that we are going to look for. So again, these are the notes. So this is a bar magnet, minus M pole strength plus M pole strength. A magnetic moment of a bar magnet is defined as a vector quantity having a magnitude equal to the product of pole strength M with effective length L and directed along the axis from south pole to north pole. Whatever we have done till now, we have already covered everything, right? Moving on, after this, when you are going to talk about the directions of magnetic field due to a bar magnet, again directions are pretty much clear to every one of you, that magnetic fields originate from, they not originate but they move out of the magnet from north pole, they go to the south pole, and then inside the magnet they move from south pole to north pole, and inside the magnet they are pretty much uniform, that is parallel lines, right? Got it? Then after this, some of the properties which are similar to what we have done in electric fields. The only difference is over there we had open loops. Right now we are going to talk about closed loops. Alright, we are going to talk about the closed loop. So the magnetic lines of force or solenoid forms continuous closed loops. So this is a major difference between electric field lines and magnetic field lines. The tangent to the field line at any given point represents the directions of the net magnetic field at that particular point. Same thing like electric fields never cut each other, magnetic fields are never going to cut each other, because if you are going to let magnetic fields cut each other, then there are going to be two tangents that are possible, which will basically means that there are two directions of magnetic field at a single point, which doesn't make any sense, right? The larger the number of field lines, the greater will be the magnitude of magnetic intensity. Again the same thing, if let's say if the magnetic field lines are crowded at a place, at that particular point the intensity of magnetic field will be also more, right? The magnetic field lines do not intersect, I have already explained it, right? Tell me if you have any doubt quickly. Quick, sir. Tangent, if you have any doubt from tangent. Quick, we have talked about this point in our electric field chapter. What I am trying to say is, let's suppose that you have got two magnetic field lines which are something like this. Now at this particular point, if you want to find out the direction, just draw a tangent at that point. So at that point, if you are going to draw a tangent, one of the tangent is possible something like this, the another tangent is possible something like this, right? Now this is actually absurd, that at one point we have got like two tangents, which is not which basically means that at one single point we have got two directions, which is not possible, right? Got it, dosto? After this, the main thing that will be left in this chapter is going to be your Earth's magnetism. But before that, I am going to also explain something which is actually important, which is about the magnetic properties of the materials. Like, now this is actually very important for your exams. Other than anything, this is actually very important. Many questions come from this. So let's first complete this topic. Now, first thing that we can classify the materials as diamagnetic, you already know, you have been waiting for this chapter, for this topic. We can classify the material as diamagnetic, paramagnetic and ferromagnetic on the basis of the magnetic susceptibility. Now first of all, what do you mean by magnetic susceptibility? I'll explain it to you. Let's suppose I have got two bodies, right? I've got two bodies, and both of those bodies I have kept in a uniform magnetic field in same magnetic field. And what I am actually observing is that one of the material gets magnetized, it gets magnetized, and the other material does not get as much magnetized as the other one, right? So the magnetization in this one is actually quite larger than compared to this one. So I am going to say that this has got higher magnetic susceptibility. Got it? So this is what the magnetic susceptibility is about, that the amount of magnetization that can take place in a material. Now for diamagnetic materials, the diamagnetic materials actually repel the magnetic fields. They move from the region of stronger magnetic field to weaker region of magnetic fields, right? So this means that they have got a negative magnetic susceptibility. They have got a negative magnetic susceptibility. They repel stronger magnetic field, right? Whereas paramagnetic materials actually they are attracted to, they get magnetized, but they get weakly magnetized. They get weakly magnetized. So for this one, the value of this is going to be very small but positive, but greater than 0, right? Are you understanding what I am trying to say? So first we have got diamagnetic whose magnetic susceptibility are going to be less than 0. For paramagnetic, they will get weakly magnetized, and the magnetic susceptibility will be very small but greater than 0. Other than that, let's talk about the third one, that is ferromagnet. For ferromagnet, they get strongly magnified, and that's why their values of magnetic susceptibility is actually far more greater than 0, and they have substantial values, that means large values. So this is one of the bases on which we have categorized these materials. Now let's talk about some of the more things over here. Let's talk about the individual things, and these are some very important for your exams. So make a note out of it, take some screenshot, whatever you want to do, but this is very important. For diamagnetic substances, they have a tendency to move from stronger to weaker part of the external magnetic field. A magnet repels a diamagnet, right? The resultant magnetic moment in an atom of a diamagnetic substance is 0. Now what do you mean by resultant magnetic moment? That means they are talking about the individual molecules, they have got 0 magnetic moment. Examples are, this is actually very important. Examples are bismuth, copper, lead, silicon, and nitrogen and sodium chloride. By the way, last year, I think last year in NEET as well as usually in the CBSE exams, questions comes that if you have got a diamagnetic material and it is kept in an external magnetic field, draw the pattern of magnetic field over here. So the magnetic field will be drawn something like this. It will be drawn, first they will get actually repel something like this. This is actually something important for your exam, right? We are going to also talk about ferromagnet and paramagnet. So for ferromagnet and paramagnet, they will actually get they will pass through the materials, right? Superconductors are metals cooled to very low temperature which exhibits both perfect conductivity and perfect diamagnetism, where magnetic susceptibility is equals to 1 and relative permeability is actually equals to 0. Now let me explain what is relative permeability so that you can clearly understand it. Now for relative permeability is actually absolute permeability divided by mu naught, right? Absolute permeability divided by mu naught. Alright, so mu naught is the permeability of free space. So if somebody is telling you that relative permeability is 0, what does it mean? It means that their absolute permeability becomes 0. Right? Their absolute permeability becomes 0. Got it? Right? Whereas we are going to talk about again we have already discussed this magnetic susceptibility for each particle, for each substance. We are going to again talk about magnetic relative permeability for other materials as well, right? Superconductors repels a magnet and it is repelled by the magnetic, and this is the phenomena that's used in those Meissner effect, or those if you have talked about those French trains that levitates from a track, right? This is the thing that is being used. Got it? After this, let's talk about paramagnetic substances. Now we know that paramagnetic substances are those substances which are weakly magnetized, right? These are the particles which are weakly magnetized, but still, but if they are weakly magnetized, then what will happen with mu r? Mu r will be actually still, mu will be actually greater than mu naught, because it is getting weakly magnetized, right? It will be greater than 1. Are you getting it? They have a tendency to move from region of weak magnetic field to strong magnetic field, but the only difference is this is the main point. So please remember this. Alright. The individual atoms, now this is very important, that individual atoms of paramagnetic material possesses a permanent magnetic dipole, but on a whole, if you are going to talk about, like, we have got a paramagnetic material inside of it, we have got like different individual atoms, then on a whole the net dipole moment is 0, right? But individual atoms have dipole moments, and here the examples are going to be aluminium, sodium, calcium and oxygen and copper chloride. There we have got sodium chloride, so remember, and nitrogen over there. Here we have got oxygen, right? Other than that, for for paramagnetic substance, we have got also a very important thing, that is Curie's law. What does Curie's law says? Curie's law says that the magnetization of a paramagnetic material is inversely proportional to the absolute temperature. It means that if you are going to increase the temperature, the paramagnetic material will actually start losing its magnetization. At a particular temperature, it holds good for high temperature and not for strong magnetic field, right? So magnetization is actually directly depends on the external magnetic field and inversely depends on the temperature, and C is the Curie's constant. Alright, and the temperature at which it will actually, at a certain temperature, it will become a diamagnetic material. Got it? So hopefully this is all good. And after this, I must actually explain you the ferromagnetic materials. Now ferromagnetic materials, we all know that they get strongly magnetized, but from start you must understand that these are of two types. One is hard ferromagnets and the another one are soft ferromagnets, right? Now these are strongly magnetized when placed in an external magnetic field, and they have strong tendency to move from weaker region of magnetic field to stronger region of magnetic field. That means we have already talked about their magnetic susceptibilities will have significant values. Their mu r will be also far more greater than 1. Got it? Again, individual atoms, just like paramagnetic, their individual atoms also have net magnetic moment. What do you mean by this net magnetic moment? It means that if we are talking about like a ferromagnetic material, then this is something like happening over here, that these atoms have magnetic moment but in random direction. But when they are going to be when they will be present in an external magnetic field, they will align themselves, right? And the extent with which they align themselves is quite high as compared to a paramagnetic material. That's the difference. All right, clear? Hopefully this is all good. After this, I think just go through this if you want to actually have a look at this. This is from your NCERT only. So all the things which are actually having a negative value of this, these are all the diamagnetic materials, and all the materials which have positive magnetic susceptibility are paramagnetic substances, right? So you don't have to actually remember it, but you just have to remember it. If magnetic susceptibility is negative, then it will be a paramagnetic, a diamagnetic. If it is positive, then it will be a paramagnetic material, right? Do you have any doubt from this point? Quickly tell me in the chat box if you have any doubt till here. Quick. All good? All good? So after this, we have been left with a small part of the same chapter, that is Earth's magnetism, right? Hopefully we have got Earth's magnetism in our course, right? Can you confirm? Can you confirm whether we have Earth's magnetism in our course? I think we have. No, we don't have we don't have Earth's magnetism over here, right? We don't have Earth's magnetism. So we don't have to worry about it. We don't have Earth's magnetism, so no worry. Yeah, so after this, if you don't have Earth's magnetism, let me also explain some brief things about electromagnetic induction to you, so that some of you which you have exams on. Acha, by the way, if you have got some questions like this, then can you do it? Curie temperature is the temperature above which, sorry, this is actually ferromagnetic material becomes paramagnetic. First I told you that paramagnetic becomes diamagnetic. It is ferromagnetic becomes paramagnetic, right? This is the answer. And actually I have Curie's laws for you for this one as well. This is the Curie's law, right? Remember this thing, remember this formula of magnetic susceptibility, right, at temperature Tc. After this, let me explain one more question to you. Let's see this one. We have got a table, we have to match list with material and with its property. So we have got diamagnetic, we have got paramagnetic, we have got ferromagnetic, and we have got dielectric. Let's quickly solve it. Quick. See, I'll explain it. I'll explain it to you. We have got diamagnetic. First of all, for ferromagnetic materials, we know that mu r must be greater than 1, right? It should be greater than 1, and it should be actually quite, I mean, it should have large values than 1. So the correct answer for this one is going to be that mu r should be far more greater than 1 for a ferromagnetic material. Why? Because it gets strongly magnetized. Mu r is actually the absolute permeability divided by the absolute permeability of free space, right? Got it. Which previous one, Ashish? You tell me, buddy. First, let's solve this one. For paramagnetic, the mu r is actually greater than 0, but it has got small positive values. Is that correct? Small positive values. So this would actually mean that for paramagnetic, it would basically mean, would this be correct that it is greater than 1, but it has small values? So I think for paramagnetic, correct answer would be 1, and for ferromagnetic the correct answer would be, so the correct answer for this one is going to be 4th, and for paramagnetic the correct answer is going to be 1. Quickly write down in the chat box if you are following what I am trying to say. Quick, write down in the chat box. So for C, we'll have as 4th as the option, right? And for B, we'll have first as the option, which pretty much makes A to be the second, that is, it will be actually less than 1, and for dielectric it is just equals to 3. So the correct answer is going to be option A. This is the correct one. Quick. Answer in the chat box. Are you following how to solve problems like this? Got it? Alright. What about this one? For paramagnetic substances. For paramagnetic substances, correct combination for relative permeability and magnetic susceptibility of a paramagnetic substance. Again, both the things are going to be positive, right? This is 0, this is less than 0 for only diamagnetic substance. For only diamagnetic substance, this is 0, right? So it would be greater than 0 and this one will also be greater than 0. So the correct option is should be D. Is it correct? All right. So I think we have almost completed everything that's in this chapter also. Now and the Earth's magnetism is not in your course right now, right? Now tell me if you have any more doubts from here. Yes. So that will be all for today. I'll soon come up with some more chapters, so don't worry, right? So hopefully you have understood everything. To actually get through the first part of your NCERT, please start from the very start, that is electric charges and fields, and go through it all over again. And whenever you start electric charges and fields, go through every derivation, try to solve each and every derivation. Then as soon as you come to magnetism, you will revise everything, right? You revise everything that you have done in the last class, in the last chapters, right? And for I think current electricity, I have explained each and every derivation. There is nothing, pretty much nothing left. We have left with EMI AC, that I will come up with some other time, because that will take, I think it will take a lot of time. Got it? So will that do? With this, I'll end today's class. Thank you so much. Then I'll meet you in the next class. Alright. Thank you, dosto. Thank you. Bye bye. Bye everyone. Bye. Bye. Good night. Bye. Bye. Thank you. Bye. 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 All the best for everyone who has their exams. Bye. Bye everyone.